Thank you so much, and thank you for having me here at this workshop. So yeah, I'm not exactly sure what I mean by an optimization perspective, but hopefully we'll figure it out as we go through the slides. Oh, okay, takes some time. There's like lots of people that kind of influenced me doing this work, and this is just a subset of them. I couldn't fit everyone on the slide, but yeah, like I'm going to talk a bunch of papers, and these were people I worked with to get those papers done. So I wanted to start by first discussing like, okay, what is continual learning? What exactly are we trying to do, right? So it's always nice to have some kind of framing and then build on that. And yeah, sometimes this, SKCD stuff, they don't necessarily match the title, but they're fun, so I just put them there. Okay, so one way to think about continual learning is to think about inference. And I think I had this slide like a couple of years back. It's been sort of like one way I've been thinking about the problem for a while. I'm not sure if it's still necessarily the right way or the only way, but like one thing is to just think about gradient descent because that's what we're using and try to think how gradient descent actually works. And if you're just thinking mechanically of what's going on, and if you're thinking about like, okay, I have a mini batch of data points, and I'm trying to compute the gradient, what I'm really doing is for every weight of my model, I'm independently asking the question, if I increase this weight by a little bit, would the loss go down or not? So you're just asking these questions independently, and then you're kind of summing the outcome, right? So you can basically think as if each example in your batch is voting of like, oh, I want this weight to go up or I want this weight to go down. And then when you sum them is, each example is pulling on the weight in one direction, and then there's some equilibrium happening. So there's this kind of tug-of-war dynamics that is going on between the data points that are trying to, coerce the weight to do a particular thing, whatever they want. And this is sort of one of the main sources of issues that we have when we start doing continual learning, because, you can ask yourself, well, what happens if at some point some of this data is not there to pull on the weight? Well, obviously the other guys are going to be able to pull the weight all the way wherever they wanted, and that's sort of where forgetting is happening, right? So, this is why. So, like we kind of like this kind of idea evolved also partially from this work led by Tom Scholl and Diana and others, where we're trying to sort of understand how this interference is happening, and we're looking specifically at the RL setting, and the RL setting is a bit more special. And in some sense, the whole story that we had in the paper kind of only fits the RL setting, though I think exactly the same thing is happening in supervised learning. It's just a bit harder to see why that might be the case. So one thing that's special about the RL setting is that the strength of the learning signal, whatever that means, it depends on the performance, and it has this inverted U shape. So in the beginning, you don't have a lot of learning signal because you're not seeing the right states, right? You're just kind of stumbling around sort of in your initial state, and you just don't see the rewards to get learning signal. At some point, as you're starting visiting more and more of your state space, the learning signal gets stronger because you start seeing the rewards, so you can really start learning. And then the learning signal goes down because you're close to convergence. So basically, there's not much to learn. So, the gradients vanish as you approach some kind of minima. So, yeah, we had this kind of, I don't think I have a lot of slides on this, but we had this kind of like graph in mind of like how the learning signal interacts with performance, and then you can think of like what happens if I'm learning two tasks at the same time. So here, like intuitively, we're trying to think about like learning to play StarCraft with Protoss versus with Zerg. And what happens is that initialization, one of them will be slightly better than the other by chance. And then if there's interference between the two of them because they're fighting to use the same weight, same weights, the same hidden units to do the same thing, then one is going to be stronger. It's going to have a stronger learning signal because the performance is slightly better, and it's going to push the other one down. And this comes out of the simulations as well. The simulations are done with bandits, so there's no StarCraft here. But what happens when you start playing this out, you see that even though you're trying to do multitask learning and you're presenting all of these tasks at the same time to the system, you're learning them sequentially. And the ordering depends on the difficulty of the task, but there's also like quite a bit of randomness in there. So it depends on the initialization as well. And if you do many of the simulation, you get this sort of graph of how you solve the two tasks, and that's why we call this the ray hypothesis, because to Tom this looked like a ray fish. So okay, this is the perfect perfect naming for this. But the point is, or the high level intuition here is that it turns out that if you say, like, I don't care about sequential learning and I'm doing continual learning, it turns out that even if you do multitask learning and you check how you're learning your tasks, more often than not, you'll see that you actually learn them sequentially, which in some sense is kind of problematic.
Could you explain its colors a little bit? Like, sorry, are you starting at the bottom?
Yeah, so this is the performance on both tasks. So when you start with performance close to zero. So you're starting somewhere here, and then sort of by chance you either improve the one and then you move to improve the second, or the other way around.
Blue and red, what are they signifying here?
I think it has something to do with initial conditions, but I forgot exactly the details. I don't know if they're. Okay. Yeah, sorry.
In this case, like, they're all equivalent paths, is it?
Yeah, roughly you'd end up converging equally fast. It is not like there is no claim here about like, oh, one way being slower than the other. It's just the whole point is that you always see this plateau in one of the tasks where you stagnate in one of the tasks while the other one improves, and then like it kind of switches around. Once you've learned one task, you can start making progress on the other. So this is like it's a like older paper. I don't remember all the details, but this was the high level idea. And then I think this is kind of happening in supervised learning as well. Like the reasons for why it's happening are a little bit harder, because you don't have this kind of learning signal behavior that I was telling in the beginning. So you can motivate it in the same way that, one is kind of dominating the other. But we do this kind of plateau, we do see this kind of plateaus in learning more often than not. And you have sort of, even prior to our work, you have the work from Andrew Sachs that is trying to analyze deep linear system. And he's making the same kind of claim that actually, if you look at a deep linear system and you're trying to analytically look at the dynamics of the learning, you see that you're going to learn the different modes of your covariance matrix of the data. You learn them sequentially according to the magnitude of the eigenvalue, which is roughly the same thing we were saying before. So this phenomenon is happening even in, I think all you need is to have a deep model. If you have a shallow model, this doesn't necessarily happen. But as soon as you have a deep model, you kind of see this behavior, and you see the same thing in practice. Like if you do multitask learning and you start monitoring the losses, sometimes you do see that you actually learn them sequentially. It doesn't always have to happen. It has something to do with interference. So as long as you have interference, you're going to end up learning them sequentially. So this is the framing I've been thinking in the last couple of years for continual learning. So. Oh, yes.
Why do you think this is not a problem with shallow networks if you do multitask learning?
In a supervised setting, I think in a deep model, somehow the intermediate layer acts as a kind of bottleneck that prevents you to learn one of the tasks, while I think in a shallow model, this would be resolved much faster. I haven't actually played with it. I just sort of a hunch.
But how are you defining task here in like a supervised setting? Is it like every class can be seen as a task?
Yeah, so this is going to be a point I'm going to make later, which is there's no semantics to the word task. So as long as you have like an objective that you can measure, you can check different objectives and see sort of how they perform differently. But I think fundamentally, actually this is the point I wanted to make on this slide, is that you can take any task or any problem you're solving, like ImageNet, and you can think it's made out of like hundreds of subtasks that you don't know exactly what they are. And then when you're actually learning ImageNet, you're going to learn the subtasks sequentially. So it does feel like the point is that you're going to waste a lot of compute on the subtask that you're not improving on at all while you're learning one subtask. And if you'd be able to actually learn things sequentially in the proper way without like having catastrophic forgetting or whatnot, the whole argument of this perspective is that you should be way more efficient, right? So that's what I meant when I said, well, catastrophic forgetting can lead you to really fast learning, because my intuition here is that whenever you learn something, on a lot of data points, you're making no progress, but you still need to do the forwards, the backwards, compute a gradient, and so forth, and that is just wasted compute. And we do a lot of that. And this is potentially the fundamental reason why deep learning is so like compute inefficient, if you look at it, because a lot of that compute is really just wasted in this process. So if we would be able to figure out how to order the data in the right way, according to initialization and everything, like which are the data points that should be learned first, and somehow learn them without having the forgetting, then that would be ideal, and that would be super, super efficient. So,
but it's like, sorry, this
yeah.
again, but it seems like chicken and egg problem. If you knew, let's say, if you have a matrix, let's say, and you know the S3,
yeah,
then you know that if you use constant step size, maybe larger eigenvalues you learned before. But if you know it, then you can do it. But that's what you're trying to learn. So I think it needs to be somehow iterative, but I see your point. Sorry.
Yeah.
That'll get here.
I mean, I think it depends on the level of granularity and how you approach this. There's definitely, and I think, I guess sort of this is the point of curriculum learning and what they're trying to do, right? So there is a level of granularity where maybe you can sort of figure out beforehand what would be a reasonable ordering. I think, so for example, in the examples that we had with the bandits, like, the initialization and everything had like a preference of which of the two tasks would learn first. But I don't think that matters. Like if you force the system to say, well, learn with Zerg first, even if you had the wrong initialization, I still think you would do better. I mean, like in the initial few steps, you'd figure out how to correct sort of things so that you can learn Zerg, you learn Zerg, and then you switch to Protoss. So I don't know if it's that big of a problem. I think the bigger problem is that we don't know how to do this sort of sequentially. So the summary of the slide is, I think HGD has this tug-of-war dynamics, and this is what enforces you to have ID data, and catastrophic forgetting, it's a failure of what I call credit assignment. I think it's kind of like an overloaded word because in RL it means something specific, but in like what I remember, well, at some point the word has been used to mean like how do you decide which weight is to blame for what error, and that's kind of the semantics I'm using. So when I say credit assignment is deciding, how do you propagate credit within the architecture. So how do you decide which weight is supposed to, or which feature is supposed to respond to what part of the observation, and that's sort of the bit that we don't know how to do differently. Maybe I'll come back to this, but I think there's like no explicit knowledge composition. So when we're learning things, we're not learning things in the form of like, oh, looks like A plus B, and I'm composing them, and now I know how to do C. The learning is like explicitly not compositional, and that's problematic because that's why we don't get sort of this accumulation of knowledge and sort of faster and faster learning as we go forward. So yeah, all of this I think come down to HGD, and fundamentally like continual learning, in my view, should be also about gradient descent and figure out how to fix gradient descent to do these things. Just a note on that. So we did these papers with Merdad and colleagues, and it does seem like scale changes things a bit. So like if you look at the amount of interference that you get between data points, that things goes down as you make the model wider and wider. And it also changes with architectures, but it never goes away. But yeah, I mean, to a certain extent, you can make things easier on you if you just scale things up. And kind of goes back to this thing that scaling up, somehow interacts with things maybe to a certain, to enough so that people think that it might be part of the solution. I don't know if it's the solution, but it definitely, you get less interference. If you do, like we found out that, for example, in vision, people use ResNets. If you don't use ResNets, without any kind of continual learning algorithm, you can get similar performance as ResNets with that algorithm. And big reason is like ResNets are horrible at catastrophic forgetting, but if you use VGG, I think VGG just doesn't suffer from catastrophic forgetting in the same way. So, which is, like it's sort of how things are, but you have to be aware that your choice of architecture and the scale of your model will affect how much catastrophic forgetting you see, how much forward transfer you see, and so forth. To a similar degree to say like EWC or other things. So it's not negligible the amount of difference you see. Okay, so trying to move a bit faster now. So we we started with this hypothesis, and we're like, okay, let's look into how to exploit this and get things to work. So one thing that we did, and this was in the RL, was that we had this paper that was kind of making this claim that solving catastrophic forgetting slows you down, so it doesn't really help you for transfer. So what we specifically did is we looked at this kind of like distractor tasks where you have something like ABC, where A transfers to C. If you just do fine tuning of a model trained on A and C, it works. But then, if you try to fine tune a model trained on B on C, it doesn't help. It hurts. It slows you down. And you want to see, okay, if I put B in the middle and I have some kind of continual learning method, would this help me? And we did this. So this was the continual world paper. So we did this in RL. So it's a lot of meta world tasks. So we create this transfer matrix, and then we created sequences of tasks based on this transfer matrix to have this kind of distractor behavior. And we've seen that basically none of the continual learning methods really help you for transfer. Like the best thing to do is to use no continual learning, because somehow, even though you solved the interference, basically you had this constant force that was trying to make you remember A and B that was strong enough that made progress on C slower. So I think kind of that's the point, is like any kind of continual learning method that is trying to prevent catastrophic forgetting will somehow slow you down, because if you account for the compute and the time you spend to remember, like if you do replay and you actually count the replay in the amount of stuff that you do, you need to do enough replay to remember that thing that would actually slow you down in how you learn.
I mean, you're learning more.
Yeah, you're learning the mixture. Yeah, so it's not the same as fine tuning. But when we started, when I started, I was saying well, if you fix catastrophic forgetting, maybe now you can learn faster. So at least the way we're fixing it is not helping you to learn faster. So there has to be a different way. We did, okay, the slide changed slower than I expect. So we did have this follow-up work now that we're looking at just transfer from A to B. And it does seem that, so now there's no distractor setting. And it does seem that, and here you can easily imagine scenarios where actually catastrophic forgetting techniques will help you, and they help you in practice. And the idea here is that if I'm thinking about fine-tuning a policy that was trained on task A to task B, and task A somehow leads to you to have a good policy on some part of the state space that is maybe not where you're starting, then maintaining that policy there is going to be useful. Because what happens is as soon as you start task B, because you're now exploring around where you're starting, while you're learning this, you're going to forget how to behave in that part of the state where you knew, and when you get there, you're going to have to relearn it from scratch. So we had this kind of task where you had to learn to move I don't know how to call that, like a little box, the red thing to the blue, from the blue thing from the corner to the other position. And then you had to do the same thing, but first you had to open the drawer. So first you have to learn how to open the drawer, but then you had to execute the same motion that you had before. And then if you do, if you add anything, like EWC, whatever you want, if you add to the system, the transfer would work better. Another scenario that is kind of interesting is when you have, so this is the first scenario, when you have this state coverage problem. So where your pre-training task helps you to learn policy on states that you're not going to see as you start learning on the second task. And the other thing is when the fine-tuning task is kind of similar to the pre-training task, but there's some perturbation, some change, and then sort of the policy is not perfect. And I hope it's on the, okay, this is the robotics task I'm going to skip. But I'm going to go to the NetHack, which is more of the second thing. So what happened on NetHack that was kind of interesting is, so when you have sort of this pre-training done with offline RL, you have this non-parametric or this kind of handcrafted solutions that you can use to collect the data. And these solutions, collect data. This is sort of the distribution of the data over the level. So this handcrafted solutions, they can go up to level 10 and you collect data from all kind of levels. But then after you've done offline training on this data and you deploy this policy, and you check the visitation, like this policy only gets to room 3 because there's some like small changes and it's not perfect. And now if you want to like online fine-tune this policy, to continue improve it using the proper RL loss, what would happen is because you're seeing 1, 2, and 3 a lot more than everything else, you're actually going to lose anything you knew how to do there. And then, by the time you know how to reliably get to level 5, you basically have to relearn how to work in level 5 from scratch. And in this kind of settings, if you add any kind of continual learning mechanism, again, you get some forward transfer. So these are the kind of scenarios where it works. And then the other thing I wanted to talk about is, so like if you change granularity, and now we're going back to supervised learning because maybe it's easier to think there, like back to the discussion we had before, if you just have a big data set like ImageNet, you can think of it being composed of multiple tasks, and you can think like, okay, is there anything I can do there to make things work? And in particular, like one thing that emerges when you try to learn things on ImageNet, and this has been reported many times, this is just a few more recent papers, is you have this behavior where you have easy examples and hard examples. So as you learn some things, you learn really fast, and for some data points, you have to go 10, 20 times over the data set to actually learn them. And the idea here, it's potentially not even new, but the idea was kind of simple, was saying like, okay, let's just think of the easy and hard as being 2 different tasks. The easy ones, because you already have 0 error, is the first task that you already solved. Can you now just focus on the second task, the hard examples, and have some kind of continual learning mechanism to make you not forget the easy ones and kind of move forward? So basically the idea is split the data according to the error, and you can, you have your choice of how to define this. So this idea, to be honest, is actually inspired by this paper, Selfie Boost from Scheisele-Schwarz from 2014. It's been on arXiv since then, never been published anywhere else. And I think there is a reason for that. I think there's something that doesn't work, but it's a paper that kind of obsessed me for a while because it just made a lot of sense. This paper came before EWC, but if you look at what he does, he's basically doing EWC to prevent catastrophic forgetting. So it's really like exactly what you'd want to do.
So like beta is a threshold or something, and then if your error is more than that, then you add it somewhere.
No, so this is going to be sort of you're going to use this as a binomial to sample, and beta is sort of just like a floor so that you always sample things. So you can't say, okay, there's going to be some data that I'm never going to look at. And then, because the error is somehow bounded between 0 and 1, because it's like an L1, and it's depending on your choice of things. So the way we did this, so this is very similar to importance sampling. I have to draw that parallel as well. We just didn't use that motivation and didn't phrase it that way, but you can phrase all of this as importance sampling. So the difference to importance sampling, what we've done here is we do this per epoch. So you start with your data set, and each data point has kind of like a weight that it's 1 for now. You use that to sample, you create your batches out of it, you do your updates, and when you do your updates, you update the weights for each data point that you're seeing, and then you go to epoch 2 and you sample again, and then you create your batches out of that. So the point here is that you always have batches of the same size. So it's not like in importance sampling, you start with a big batch, you subsample it, and then you compute your update, and you keep going that way. Here is you sample once at the beginning of the epoch, you create, and then you treat it as a normal data set. You do all the tricks you have to do to push things through, and then you only update the importance weights of the data that you actually visit. And for everything else, you use stale importance weights, and that's fine. And this process can be quite efficient and quite scalable. You can do this at any scale you want. Yeah, I guess so, yeah. So we've done this, and initially it looked like it was kind of working. So the green line was the thing that we're doing, and here, like this plot, I'm just making the point that like if you're looking at number of epochs, we actually end up doing a lot of epochs, but all epochs like shrink a lot in terms of size, because most epochs you're just looking at the hard examples with a small subset of the easy ones, so you don't forget them. But then overall, if you're looking at training step or time, where it seemed like we're doing better, but then the negative results came later, which is when you start doing this with ImageNet, you find out that there's like a weird interaction between the learning rate schedule and this procedure. And one thing that this procedure does, if you try to adjust the learning rate correctly, it just makes the learning rate schedule much more aggressive. And then we run a baseline, an ablation study, where we said, like, okay, let's make the learning rate schedule more aggressive, but replace data with IID sample data from the entire data set. So we're not prioritizing hard examples. And we find that just this more aggressive learning rate schedule gives you like 80% or so so it's like the green versus the red there. So our green is like slightly better, maybe, but basically 90% of the performance doesn't come from your selection of data, but really just comes from having an aggressive learning rate schedule. So basically this is where we stopped with the project. I mean, I think there's still something there. So you have like a dynamic way to figure out the learning rate schedule based on how much you've learned so far. So basically on the kind of errors you get on your data, but it's not what we wanted. It has nothing to do with the continual learning and the hard, easy example thing that we started with. Okay, so now I'm kind of moving in the second part of the talk. So this was about the interference and sort of this kind of behavior and how catastrophic forgetting can help to do forward transfer and why that's maybe a nice way to think about it. So I wanted to go back on the definition and talk about like why I don't think now continual learning is just about this interference and this tug of war dynamics and how things have changed. And I think this came from like a lot of discussions. So part of these discussions came with a bunch of RL folks. So like, for example, Rich Sutton has been pushing this perspective of the world is bigger than the agent, which kind of influenced a lot of people, and sort of they started thinking of continual learning that way. Yeah, I mean, this is a kind of a different perspective. So here, the perspective is the world is always going to be bigger than what you can represent. Therefore, even though the world might be stationary and there's nothing nothing like that going on, like no stationary going on there, you're learning for the agent that things will look non-stationary because the agent can only like locally fit whatever the data is, and then when it moves somewhere else in the world, it has to like unlearn what it learned before so that it has enough capacity to learn the structure locally there. So there's this kind of intuition that in the limit, no matter what we do, we'll have to do continual learning because there's not going to be any way for us to build a system that's large enough to encode everything that is there to be encoded. So this is kind of the hypothesis, and this kind of perspective pushes you to think a lot about plasticity, and that's why I brought it up, because once you start thinking this way, it becomes apparent that one thing that you need to think a lot about is how do you unlearn, and then sort of what happens when you run out of capacity. Are you going to be stuck and unable to learn something new, or are you going to get into this kind of catastrophic forgetting? And there's this paper that I cited, which I think is kind of formalizes this idea quite well. And it's kind of really nice. It starts from the first principles.
Sorry, why is this not interference?
Yeah, it is interference, but I think once you have this perspective, you start also thinking about like plasticity and other stuff. I mean, I guess for me, when in the previous slides, at least, when I was thinking about those things, I was really thinking about like, okay, there exists a multitask solution to everything. The only issue is that there is interference between tasks when I'm trying to figure out this multitask solution. So if I find a way of resolving that, that's fine, and I can converge to this multitask solution. Here, the point is there is no multitask solution. There's no solution that will cover everything. So all you can do is locally fit the data, and then you have to think of like what would happen once you move on into a different mode of the data or anything like that. Yeah?
But then future and past are interfering.
Yeah.
So similar question. Is this basically going to be like some RIKEN kind of thing in theory, or?
In this particular paper?
Yeah, like in general, I guess it's like future. Is this going to be like some DP thing where like you say the world is static and it's partially observable?
So in the formulation, so not necessarily. So it can be like done like a information bottleneck kind of perspective. So I think that was the so the formulation in the paper I cited is more like Bayesian, and it's more about like information and capacity and stuff like that, and sort of. But you could phrase it as a POM-DP. I mean, I think it's sort of like an active area of research, and maybe Adam or others will have more thoughts on where this thing is going. But you can definitely view it that way. I mean, I wanted to say that I have issues with this view. So I brought it up, but like I actually, I'm not necessarily buying that much into it. And the way I see it is like, it is sort of the right way, like this perspective and sort of this kind of theory that you build here, definitely you can use it in the same way you use the universal approximator theorem to say, at some point you have to deal with continual learning. You know, there exists, no matter how much you fix all other things, at some point you'll end up into this setting where you just don't have enough capacity. So you will need to have some kind of forgetting, you'll need to have some way of dealing with all kinds of things. But what I don't agree with is that this is the reason why we have the problems that we have right now. I think almost all of the problems that we're seeing right now, they have nothing to do with capacity. I think people heavily underestimate the capacity of a neural network and how much stuff it can store. That's one thing. And also the view, it's a bit misleading because even though the world is huge, acting optimally, the policy itself of acting optimally in that world, we have no idea how complex that is. Maybe the optimal policies actually can be encoded in very few bits because it's, you know, you don't really need to understand everything about the world in order to be optimal. You can, in some sense, skip something. So I think there's some kind of issues. I mean, there's not issues with the perspective. I think there's, the perspective itself does not tell you why we have the problems that we have.
One question?
Yeah.
Shouldn't we also think about representation learning? So the power of deep learning is that we learn these compressed, layered, abstract representation of the world, so we don't need to fit like the details, but our agent maybe learns a very abstract representation, and then having a good representation helps you very quickly adapt to your current situation. And I haven't seen in the whole talk yet anything about representation learning, so I'm just curious if you could comment on deep representation.
So I guess this kind of goes towards what I was saying in the sense that the optimal policy might not need that like a lot of bits to encode, in the sense that like, you know, you just need to represent certain things in an abstract way to kind of figure out what you need to do, which I think is your point. That I haven't really pointed out here, but you're correctly right, is that system can also adapt on the fly, which is sort of something different than this. But you have, and I'm bringing that out because adapting on the fly. So if I have a transformer, then you're just like, you know, evaluating the transformer on some data, there's going to be in context learning happening. So there's going to be some kind of adaptation that happens by just doing inference. Like you don't need to explicitly have some kind of learning mechanism that it's happening at test time that will keep your system up to date. It turns out that, you know, if you have memory, these systems can sometimes end up having this kind of like adapting perspective. So another kind of perspective in this space that I like a bit more than the world is bigger than, but I had to bring that up because I think it's kind of, it's a very useful, but like also like a big kind of part of the RL community. I think is thinking a lot about sort of the setting of the world bigger than the agent, and it's something that we need to consider. And it does give you some like solid foundations of why you can't escape continual learning and you have to do it. But like another way of thinking about that, I think I find it's a lot less formal, and I don't actually know what it means, but I find it might be more useful, and kind of building on the sort of, this will be the new thing that is trying to replace the tag of war dynamics thing that I presented in the first slide. That was sort of what I was doing 2 years ago, is this idea that like what we're doing is some form of tracking. So you can think of the problem as tracking, and I think that's kind of interesting because and this was actually brought up by Rich Sutton as well, because he was kind of complaining to me when I was talking about continual learning that I kept using words like loss surface and stuff like that. And he's saying like, there's no loss surface because there is no, you know, there's no loss, like things keep changing all the time. So I think it's actually quite interesting if you think of things as tracking, because some concepts from, you know, traditional optimization, they might not really make sense as easily. You know, you don't have a static objective so that it has a loss surface. Like the loss surface is dynamically changing as things are changing. And I think in general, I think it's kind of nice to think about that. I'm going to talk a little bit about like what comes out of this, but you know, you can also think about like, oh, the generalization that we were complaining yesterday that it's very ill-defined, but you can think about like, okay, how can you evaluate these systems and how you can think about sort of what they do when the distribution is changing. And I wonder whether like the speed of adaptation, it's a better metric than things like zero shot or anything like that. So you can, you know, it can help you change the perspective of what you'd expect from a system. I also want to bring Thomas Griffith's work because I really like it, and I think it's, so this is like cognitive science. It's a bit kind of different, but I find it quite motivational. Where he has this, like he has this whole paper trying to figure out what's the difference between humans and machine learning and, you know, AI, and like what you'd expect to be different. And he's arguing that like the profile of the human intelligence is due to the limitations that we have. Like we don't have a lot of compute, or we can't spend a lot of energy. So, the way we have to do things is, for example, what comes out of it is like we need to do things in a compositional way. But the argument that he's making is like, why does AlphaGo doesn't do sort of this decomposition of the Go problem into sub-problems, solves them to find a solution, is because it doesn't have to. Like if you train a system that's constrained, that cannot do as much compute as AlphaGo does, and then the only way it can solve the problem is to make it compositional. So his point is that a issue, or at least my reading of his thing, an issue is, for example, when we think about compositional, we're complaining why these compositional systems don't do better than the non-compositional one, or why model-based RL doesn't do better than model-free RL, is because we don't have the right constraints. When we're evaluating this, we're evaluating them in an unfair way. So the only way compositional system would work well is not because that's the optimal solution. That's the optimal solution under certain constraints, and those constraints have to be there. And the whole point here is that continual learning could act in that form. So like, why would you want to have a system that learns continuously? I guess if I paraphrase this, is because if you manage to do that, that would have side effects that might be interesting. Maybe a continual learning system will have to be compositional and hierarchical because it will have to compose solutions, and that's useful for other reasons. You might get the same performance on ImageNet if you run these two systems. You might end up spending more compute to do it in a sort of continual learning way, but then you have this hierarchical representation, you have this compositional structure that can be exploited for other things. So the point here is that why do we want to add these continual learning limitations to our problem? Maybe it's because there are real reasons why we have to do that, but sometimes it's also because this limitation will shape the kind of solutions we have, and what we're looking for is this sort of side effects of the solutions. So this slide kind of says the same thing, which is, kind of says the same thing, which is sort of this compositional generalization is something that we might want, and it's not clear that typical deep learning models do that. And particularly if you take sort of people actually even use this kind of, interpolation kind of perspective of how generalized. If you look at Belkin's work, he uses this word of like interpolation sort of as the regime we're in and stuff like that. And it's because it doesn't really have any kind of compositional structure to it, these models, and that could be quite problematic. So there is work, so for example, Sanjeev had this recent work where he's trying to argue that transformers are actually compositional, which is kind of interesting. I don't fully parse all his arguments, but he's trying to make the claim that because language is compositional, then transformers have to be compositional, and he's trying to show that this is happening in practice. So you can show transformers like new compositions and they kind of deal with it. And he has a statistical argument of why that has to happen. It's something about excess entropy, that there's no way of dealing with that unless you find this compositional solution. So I think it's an interesting paper, but, and then, kind of building on that, we're trying to look at like compositional, like when does this happen? And it turns out that there are some constraints on the data, so I'm not going to go into the details, or I can go a bit in details, but basically we're trying to figure out if you have a system like a hypernetwork, which by construction can easily represent compositional things, and you just give it data, will it learn a compositional solution? And it turns out that, of course, the data needs to have certain properties. Even the model is exactly, so the data is done by a teacher, which is a hypernetwork as well. So, and your student has exactly the same structure as the teacher. So there's no reason for you not to discover that structure. The student will not discover it unless you have a particular structure to the data. And in particular, one thing that we found is that you need to have this kind of, if you take any of the skills that you're composing, you need to have this path where, like, if you want to be able to compose A with C, you need to have something like A composed with B, and then you need to see B composed to C. And then because you have B in both things, like the system can figure out how to compose A with C. So, and there's some theory in this paper of why that could be the case. And then in this follow-up work with Simon as well, and Joa, we showed that actually, like people who work on mechanistic interpretation like to do this kind of things. Actually, you can look at the linear layer, and because it has this multiplicative structure, you can rewrite it, and it turns out that it looks exactly like a hypernetwork if you reorder the computations. So the question was, like, why do transformers show that they're compositional? Like, where is this compositionality comes from? And the point is, you can think your heads, if you have multiple heads in the attention layer, you can think of the weights the attention weights. This is true for a linear attention at least. If you look at the weights you have for a linear attention over the head's dimension, that's almost like your latent code that describes, okay, which components am I going to use? And what you're composing is over the head. So you can rewrite the, so the paper is out there, like you can see how you can algebraically manipulate the matrix multiplications, but you can rewrite them and you come out, I might have the formula on the next slide. Not sure if it's easy to parse, but you multiply things together and you get that the hypernetwork, the latent code is this weights that now you're doing it over the heads, and it's a linear hypernetwork, and the things that you're mixing is W out with W value. So those two weights, like they get composed together and those form like the, like if you remember hypernetworks is you have this latent code that you compute, in this case by a linear layer, and then you multiply this with this thing and you get the code. And it's kind of potentially, arguably, like this is how with this mechanistic interpretation works. This can explain how the attention layer can exhibit some kind of compositional behavior. So, like you need to have two things. Once you need to have the data, and language definitely is compositional, like everyone knows that, so the data does have that. But the other thing is you need to have the structure in the architecture that allows you to do some kind of compositionality. And it wasn't clear where that structure was. This paper is arguing that maybe some of it, at least, is in the attention layer, in how the mechanism,
I think my question here is essentially, even when you argue that your data has compositional structure and your model can do compositional things, are they having the same kind of compositional structure? If they have mismatch between the compositional structure, then you have no guarantee, or at least I don't have hope to let your network actually learn the right compositional structure.
Yeah, that is true. And the kind of compositional structure you get through this kind of manipulation of the attention layer, in some sense, is quite limited, right? Then again, like transformers exhibit this kind of in-context learning or kind of composition generalization sometimes, not always. So maybe, that's the reason why they don't exhibit it always, because some of this composition can't really be represented this way. This is just kind of hinting of what could be the starting points of trying to make some arguments why this is happening. I think the one thing that I kind of got convinced when I was working with this work was that initially I was dismissing the whole transformers can do compositional generalization completely. So now I do see it. So in explicit settings, in sort of controlled settings, they do exhibit that. And I do think we shouldn't ignore it, and we should try to figure out where it might be coming from. But yeah, I totally agree. I think there is a lot to be said about what kind of compositions we can represent. I mean, even when I looked in the sort of the papers, when I did a bit of literature review on this topic, I feel like even the defining sort of what we mean by composition, it's still a little bit vague. I think people in neuroscience, cognitive science like to do this kind of stuff, but I don't feel like they formalize it in the way I would formalize it, in sort of more of a mathematical sense, that I can actually look at things and measure and say this is what I mean is compositional. So I think there's more things to be done, but I think it's a direction that it's worth pursuing, and I think it's kind of connected with continual learning and fast adaptation, because compositional generalization can sort of shortcut some of the problems you have, and it kind of interferes. So this was another thing we've observed, which is if you just try to do continual learning, say on split CFAR or whatnot, but you use a transformer that has a context of just random previous examples, that changes a lot how your catastrophic forgetting behaves, how your forward transfer behaves, because now you have this interaction between two learning things, right? The in-context behavior of the system and sort of your normal learning dynamics by gradient descent. And we need to understand both of them separately, and we need to understand how they interact together. And I think sort of systems with memory is kind of what's going to happen in the next couple of years. We're kind of moving away of just feed-forward systems that don't have any kind of context. We're probably going to end up in a space where we're always going to have this hybrid models that have memory, and through that memory they either can exhibit some kind of learning dynamics. In the transformer, there's quite a bit of work also that argues that the attention layers act as some kind of non-parametric, k nearest neighbor kind of behavior. So now you have non-parametric models interacting with parametric ones in sort of interesting ways that again changes the whole like profile of the problem, and I'm kind of just arguing that we should look more into those kind of things. I still have 15 minutes. So okay, so now going to the plasticity thing. So one thing that came when you start thinking about the world bigger than the agent, or the tracking problem, or even sort of like the kind of Belkin's perspective of double descent, is sort of, you come up thinking about sort of this plasticity issue, and this kind of comes to the point of like, why do we think that when the data distribution changes, the system should still be able to learn? So I think when you think about the Belkin's double descent, sorry, I tried to make my slides as short as possible, so I kind of skip. I would have had like an entire story to get you here. But the point of Belkin's double descent thing, one way of interpreting all of his work that I find kind of interesting, I'm not exactly sure if he uses exactly this word in the paper, but to me, what he says is that initialization matter. This is how I understand it. So basically, you have these two sides. You have the classical regime that we all know, and then you have this modern interpolation regime that we actually operate in when everything is over-parameterized. And the reason why we're still improving generalization when we're in this regime is because now the solution that you get depends on where you started on. So that's basically his point, right? You always converge to the closest solution to where you started on. So your initial conditions are going to affect your end solution. It's not one fixed point. It's like now a complex dynamical system with many fixed points all over the place. And initialization matter. And the reason we generalize is not because we take the shortest path to the shortest solution that we have, is because we use the initialization that we use. There's something cooked in that initialization that helps us find the solutions that we have. So basically, maybe the simplest argument that I think is made in the paper as well, the initialization has small norms, so the solution will have small norm because we're going to look at something close to us, and small norms should lead to initialization. But the whole point here is that initialization matter, and we have full control of it when we're doing a static learning thing. But when we're doing a continual learning, we don't have control over it anymore, right? So where do we start after we do one task? We don't know. It could be in a part of the space that's really not good for what we want to do. And I think sort of the work of Jordan Ash and Ryan Adams is really in this space. So like Jordan Ash and Ryan Adams, and sort of, I think they I don't think they use the word plasticity, but we use plasticity afterwards to refer to their work. Their point is that if you do pre-training and then you do fine-tuning, you don't get the same generalization because you don't have control of your initialization when you do the fine-tuning stage, and somehow it doesn't have some property. We don't know what property, but it doesn't have some property that a typical initialization would have that would lead you to good generalization. So you have this gap, you lose something. And I think people have thought about this as loss of plasticity. Oh, I misspelled the word loss. And then, like, I think there's stuff to be done here. Even sort of understanding, basically what is important here is to understand what properties of the initialization matter. But I think what happened is that, people started getting excited about this, but then it turned out that they started focusing on something different. And that's sort of what people understand by plasticity now. Basically, there was this switch. I just wanted to bring that up as in, that's an unsolved problem. They're still out there. It's not what people call plasticity anymore, and it kind of died out in terms of research. People don't, and the reason, there are good reasons for that. So one reason for that is because most of the plasticity work kind of moved into the RL domain, and I think in the RL domain, the concept of generalization is not very clear. And people just avoid that word because they don't know what it means. Like, what does it mean to generalize? And because of that, you can't study the phenomenon that was on the previous slide. But what you study and what is kind of more, like comes more through if you take this other two perspective, is sort of the optimization issue where you can't reduce your training error. And that kind of makes sense, when you're thinking just about, if I'm thinking about the world is bigger than the agent and I'm thinking about the tracking thing, I'm not really thinking about generalization. I'm mostly thinking about like, oh, I need to encode, I need to cram all of these things into my agent. I don't have room, what I'm going to do. Or the tracking, it's really like an optimization kind of thing where I'm running after that guy, but I'm not discussing sort of generalization properties. So it's quite a popular topic in continual RL. And there's more and more work on it. So I'm mostly going to focus on the work that Claire did, because I worked with her on this kind of topics. And we're trying to understand, so initially, I guess people blamed saturating units for this, and there's lots of work that discuss saturating units and how can you replace them, how you can reset them, and so forth to deal with this. I think what we started doing with Claire is trying to look at this from an optimization perspective. And what we're trying to claim is that it's not about saturating unit. It could also be about ill conditioning of the curvature, whatever that means. I know some people disagree that there's a concept of curvature when you have non-stationarity, but there's some kind of ill conditioning of the system that makes the optimization process break down. And that could be even if all your units are not saturated, right? Like it just, your Hessian has, like a weird condition number. That's one thing. The other thing is plasticity, loss of plasticity is not always bad. And that's something people need to kind of also agree and kind of acknowledge. So I think in the community it's always dealt with as, okay, if I lost plasticity it's a bad thing, I can't learn anymore, that's it. But if you look at supervised learning papers, I don't think they use the word loss of plasticity, but they study this thing and they claim that this is why the system generalizes. And it's actually a key component of the deep learning dynamics is the fact that it can throw away directional variations that are noise. And then that's why you have robustness when you're trying to predict. And you can see this in RL as well. So you can have policies that are lose plasticity under some metrics, like, you have low rank of the features or whatnot. But those are policies that generalizes quite well, because if you add noise to your observations, or you see some observations that are slightly different, the agent will just ignore those variations and will act quite well. So the fact that you have a lot of saturated units, or the fact that you have low rank, it doesn't necessarily have to be a bad thing. And there is a problem here when you're trying to fix loss of plasticity, where you need to identify whether that is harmful or useful to your policy. Or to the agent that you train, because you do want to have this kind of contracting behavior to kind of be able to get rid of the noise. We also did this paper where we were talking about loss of plasticity as a way of doing pruning. So you can encourage the system to lose plasticity so that you can actually prune it and compress it, and it's actually more efficient to do it in sort of this soft kind of way of doing things. And in the work Claire did, we also pinpoint to these 3 reasons of why we think you get loss of plasticity. Okay, 5 minutes. And they're all kind of in this kind of derivation and this kind of perspective, they all have to do with optimization. So you have this regression target magnitude issue. So if your targets change in magnitude quite a bit, what it turns out is that the model doesn't really use the biases to correct for the change in magnitude. So just think you add the constant to all of things. This goes into the features. And that's why your features become ill-conditioned, like all your Hessian becomes ill-conditioned. It's kind of interesting. I would have expected that the biases would correct for this, and that's why we have biases, but somehow they're not doing their job. The other thing is pre-activation distribution shift. So basically, the way deep learning works, they always make strong assumptions on things. Like the activations that we use, like ReLU and so forth, they make specific assumptions on their input distribution, which is 0 mean and kind of standard, like variation 1. And if that breaks, the activation function doesn't work anymore. So what can happen is you either get that unit, but you can get a different behavior, which is basically your unit is always linear. Like if you'd have a ReLU, we call this zombie unit. So you can get these units that always are linear. And if you imagine all your units are linear in a layer, you basically lost that layer, right? Because now you have 2 linear operations out of the other, you can compress them into a single linear layer. So actually not having enough nonlinearity in your activation is problematic from an expressivity point of view, and that can happen, and you can't detect that by just looking at dead units or things like that. You can't really tell easily if the unit is too linear or anything like that. But you can control the activation distribution before, and you can ask it to be in whatever the activation function requires it to be. So and the other thing is the parameters norm keep growing, and this again affects the Hessian. So you have this behavior and gradient descent that just likes to grow the normal parameters no matter what, and that would affect sort of it can lead to vanishing gradients, or it can lead to exploding gradients depending on where you are. And I guess sort of in the work that Claire has been doing, what we're trying to push is this sort of idea that loss of plasticity, it could fully be understood by just thinking about signal propagation problems in deep learning. And that's something we were studying, early 2000 was the main thing, how do you get neural networks off the ground? You need to make signal propagate through them. So, can we use some of that? And should change. How did we solve this in deep learning in the early 2000s? Initialization played a big role, and then sort of the activation function that we use, but like more recently, I guess the main thing is normalization. That's the main tool that we have to ensure signal propagates well. And I guess in our work, we're asking, like, why is layer norm not enough? And it turns out the layer norm can deal with most issues except the weight norm growth. So it just doesn't affect how your weights grow. It just makes the forward be normalized. So your signal propagates okay, but your weights could be large. And that has like an interesting effect that I never appreciated, which makes the effective step size to vanish. So if you think about the gradient on a weight, because you have layer norm, it turns out that this gradient is going to be multiplied by 1 over the norm of the weight. So if the weight grows, the gradient vanishes. And you have this weird behavior. So we proposed this new normalization that we call NAP, which is just basically layer norm plus weight projection or weight standardization, because that's the one thing the layer norm doesn't do. And this works quite well. We had like a surprise when we tried it on RL, because it turned out in RL people tend to use constant learning rate because they assume you have to always learn. It turns out that in RL, if you have layer norm, you actually have an implicit learning rate schedule because of this behavior of the weight growing. And the reason you get good results on Atari is because of this learning rate schedule. So basically what we had to do if we use layer norm and weight standardization is we also had to add a learning rate schedule to RL, which is kind of counterintuitive because it basically says, well, I have I have a number of steps, and in that number of steps, my learning rate will go to 0. So that's when I'm going to stop learning. So it was a bit, yeah. Okay, a few minutes. So last thing that we had this work, I wanted to present it because it's sort of maybe more in the vein of what you guys like, but I don't have a lot of time. I'm just going to put the slides out there, and I'm happy to talk a little bit about it. So this was another, so I guess MT asked me about this. This is the Kalman paper. This is very related to the Kalman paper. It's almost like a follow-up. The Kalman paper just had the Kalman filter on the output layer. This is like looking at the entire weight. And the motivation is more like, oh, if we're looking at gradient descent, you have this regularization to theta t, and this is not okay when you have non-stationarity, because if your target moves very fast, you can't react to it. You always have to stay very close to your previous solution. So the idea is, can we change the target of this regularization in a proximal form? And people actually have done it in online learning, and we kind of just do the same, but do it for deep learning. And the question is like what you want to do. So Michalis did this really nice visualization for those who like these things. Okay, I'm going to try to explain it because maybe it's a bit easier. So the idea here is what we decided to do is something like if we detect that the data has changed, we just want to diffuse the posterior, because what happens is in normal learning, like posterior kind of concentrates as you're approaching your minima, and then you start moving less and less because of that. So what we want to do is to have some kind of drift model. So we have some kind of model that tells you what should, before seeing the data, what should theta t plus 1 should be given theta t. And we use this drift model to basically like diffuse our posterior every time we think there is a change. And we use this process that I've never heard before this work, Ornstein-Uhlenbeck, for those who knows this stuff. But it turns out that we use this process because basically what we wanted is a form of soft reset. So what we were looking for is really like some kind of interpolation between initial state and sort of where we are, because we make the strong assumption that the initial, the initialization is maximally plastic. And so that's where we want to go if we don't know what's going on. Like if we feel like, okay, things have changed too much, we just go back to initialization and relearn things from scratch. You can work all of this through, I can talk about like how you work this through, but in the end you get this update. And I think what's nice is if you think about shrink and perturb and other methods that kind of have this vibe, it ends up looking a lot like this. So it ends up being quite connected to hard resets, like continual backprop and all of this stuff, and sort of things like shrink and perturb. The difference here, you do similar to shrink and perturb, you basically shrink your weights, but you also compensate the learning rate. So it turns out that you also have to increase the learning rate. The more you go towards theta 0, the bigger the learning rate becomes. So And there is a way of how to do this properly, right? If you start with those assumptions, you get the exact correction of your learning rate and everything. Like you don't have any hyperparameters, just sort of comes for the formulation. So you have this very simple thing where you have this eta that controls how much you move to theta 0, and then based on that eta, you get sort of also the learning rate. And the other nice point about this work is that we actually learn eta from the data. So we're looking this like one step look ahead kind of predictive likelihood, and we use this to learn eta online as we're learning everything else. So the point is you don't have to control the soft reset, you just kind of run this forward and it automatically decides how much you should move the parameters back to the data versus how much you shouldn't. And it turns out that it works really well on standard plasticity benchmarks. That's where we kind of stopped. We're not exactly sure. So the way, the framing is good. I think the choice of the process and the choice of objective to learn eta will decide how useful this is and what it is useful for. And the choices we've made are kind of very specific to plasticity stuff. And then when we run it on other things, like we tried a bunch of online learning problems and so forth, it turned out that it didn't help because, well, we're not addressing the right problem. So I think the big challenge here is like, okay, can we come up with like different processes, different objectives to learn eta to do other things like maximize forward transfer or whatever else we want to do, because this is very myopically looking at the plasticity loss kind of thing, and it works there as advertised. And then with that, conclusions, just to repeat, again, CL or catastrophic forgetting can be seen as credit assignment in neural networks, and if we fix it in an ideal world, should lead to very fast learning. And this could be one target for continual learning community. You just say, we want to speed up your LLM training by not forcing you to waste that much compute on data that you're not making a lot of progress on. Gradient descent does not explicitly do knowledge composition, which I think is problematic. And we need to think about it and how to bring that back in. I think otherwise we're not going to make a lot of progress. And I really like this sort of tracking perspective. I don't think the last bullet point is phrased correctly, but basically I mean it's a bit rough, but I think if we work on it, I think it could be quite nice to think, like instead of thinking of optimization as going to a fixed point, you think of this tracking problem where you want to keep, you don't want the gap between you and the target to increase over time somehow, and you want to control that. I think there could be quite nice things out of it, and with that I'm finished. Sorry.
Questions?
I really like that last part about the plasticity thing. So there's one thing you haven't mentioned, kind of, which is the activation function. Like you kept talking about the units. Like we had a series of works, including like actually this year on, if you parameterize the activation function, like if it's a polynomial or something, start as relevant, like that, you don't get this like that unit problem. You can use like a lot less parameters. It's more plastic because the activation function could just change, because ReLU is like really stupid, right? So I'm kind of wondering, like, is loss of plasticity in a sense the problem we just created ourselves by choosing like bad activation functions?
No, basically I think ReLU as an activation function is fine, as long as the distribution of the pre-activation is the one that ReLU expects. So that we kind of fix the activation problem by looking at the distribution of pre-activations and trying to control that, to have like a particular profile that ReLU expects. I mean, there's a different question of whether they're more efficient activation functions, like the polynomial one would be more efficient and maybe you can compress the model, but I think, that's like a slightly different problem. It depends a lot on the regime. If you don't care that much about the exact number of parameters, I think it's really hard to show that a different activation function will be better than ReLU.
It's like, I mean, you said that like this whole like that units, it might be a feature, right? You want to get rid of units, but like once a unit is dead, it will be impossible to recover it continuously ever again. It's just
that's
a very
not
strong thing, right?
That's not exactly true. So it's that because of the input distribution. I mean, it depends on like, okay, if all the drift is in the output, then yeah, definitely you're never going to recover it. If the drift is in the input, by chance that would recover as well. If you have layer norm that's applied the pre-activation, there is a nice side effect that because you have the normalization, you're going to have gradient flow into the weights, even of dead units. So the dead units, there's going to be some noise or some movement of them, even if the unit is dead. So I don't think it's that problematic. I'm not saying that activation functions are not cool and we shouldn't play with them. I'm just saying, if you're thinking just about signal propagation, there could be a way of dealing with it without affecting the activation function. We just.
Great talk, thank you. I'm just curious to go back to the compositionality.
Yeah.
As trained as a physicist, everything in data at least is compositional. I'm curious if you're going to give examples of things that are not compositional, and what are things that are architecturalized, that you think are not compositional to start with.
Okay, that's a great question. So I think maybe the only way I can answer this is that, well, everything is compositional at some kind of level. It depends whether you match, I guess, the kind of compositional that the architecture does with the kind of compositional of the data. And I guess that doesn't typically happen most of the time, and that's why we don't see this kind of compositional things. But yeah, it's hard for me to say what would be something that's really non-compositional. I mean, you can always do like, okay, I have this kind of like random stream of numbers, and I put like some random labels to it, and then potentially there's no composition on it. And MLPs do great on this kind of stuff. If you can try to train an MLP to be like a random number generator, and it can almost do that as well, right? So it can really match random patterns through random patterns. So you can create synthetic data. If I'm thinking about real data, I guess, yeah, I don't know if it's a bias because of us. You could also think, I mean, that's kind of Thomas Griffith's argument, is because, we're built to see everything compositional because that's the only way we can understand the world. So maybe, that's why we're like looking and just seeing compositions everywhere, even though there might not be. So maybe an argument, like I guess from the paper that Thomas did is, I guess slightly his argument was that Go might not be compositional. Like the fact that and I don't know much about Go, I know as much as I know chess, and I don't know much about that either. But as far as I know in Go, people do have this kind of sub goals that they're trying to do just because they can't view the entire problem to the end. They're and they think that this is how you should play Go. I mean, I know in chess they do that. You do whatever, you protect the queen, you do whatever. You have all of this kind of compositions of pieces of stuff that you need to do as the game evolves. And that's how people play Go as well. But it's not clear that you have to do that. Like there could be, I mean, the surprising move that AlphaGo was doing, I guess Thomas' argument was that, the reason we couldn't understand that move, why would anyone do that move and why this was useful, is because AlphaGo wasn't trying to solve any sub-problem. It was just thinking about the end goal. And there's a way of solving the game that doesn't involve solving any sub-problems. I don't know if it's really true or not. Go is too complex to be able to say, but this is his kind of argument, that some of these things, like chess and Go, we think of them as compositional because that's the only way we can approach them, otherwise we can't solve them, but like an agent does not have to do that.
Okay, it's coffee break time, and we're going to have a bunch of talks on this series, so more discussion as we go through the day. Okay, let's get going again. Next we have Rupam. He works in all kinds of different things, but importantly for this workshop, I think he thinks a lot about continual learning and building incremental learning systems, and specifically on robotics. So, this comment about computational constraints is a big deal for him. So he's a professor at the University of Alberta, Canada's CFAR AI chair. Take it away, Rupam.
Okay, thank you so much, Adam. And thank you everyone for joining me to listen to me, to my talk. I'm really excited about. So you can think of it as a continual learning talk, but it's really about my research program, the works that I do, but continual learning happens to be essential. Okay, so and yesterday we were talking about being clear about the goal. So yeah, let me try to do that. So let's start with the goal. So the goal here, my goal, is pretty much probably the same as yours as well. So to understand computational and general principles of intelligence. Right, so we want to understand intelligence. in a computational way. There are different ways of understanding it, right? There are neuroscientific ways. We want to understand it computationally, and we want to understand it generally, right? The principles that we want to know about, they should be generally applicable to many different organisms, many different embodiments. So that's the goal, and really, this is probably where I diverge with many of you, which is, I'd like to know like what governs the behavior of animals, including us, right? So MT is with me, but many of you may not care about it. But this is what I really care about. I really want to understand what governs, what computational principles govern the behavior of animals, including us. And now, many of us are still with me, I guess, but I need a point where I can actually really diverge. So here I'm going to really diverge. So I want a test for me. When do I know that I understood it enough, right? So you pick your area or application area, right? So NLP, computer vision, where you want to really prove to yourself that you understood it enough. So this is my area. I want to understand it enough to build animal-like intelligence for mobile robots, right? So that is closer to natural intelligence, right? So natural animals like us, we can be thought of as mobile robots, right? We move around, and all of our computations that happen on board in our brain. So that's my goal. So this whole talk is driven by this goal. So keep that in mind. So that creates all the constraints and the objectives. Okay. So that leads me to work on this discipline that I would like to call continual robot learning. Right? So it's a combination of multiple things. So one main part is robot learning. Now I'm not giving definitions that are necessarily like agreed upon in the community. These are definitions that are from first principles, and I agree with, so hopefully they will make sense to you. And by the way, this talk is going to be super high level, so this is what I can promise, that you should be able to understand almost all of it. All right, so what is robot learning? What do I mean by robot learning? I'm talking about learning the control for real robots in real time. So as opposed to learning offline, right? So learning should happen in real time. So what does real-time learning means? Real-time learning means that learning happens as you interact. Okay, so and we are talking about real robots, not simulations. So that's robot learning. And of course, continual learning is part of it in this discipline. So I just don't want these robots to learn the control in real time. I want to learn the control indefinitely, meaning that we would expect that this robot will be given newer and newer tasks, possibly in a sequence. That's one interpretation of continual learning, and that's what I'm gonna stick with. Okay, so that you can take as a definition of continual learning that I'm using, learn indefinitely, right? So there will always be newer tasks that you cannot do well without learning more, without extracting more information from that task. All right, so here is a third part, which I think is crucial, but is often overlooked, which is resource constraint, right? So I not only want to learn in real time for real robots and continually, I also want to learn using only onboard computers for mobile robots. So imagine a small robot moving around, whatever computer you can put on it, everything should happen there, right? So the control behavior should happen there, inference should happen there, learning should happen there. So, and this mobile robot is not going to carry around workstations, right? It will be a small computer. So that's what I mean by this discipline of continual robot learning. So we are trying to solve this problem divided into these three parts. All right, so although, by the way, I would also see continual robot learning as part of continual reinforcement learning. I just don't mention it because the robot control, it necessarily includes, to me, using RL. But to make that point more clear, So to develop robot control in a general sense, to understand general principles, I would say RL is a natural choice. Why is that? Because RL naturally gives a general formulation of the behavior problem, right? So here we are trying to formulate how animals should behave or how embodied systems should behave. The nice thing about RL is that it abstracts away all the embodiment related details and talks about concepts mathematically and computationally. So in RL, we are going to have this agent. Instead of talking about a robot, we talk about an agent, which is a computational system. So it contains the computational processes. Ideally, you'd like it to be a map. You can think that way, but essentially, they're not really a map. They're processes, but you can think of them as maps. So they take this object state of the environment, and based on the state, it will determine what action to take, and that action will be passed on to the environment. And that's the way an agent impacts the world, right? It can change the world by taking actions. So the goal here in RL is then to put computational processes in this agent box. So you need to come up with algorithms and the map, right? So as to achieving this goal of maximizing the aggregate reward. So each time step, this agent is receiving a reward signal. So this is what we call interaction diagram. Each time step, the agent gets a state, it takes an action. In response, the environment changes the state. So this goes on, and each time step is also getting a reward. The agent wants to maximize its future aggregate reward by changing its behavior. So by taking appropriate actions, it wants to maximize the reward. So that's the goal. Now, as you can see, this is quite a general formulation, right? I didn't talk about any robot. I didn't talk about any implementation detail. So through this general formulation, RL can provide general principles. So much so that now we have deep RL algorithms. It's quite dark here, but here there is a robotic arm that's reaching a red dot, right? So quite successfully, it is learned using a deep RL algorithm in simulation. But same algorithm can be used for other simulated robots to solve different tasks. So that's the generality, right? So the same algorithm can be used for different robots to solve different tasks. So when you can do that, you can say that, okay, so we are getting at some kind of general principle. All right, so this is what deep RL can do. And as I said, that I'm interested in doing something similar with mobile robots. Can we do that? Okay.
So in the previous slide, you talked about a sequence of tasks. So how are you thinking about that in this framework?
Right, so this is here, we are only looking at a single task, but you can think of now the same robot, like the rightmost one here is learning to walk. Next, it might have some obstacles, and so on. It has to go around or jump. So the task will change in some way, and you will have the opportunity to transfer skills. So that would be the scenario. Here, we don't have the continual learning problem. We are only looking at a single RL task. So that's typically what we do in deep RL, right? So we don't necessarily tackle a continual learning problem, but in a continual learning problem, we'll have a sequence of such tasks. Okay, so now here is the issue. Issue is that deep RL predominantly is used for offline learning. So remember, I want to do learning in real time while we interact, whereas deep RL is not used that way. So it is used in an offline way. So offline learning is kind of like this. You have this world where you want to deploy a model, a neural network. For reinforcement learning, it will be a policy network. So it will get inputs, the robot inputs, like the joint positions and such. It could be the camera feed, and the output will be the actions, right? So that's what you want to deploy. But the learning does not happen when it's deployed. In offline learning, learning happens based on stored data or a pre-created simulation. So you use it, you train it for a long time, while the robot is not at all interacting with the world. It's detached from the world. Learning happens, and then you deploy the policy. And when you deploy the policy, then there is no further learning, right? So that's the essence of offline learning. And that's how deep RL is being used currently. And not just deep RL, I'd say almost all AI we currently know are offline learn. You can call it train once AI. Just train it once, not anymore. It's exact opposite of continual learning.
I was very saddened by the existence of this many years ago.
Yes.
I don't know why.
Still there. Okay, yeah, so we just have that. As opposed to that, we want to do, as I said, real-time learning. What is real-time learning? So in real-time learning, this policy is deployed, it's interacting with the world, but training is happening at the same time. So there is no separate phase of training and then actual application. When it is actually doing the job, critical job, it's also learning from its experience. So that's real-time learning. That's what we want to do. All right, so now the question is, how can we do that? So here is an example of real-time learning with limited resource. Cats learning to walk on a treadmill. So cats definitely did not evolve with these kind of treadmills, right? They learned about it in real time, in their lifetime. And yeah, looking at other cats. But the main thing is that they're learning in real time and they're learning using their onboard computation. There is no cluster computer used here. That was not available for cats.
Not that we know of.
Not that we know of. There's no divine intervention happening. It was just all, earthly using soul onboard computation. So it is adapting low-level control, right? The muscle activation that's happening at tens of milliseconds, that fast. It's based on low-level input, based on vision and touch, very low-level input, and using only onboard computation, nervous system. Question is, can we do the same with our existing deep RL algorithms? So that's the first question we are trying to answer here, okay? So stay with me, keep that in mind, deep RL algorithms. The question is, can we use it like this for our robots? Okay, to understand it, of course, you have to kind of understand deep RL algorithms a little bit. So I'm gonna help you with that. So this is pseudocode for a deep RL algorithm. This is probably, was much easier to understand, right? So this interaction diagram. So this interaction is happening each time step, right? So we call it a time step. So that would be kind of a loop. So that loop is this one. So this one iteration within the loop is this one iteration of this interaction. So it means, yes.
So I hang out with a lot of RL theory folks. So I don't do RL, but I hang out with RL theory folks. It seems a separation needs to be made when you have a simulator for the environment and when you are collecting data online live in the system.
Exactly.
The second one is dangerous. Right?
Exactly.
So I don't know if you'll be differentiating because a lot can be done if you have the first one, but generating a simulator for real world scenarios is hard.
Exactly. Okay. So when we have a simulator, we can learn like this, right? So now the assumption here is that in continual learning, you're going to have an indefinite sequence of tasks. You will never have good enough simulator indefinitely. So we are giving up on that. So we are not learning from simulation. We are only learning online in real time. We are doing, as you mentioned, something dangerous like cat learning to walk on a treadmill. So that's the goal here, no simulation, right? So by the way, we can start with a pre-trained model, but that's not the point here, right? So you start with something, but that's not what we are focusing on. We are focusing on learning in real time. Yes?
Some people will say cats are fine-tuning.
We are only doing a little bit of fine-tuning forever, continually, right? So we are trying to learn in a continued way forever. Okay, so now let's try to understand this pseudocode. It's much easier to understand if you look at these symbols first, right? You take an action.
I
Yes.
have a question as well, if I can. So I was wondering, because you gave the cat example, but you don't know how much compute the cat has. Like, I wonder, basically, you're going to end up with an argument that say, like, oh, we're limited on the device because it's just this chip and can do this many flops, but we don't know if, like, what you're trying to do is doable, and or like, I just don't know, like, how do you think of this? Because, like, I think looking at a cat is fine, but a cat might be doing lots of flops, and we...
It might be. The question I'm trying to answer is, using today's embedded device, can we use our current deep parallel algorithms?
Okay, and you're happy with, like, it's impossible, we just need to have better embedded devices that can do more flops?
Or better algorithms?
Yeah, but it's hard to know which one.
But also the other difference between the cats and the robots is like cats come with a lot of background knowledge.
Exactly.
So that is currently missing any of these pattern generation systems.
True.
Except for
True. So, and yet it has to adapt. So we are focusing on the adaptation part, right? So can our AI agents adapt in real time, right? So we're not really doing the walking on the treadmill thing yet. Okay, so let's look at. I have to go through this quickly. So let's look at here we are taking action. This is just this statement, right? The action is being drawn from a policy network. This is a neural network. It's taking the state and then giving action as an output, and then this action is then passed on, is sent to the environment. So that's just this statement. And then here is another important part. The agent is getting state and reward. That's just the next line, right? The observation of reward and next state are t+1 and st+1. So those are the two parts. So what are the other ones? Why do we have more? So other ones are learning. So these two are just interaction. So rest of them are learning. This one is just the new observation that you saw. That transition sample is being stored in a storage called replay buffer. You initialize it to be empty. This is, by the way, part of all existing deep reinforcement learning algorithms that are practical. So you add it to the replay buffer, and you keep storing on, and then you sample a mini batch from the replay buffer. You make a gradient update, or maybe you use Atom. So that's a typical deep parallel algorithm. Now a question for you. So which statements here are kind of costly, as opposed to like quite instantaneous? Which statements will take like tens of milliseconds as opposed to like nanoseconds in your mind? Updates, right? Right. So this one is quite expensive. Anyone else?
Observing is hard.
So observing is, in a way, it just appears. It is incident on your sensor, regardless of you do anything or not.
If you do wrong things, it's very bad. Or if you don't do anything, it's very bad.
So I would say that this is not computationally expensive in the sense that they come at a fixed rate, like images, they come at a fixed rate. That's not computationally expensive in that way. Or some sensors that you're sampling. That's not as expensive as, say, a forward pass.
Okay, then the next is store.
Storing is also much cheaper than update, but it has computation. You just like push it, a single sample, you just push it to the replay buffer. But they have expense. So most expensive parts are these three ones, that the colored ones. This one is a forward. This is a forward pass, right? You're doing a forward pass through a neural network, and if your policy is based on pixels, it's a CNN policy. It's going to take some time. But more expensive would be the mini batch update. But even the sampling of mini batch, if your samples are images, sample that from a replay buffer from your RAM and put it to a GPU. That can be actually as expensive as the update. If you measure it, you'll see this is actually expensive. So these two are actually quite expensive, way more expensive than this one. So why I'm talking about these things, right? So in continual learning, we have been talking about mathematical framing of things. Here we are looking at things mechanistically. We open the gut of the algorithm and trying to understand which parts are expensive, because we are really worried about running these algorithms on small computers. We have to pay attention to this. There's no other way. So,
but in a way, storing sample is the hardest thing. You have very little memory you have to make a decision about. And or maybe at time wanting to abstract it on W, so you think the W is the hardest thing, but you could just store the whole thing, right?
So the question was like,
and then do the offline thing later.
The question was, in one iteration, which one of them are expensive? So expensive in the sense that like how much computation it is spending. If you just take the sample and store it to the replay buffer, that doesn't require a lot of computation at that moment. But you're right. So let's get back to the other expense, which is the memory expense. That's what you are getting at. So that's true. The replay buffer is another kind of expensive component, which is not about computational expense, but memory expense. It's going to grow larger and larger, and you are storing samples that are images, right? So millions of images you're storing, that is going to be expensive. So let's look at them more closely. So as MT mentioned, right, the storing is really expensive. So let's talk about storing, replay buffer. When they're image-based, a typical deep parallel algorithm will have a replay buffer that's of the size of tens of gigabytes. Right? So it will be tens of gigabytes just to have a replay buffer maintained. They're usually of like size 1 million samples. As opposed to that, the CNN policy will take about tens of megabytes. But the difference is 3 orders of magnitude. And that makes a huge difference. Why? Because now if you're shopping around, if you're trying to buy a small computer, it really matters, right? So, because if I have to fit in just a policy, I can just buy a small microcontroller. But if you have to fit in a replay buffer, then you have to buy a much larger computer. So that's a problem. That's one problem. Another problem is, even if your computer has, 16 gigabyte of RAM, I would argue that you'd rather want your policy to be much larger and fill up all the space to have much better capacity. But now you cannot do that because your replay buffer is taking up the space. Okay, so that's one problem, which is the memory requirements of different deep parallel components. They're really large. Now, let's talk about the computational requirement. So the computational requirement requires thinking about time, right? So now let's talk about an embedded computer, Jetson Nano. So if you do a policy inference, it's gonna take tens of milliseconds, which is actually okay, even though it's a small Jetson Nano. I'm not sure if you looked at a Jetson Nano. It's a small computer, right? So it can be placed on any small robot. And the policy inference is gonna take tens of milliseconds, but it's fine because your image frame rate is like around 40 milliseconds. So the kind of robot control we do, they have an action cycle time of 40 milliseconds. So you can easily fit that in. But the problem is the learning update. Learning update is gonna take tens of seconds. So again, like orders of magnitude, difference we have here. This is the consequence. So this is why this is so bad. It's bad because you're gonna make just one update per like thousands of samples. It's gonna affect your sample efficiency.
Sorry, can I ask a question for
Yeah.
the update? Why is it that expensive? Like, the backwards is roughly the cost of the forward, so you'd assume it's maybe twice more expensive, but in your case, it's orders of magnitude more expensive. Is the update done on, it's not like an online learning, it's done on a different batch. But even if it's done on a batch, it just needs to go forward and backwards, right? Oh, you don't have a GPU, so you don't parallelize on the examples.
So Jetson Nano has a GPU, not so powerful.
So here, like every example is done in parallel, in sequence, or how does it work?
So Jetson Nano's GPU, which it cannot fit even the mini batch, so it has to do some sequence, some small parallel.
Okay, but like if you do the batch size 1, you'd expect this to be twice as expensive as the inference.
True, yeah, exactly.
Okay, but you're not doing batch size 1 now.
No. Okay, mini batch, this is like 256 samples.
Okay, just because of that, that's expensive.
Yeah, right. So mini batch is of size 256. So now the implication of this is that you are gonna spend thousands of samples per update, and this is why it is bad. It's bad because the claim to fame for many deep parallel algorithms in terms of sample efficiency is that they make one update per sample per time step. Each time it sees a new sample, it makes one update. That's how it maintains like high sample efficiency. Whereas now, if I'm going to do use it on an embedded device, it's going to actually lose in terms of sample efficiency, right? Okay, so then what we looked at so far is that there are two main components, computational components of these algorithms. One is the performance component, you can say this way, which is essential for the robot or your learner or your classifier to perform in the world, right? So if for robots, it will be the policy. For your classifier, it's just the classifier network. That's all you need to classify. But there is this another component, which is the learning component, which contains the batch update, replay buffer, and so on. And the problem is that among these two components, learning components of deep RL algorithms are much more expensive than the performance components, right? So there is a huge disparity. So performance components can almost always fit today's embedded computers, learning components don't. All right, so then the bottom line is that, so we kind of already answering the question that we asked, that our deep RL, they are much more expensive, and then they cannot be contained on board, the learning components. But here is a more important statement I want you to remember. So this is very crucial. Deep RL methods. So I cannot have a big replay buffer. I cannot have mini batch update. What do you want to do? You want to learn without a replay buffer. You want to learn without a mini batch, right? You want to have, as you said, mini batch size of 1. We want to do that. What happens when you do that? So this is the statement, this is the claim I'm making. They are known to fail catastrophically. They don't work. Deep RL algorithms don't work without a replay buffer. Deep RL algorithms don't work without a mini batch update. They are stuck with it. So now we have an interesting problem. Deep RL algorithms cannot do without these components, expensive components. These expensive components cannot fit within our small onboard computers. All right, so that's the problem we are at. Any question?
There's another problem that we used to call it learning to control. And somehow that, like, their adaptation means different things, like in a plant or an airplane. Some turbulence happens, it needs to come back to the steady state performance. How does that fit in here is what I'm thinking now. Because I'm thinking if you don't want to use RL, there's some methods in traditional control that also address some of these things where it makes it more like stability and trucking.
So yeah, that's a good question. Some kind of like classical control methods, they don't learn continually. So, but the system is designed in such a way that it's kind of stable in that way, right? So it's pre-engineered, uses human ingenuity. It's a heavily engineered system where you only need to, the intelligence, the adaptation is only a small part.
Yeah, so like the cat walking, it's that kind of thing as well. Sorry, it's the cat's fault. Right? The cat walking is more like cat has to walk and not fall. And so they know that. You know?
Yeah, sure. But then we also have to learn how to bike. We didn't know. There are things we learn in our lifetime that
cats don't bike.
But like my cats learned a lot of new things. But the whole point is that we do learn new things at our lowest level that requires low-level control and adaptation and continual learning.
Yes, sorry to take time away from you. I'm just trying to understand the difference between like that kind of thing where it's adapting and being stable, and Razvan also talked about tracking. But then the thing about learning, how do you know which one's what in robotics? Like which one should really go on data, which one should be systematically designed in the system, inbuilt, right? And the low-level control.
So the point of there is no clear answer to these questions. My point of view is that there will be things that are inbuilt, but you don't want them to be rigid and fixed. You would want them to be flexible so that they can adapt to a great extent. The being too fixed is a problem. It will go against adaptation. So then the answer is learning. There will be learnable parameters. Within your pre-trained or like prefixed system, there will be learnable parameters that will continue to adapt. Okay, so we have our problem. Deep RL methods are too expensive. What do we do? So now, first let's look at what we do already in simulation, right? We are saying that we cannot maintain one expensive update per time step on embedded devices. In simulation, this is what we do. So this is one time step in simulation. We will do policy inference, and then sequentially we'll do a learning update. And as we can, at will, advance or pause the simulator, we keep the simulator paused when we are doing policy inference and learning update. Now think about it. In simulation, it really doesn't matter how expensive your learning update is. You can always keep the simulator paused, which is really unrealistic. This is not how the world works. On your robot, if it is taking up a long time to make an update, the robot will move on. It will hit a wall. But simulators never actually face this problem. So that's how these deep parallel algorithms can always have at least one update per time step, right? So this is how they can maintain it. So that's the problem. Now we understand the problem. So my talk actually starts just now because I'm gonna talk about 5. I'm gonna go through them quickly. I'll skip a lot of slides. I'm gonna go through a series of my works that try to address this problem. Some are through robot learning research, some are through continual learning research. So the first work, so this one is at ICRA. ICRA is a robotics conference published in ICRA. Here, we just say the obvious thing, which is that if you do deep parallel sequentially, like all the current implementations do, then your achieved action cycle will be much larger than the target action cycle. So you'll miss the deadline for observation and action. So it will not be reactive. It will be slow to react. It's an obvious thing, right? You already understood that. So then what is the solution? Obvious solution. Let's do the policy inference and the learning update asynchronously, parallel to each other. So that at least helps you with the action cycle, because now while learning update is taking time, you can have more policy inference in parallel, so you can maintain your target action cycle, the 40 millisecond action cycle. But the problem is your updates cycle is going to be longer, right? So, but we saw that there are 2 parts to your update cycle. One is the mini-batch sampling, which is quite expensive. One is the batch update. If both are equally expensive, you can have them in parallel and cut it like into half the cycle time. And that would, in many cases, we show that would allow you to have your update cycle match your action cycle. So you can end up having 1 update per time step, but not on mobile robots, by the way. This still requires a stationary robot and powerful workstation. But with this proposed approach, you can have 1 update per time step, maintaining sample efficiency. But once you understand the problem, the solution is obvious. The more important part is, to validate using experiments. So we did that. As I said, that we used a stationary robot. So this is a stationary robot. This is a robotic arm, has 5 joints. I'm controlling 5 joints by sending velocity commands every 40 milliseconds. And the input is the camera feed. So this is the camera feed. It's looking at this monitor where you have this red dot. So the goal is to make this red dot larger on the camera feed. You have to make that larger. So larger the red dot, red circle, more reward you get. So that's basically it. All right, so learning from scratch at the beginning is random policy. It's not doing any good. Learning just started, right? So it doesn't look that good. But now we're looking at after 60K time steps. So now it looks a bit better, but it's still not great. I don't say that. And finally, after 180K steps, so about 3 hours, real-time learning. Started from scratch in 3 hours. It learned to, consistently go to the red circle again and again. So learned in real time. Okay, so this is based on our proposed architecture, but it's still not fully satisfying. Why? Because our goal was to use mobile robot. This is not mobile robot. Our goal was to use an onboard computer. This is a workstation behind this monitor. We have a big workstation. That's what we use here. Okay. So I'm going to skip this slide. This is more comparison. So now, second work, we try again. Okay, let's try to use mobile robot. Can we do that? What are we missing? And we already established that onboard computers, they are too small to contain large replay buffers or mini batch updates. So what do? There are 2 alternative paths. One is fix the way deep RL is broken. As I said, deep RL doesn't work without replay buffer or mini batch update. can we develop new algorithms that can learn without replay buffers and minute batch update? And we call them incremental methods in classical RL. Yes, please.
Is the problem, so the model size and the model capacity, and these, do they factor in this 100, long time that you need, 3 hours to learn?
They do, yeah. So as I showed before, like it's tens of milliseconds, so you can always fit in within the cycle time.
No, but my point is that that 3 hour, like, what's
can it be shortened?
Yeah, what's the minimum time? Like, is there a goal? Like, you say, is this big a computer, and sorry, is this big a model? I know that it should be able to learn from like 10 trials or like 50 trials or. So,
we don't have that kind of knowledge, but the same question we can ask in simulation, right? So the learning we had was comparable to what we have now in simulation.
I see. So like then it will be 3 hours because of the model architecture that you have chosen, right?
It won't be?
It will be? Is that what you're saying? So I don't.
It will be, yeah, exactly, right. So you don't.
I don't understand what we're doing, right? So.
What do you mean?
So we want to learn quickly, right? We want this to not take 3 hours.
So this is how deep RL methods work currently. Okay. They take a long time. They take a long time. We don't quite see it because all we see in papers is a learning curve. But if you actually do it in real time, that's going to take like 3 hours. They'll say, perfect, that's amazing. Because in some cases, it's going to take weeks. So this is how learning from scratch looks like. So this is, the start of something bigger. We are not seeing yet. But at nowadays, it's taking 3 hours. Like over time, we'll have better algorithms that will be faster. That's the hope. Okay, so one direction, as I said, one direction to address this problem is to solve the way deep RL is broken and introduce incremental deep RL algorithms, right? So that will solve this problem. So that's quite hard. It doesn't exist. As I said, in the whole deep RL community, it does not exist. There is no incremental deep RL algorithm that works on the usual benchmarks. Okay, even if you like run it longer, much longer, yes.
Sorry. Question. Are you making the assumption that the problem is the RL and not the deep network? It could be that just neural networks don't learn fast and there's no solution. Like, whatever, Q-learning is fine. You don't need to change Q-learning. You need to use a different function approximator. That's the issue.
I think RL can fix it with neural networks, such as like model-based methods. Okay, so yeah.
So I'd just like to hear your opinion on policy. This is a policy because I saw you use SAG, but could make the argument things like PPO, trust region, etc. would be more stable.
Great question. Let's take it offline. I have 20 minutes, but thank you for the question. Let's talk about it later. Okay, so it's just the second work. I have 5 works. So it will be fine. Okay, so this is hard. We don't have it, so we are not going to do it in this work. We are going to do something else, which is that we will have still a workstation, but not in a tethered way. It will be connected wirelessly, okay? So this is the proposed architecture then. You cannot quite see it. This is a mobile robot, round. If you know about Roomba, this is the Roomba robot, known as Create2, the research version. There will be an onboard computer, right? So Jetson Nano will be on board, and Jetson Nano will do some computation, but most of the computation will happen nearby on a remote workstation, and these two will communicate wirelessly. So this is all we can do right now. So that's the proposition, and I'm going to skip this here. I'm just comparing different ways of distributing my computation between these two computers, and it turns out that the best thing to do is to have the policy inference on board and the learning updates on your remote computer. If you do that using that system, this is how it looks like. So another video. So now we have Roomba. Okay, no, it is coming. All right, so here you have now a mobile robot, Roomba. It has on board this Jetson Nano and a mounted camera. So goal is similar again, like you have to reach one of these sticky notes, right? By enlarging it, the number of green pixels on your camera feed. And again, actions are being taken for every 45 milliseconds, low level. And I'm learning a CNN policy from scratch, from pixels, everything from scratch. At the beginning, like before, it's a random policy, not looking good. But over time, after 100K samples, this is after 100K samples, so like a few hours, 2 hours. Now it consistently learns to reach the target, right? So it's all learned in real time. All right, so this is another work at ICRA 2023. So what's the lesson here? Lesson here is that we can do deep RL on mobile robots, but we need a powerful workstation nearby, right? So here learning happened on a powerful workstation that's connected wirelessly. Okay, so that's not satisfying. That's not what our goal was. Our goal was to learn everything on board. So what are we gonna do now then, right? So we have to really fix the problem of, learning without replay buffer. We want to learn without replay buffer. We have to fix it. How do we fix it? So we look for the answer in continual learning.
So the problem is that the replay buffer is big.
Also, mini batch updates are also expensive. 256 mini batch as opposed to I would like to do it with one sample. So the goal is try to understand what the goal is. If the replay buffer is diminished to a single sample, I want to learn from the immediate sample, make an update based on that sample, throw it out, never store it. So truly incremental learning. That's what I want to do. And it doesn't work currently. I want to fix it. So why it doesn't work? I am looking for the answer in continual learning. Well, I think you already guessed it. Problem is catastrophic forgetting. So problem of catastrophic forgetting, as we know, is a phenomenon that learner performs poorly on past tasks when you are learning from new tasks. Now, what is the solution we know in continual learning, right? The earliest and long-standing solution, replay, right? So we store samples from the past and then we repeatedly replay them. That's what we do. And that's exactly what we are doing in deep RL. Deep RL, so presumably, is facing this catastrophic forgetting. Although we are looking at a single task, not even continual learning. So why, even on single task, we are facing catastrophic forgetting? Because there are things common between continual learning and single task RL. Both are using gradient descent, which is, I'm going to talk about it, it's a problem. And second is both face a lot of non-stationarity, right? So in RL, you have this non-IID sequence. That's the problem. Your policy is changing over time, which is changing your data distribution, which is creating non-stationarity. So due to non-stationarity, you face catastrophic forgetting. And that's why I'm claiming that all deep RL algorithms, they end up having a replay buffer. They are solving the catastrophic forgetting problem. Okay, so based on this insight, now let's talk about the third work. So in the third work, we said that, okay, replay buffer is helping with catastrophic forgetting. If I have a small replay buffer, I need something else to address catastrophic forgetting. What do I do? So here we are talking about a specific algorithm, DQN, the first popular deep RL algorithm. So in DQN, so this is the DQN, the first term here is the DQN loss, right? So the main idea is that I'm trying to train this action value function based on this target, which is the accumulation of reward, but it is estimated based on the approximator itself. So, and that's the problem, right? My target is based on my prediction, unlike supervised learning. So the way this issue is resolved is by having a target network, which is a delayed network. It's an older version of my current network. So I have this target network. So our idea is, why don't I use it to regularize the current network? So I said that, okay, this is already delayed, so it contains some past information. Why don't I make my current network kind of like move toward the target network so that it kind of retains the past knowledge. And it kind of connects with a lot of other things that you have already presented, right? So, but it's a simple thing we tried. This is published at TMLR, and I'll quickly just describe this learning curve here. This is a typical RL learning curve. So in x-axis, you have time steps, right? So those 40 milliseconds, but in simulation. So they are going on. And in y-axis, you have the aggregate reward called return. Higher is better. And when you use DQN with 10,000 samples in the replay buffer, it learns quickly, it stays high. But if you use a small replay buffer with DQN, size of 32, it fails catastrophically. It doesn't look good. So that's what I mean, that when you use small replay buffer, these algorithms, they fail. But if we use our algorithm with 32 samples, it looks like it is doing almost as good as the standard DQN with replay buffer. Okay, so that's good. So now we see that we have other means to address catastrophic forgetting, and you guys also presented a lot of other methods. That's good. We were getting hopeful, except that we found a different problem, which Razvan talked about, loss of plasticity, right? So that happens in research. You try to fix one problem, you find another problem. So here we found this problem of loss of plasticity we demonstrated in continual learning. So this is what we were worried about. While we thought, okay, catastrophic forgetting is important, but another important part is that I want my robot system to learn indefinitely. Can it learn though, indefinitely, right? So after like 10,000 years, is it still learning? What's going on? So that's the question we ask. So it turns out that they actually continue to lose their ability to learn. They who, like SGD, Adam, the usual, optimizers, when they are trained on a long sequence of tasks, and we call this phenomenon loss of plasticity. They're losing their ability to learn. Okay, so this is a demonstration of that. So this is the Dohare et al. Paper that Razvan had in his slide. So here I'm looking at different tasks being presented. It's a continual line problem, different tasks being presented, and each task is an MNIST problem, but the input is permuted, meaning that the pixel orders are scrambled. So meaning that you don't have like really at all anything to transfer from one to another, maybe the biases. So, and they are all of similar strength in terms of the difficulty of classification. So desirable is that you learn each of them equally well, except that SGD Adam, their performance continues to go down. So imagine you're running a robot indefinitely. You'll see that over time it's performing worse and worse over time. And if you look closely, this is what happens. Initially, in these two tasks, backpropagation is doing what is desirable of it, but later it's learning slowly. It's not rising up as fast as possible. It has to do with loss of capacity and probably saturation and other things. So that's the phenomenon we studied, we demonstrated, we rigorously studied, and then in the community it also became popular. Now, what do you do, right? In this situation, why this is happening? What do you do? Now, Razvan mentioned some of the reasons it might be happening. One is that initialization is important, right? So we take that seriously. We say that, okay, when we randomly initialize the weight, initially the features, the random initialization makes the features diverse and plastic. So that's a good thing. Why don't we make sure that some of the features are always diverse and plastic, meaning that they are always drawn from the initial distribution. They always maintain, being drawn from the initial distribution. So that's what we want to do. We want to make sure that some of the features in my networks are always drawn from the initial distribution. But there is a problem, and I'll take probably questions a bit later. So there is a problem here, of course. If you try to reinitialize some of the features, it will create catastrophic forgetting. You're going to destroy useful features, right? So that's why we propose to reinitialize the unuseful features, the things that are not contributing. Let's repurpose them. So that's what we propose, and the resulting algorithm is called continual backprop, right? So here, the way we identify whether a feature is useful or not is also connects to pruning, because in pruning we do look at importance or utility of a feature. So this is the utility of ith feature. The way we estimate it is by looking at the magnitude of the activation, which is how much this feature is used, times the magnitude of the outgoing weights, which is how much outgoing learned weights, meaning how much this feature is useful. If it is useful, the weights will be large. So if a feature is neither useful nor used, we just reinitialize them, draw it from initial distribution again. So we always have some features that are plastic. So if we do that, then on a bunch of tasks, we show that while backprop is not looking good at all, losing plasticity over time, continual backprop either continues to improve performance or maintains its performance. So that's one of the early solutions of the problem of loss of plasticity. Now there are many other solutions in the community, and they're studying this issue. So this was, I hope, the fourth work. So if there is a pressing question, yes, you can ask. So, otherwise I would have time for the last work. And what is the last work, right? What is remaining? Well, I have this original problem still. I need to learn without replay buffer, without mini batches. But now I have another problem, loss of plasticity. So I have to address all of them. Okay, so but at least from continual learning perspective, you would like to address both catastrophic forgetting and loss of plasticity. Imagine if you have a continual learning agent or robot or learner, whatever you have, if you run it continually, indefinitely, it's not gonna encounter only catastrophic forgetting or only loss of plasticity. You'd actually face both of them simultaneously. So you need a method that can address both. So this is our fifth work. This is ICLR this year we presented, where we try to address now both of them at the same time. Prior to this, there was no method we knew in the community that tried to even address both, let alone like having one. Okay, so how do we do that? We went back to the blackboard. Okay, so we looked at the backpropagation algorithm. What happens with backpropagation? So the top line is simple forward pass. You know all that. This is the input times weight. Sum them up. You get pre-activation. Pass it through activation function. You get the input for the next layer. That's easy. Now let's look at backpropagation. Chain rule. The gradient of the loss with respect to the weight is the gradient with respect to pre-activation times input. And the gradient with respect to pre-activation can be written recursively. We all know that based on the gradients from the like upper layer. That's why it's called backpropagation. So this part is good, recursive. Now there are two other factors here. One is the gradient of the derivative of the activation, and the other is the magnitude of the outgoing weights. Now here is the problem. Here is the problem, which is my gradient is proportional to my outgoing weights, magnitude of my outgoing weights. Now imagine this feature was useful on a past task. Now all of a sudden task changed. I'm gonna change the most useful feature the fastest, because this feature was useful, meaning that its outgoing weights were large, so the gradient will be larger for this. So that's the problem. And it's undesirable, absolutely, but for backpropagation, it totally makes sense, because backpropagation only cares about reducing the loss of the current task. It has no commitment to preserve past weights or features. In fact, this is something Razvan actually pointed out in one of his papers. In 1986, the year backprop came out, he saw this problem and he noted that this does not look good. If you have this kind of continual learning problem, you are going to actually forget things. Okay, so we picked it up, and this is what we proposed then. So this allows us to attribute the problem of catastrophic forgetting to the smallest unit, which is the weights. We said that, okay, catastrophic forgetting can be attributed to the overwriting of the weights, right? So the weights are being overwritten and being relearned. So that's what's happening, is what we proposed. And then we're also saying that loss of plasticity can also be understood at the weight level, that they're becoming rigid to learning update. When you make update, they're not moving, they're not changing. So based on that, we developed a new method called utility-based perturb gradient descent, UpGD. So this method, it protects the more useful weights and perturbs the less useful weights. So that's what we do. And this is the update, very simple update, you can remember. So just this is gradient descent. But now we add perturbation to make sure that you have plasticity. But then we have this factor, 1 minus ui as a factor. So what is 1 minus ui? Ui is the utility, and it is scaled between 0 and 1, meaning that if a weight, particular weight is really useful, 1 minus u is going to be 0. I'm not going to change it. It will be protected from change. But if a weight is really not useful, then this ui will be close to 0. So I'm going to change it using this update, which is I'm going to change it using gradient descent. But if I lost plasticity, I'll at least perturb it. So I'll still move it around. So this is our method is trying to address both problems, right? It's trying to protect from catastrophic forgetting. It's also trying to keep plasticity on. Now, how do we calculate utility? So this is how we define utility. As opposed to continual backprop, we said, okay, utility is about how useful a feature is. So if a feature, if a weight is really useful, and you take out the connection, it's going to increase your loss. So then utility can be defined as the excess loss for not having that connection. Except that, yes.
For the current task or the previous task?
So this is sample based. So you have to kind of like do a moving average over the past. This is a sample based. How useful this is on this sample. So now, of course, computing this is expensive. Instead, we do a Taylor approximation, which only requires computing the gradient, the diagonal of the Hessian, and the weight, right? So, and for the diagonal of the Hessian, if you're coming to ISML this year, next month, we have a nice way of approximating the diagonal of Hessian, which is order n, as expensive as backprop, no more than that, okay? So, using all that, we now have UpGD. Now remember the input permuted MNIST, Adam is going down, SGD is going down, EWC is going down because EWC doesn't care about plasticity. So it is actually losing plasticity. UpGD is staying up. Whereas on this task, I have level permuted C for 10, meaning that I'm not permuting the, scrambling the pixel orders, I'm scrambling the level orders. So the features are still relevant. So I have a high possibility of positive transfer. Except that Adam and SGD, they are not doing good in terms of positive transfer. EWC is doing fine, so is UpGD. So UpGD is the only method right now we know that can address both loss of plasticity and catastrophic forgetting. Is positively transferring and also addressing loss of plasticity. And then we got excited. And by the way, here, this is used without any replay buffer or mini batch update. All learning happened based on a single sample, just single sample. Now we got excited, obviously, then we used it on reinforcement learning. And reinforcement learning, when your replay buffer size is small, we know that like the performance is catastrophic, and we presume that this is due to both catastrophic forgetting and loss of plasticity. So initially you learn a good policy, but you, due to variations, you forget. Your replay buffer is small, right? So it can forget over time, and due to loss of plasticity, it cannot learn it back. Whereas UpGD, as it can address both, it doesn't lose plasticity, it doesn't forget catastrophically either. So on these hard problems on Mujoko, where PPO is not doing well, we are either improving over time or maintaining our performance. So in conclusion, I think we agree that deep learning is promising but too expensive for continual robot learning, and we need instead scalable incremental methods without forgetting, without replay buffer, without mini batches. And our recent advancements suggest that such methods are well possible, and that will also give us scalable methods. Scalability is not just about scaling up; it's also about scaling down. So scaling down means you can have learning on your small computers. So if once we have scalable methods, this is what I really believe, that it goes beyond robotics. It's gonna make AI accessible and cheap to all. Thank you. Maybe allow 2 questions.
I really like the presentation, like the sequence of works. In that last batch, like maybe my question is missing because I'm not sure I understood. Like, I guess in both of the last 2 works, you're introducing some kind of perturbation.
Yeah.
Like, and I guess if you measure like offline kind of things and like you only care about the performance at the end, that's cool. But like, if you're in an online scenario, don't those perturbations like actually screw up your momentary prediction? Maybe I'm missing something. Like, every time you perturb, you're gonna mess up, right? Like, and those, like, especially in the permuted endless graph, like it was like dipping, going up, dipping, going up. So there's only like one exact point in that graph.
There is a
like in the continual backprop thing, right?
There is a cost to it. There is a small cost you pay for perturbation. We have to. I'm going to accepting it, and we do in RL. We do exploration, and there is a cost to it.
So like how much does it like cost? Like how much do you?
I suspect like this much. You see, like SGD is going above UpGD, but UpGD when it goes up, it doesn't go as high as it could be like that. Yeah.
So why did you? Oh, that was a different graph. Okay. I mean, in like the continual backprop one, the one.
Yeah.
It had really big dips, right?
Big dips.
Like that one on the right. Like it's still. I mean, it's like if you only look at like 4 points on the x-axis, it's great, right? Like, but everything in between, it's like huge dips. Like,
which one is huge dip?
Right hand side.
Right hand side.
Oh yeah, because the task completely changed. It's a complete new task.
What you said is just permuting, right?
Permuting the inputs, so there's nothing getting transferred. The pixels are scrambled. The meaning of each pixel is now different. One last question. Okay. Yeah? You have a question?
This is very interesting. I'm curious, in this world of large models, if we can imagine one day we can get them small enough, would you imagine these like multitask, all these problems will be completely solved, or you think that they'll never get small enough to be on these mobile robots?
Oh, okay. Yeah, that's a very interesting question. Now, there are two parts to these large models. One is the model itself, and another is the learning part of it. Now, the learning part of these large models are huge, not just large. Those are huge computation. So it will take much longer to wait for the Moore's law advance enough so that that kind of learning can happen on small computers. But large models can be fit within embedded computers like in, I'd say, a few decades. I'm just waiting for that to happen. I don't have to do anything. Okay, thank you.
It's my pleasure to introduce our next speaker, Sarath. He's at Mila. He's been working on continual learning, but also on language models and a bunch of other stuff, optimization and so forth. And together we've been co-organizing the COLAS conference that I hope many of you will try to submit and attend. And he has a talk with a surprisingly similar title, so hopefully different content. So that's I'll let you.
Well, thank you for the introduction. Yeah, I'll start with the title first. I was too late to give my title, and when I was looking at the schedule, I saw that Razvan gave a title which is exactly what I wanted to use in my talk. So I actually ended up spending a lot of time trying to come up with an alternate title. But it's not very different. But the talk is kind of different and complementary to whatever Razvan spoke. In some sense, it's nice because you have all the backgrounds, and he has talked about a lot of other aspects of optimization and lifelong learning. So in some sense, you can consider this as a continuation of what we discussed in the morning. Okay, so I'm going to talk about optimization for lifelong learning. Maybe before I begin, I want to give a very quick overview of the kind of things that I do in my lab. So we work in deep learning, reinforcement learning, and also natural language processing. So there was a lot of hate for LLMs yesterday. So that's one of the major research areas in my lab. We also do things in the intersection of continual learning and LLMs, some of which I will present today. So the long-term research vision for our group is to develop interactive learning algorithms that continually learn from their experiences. Okay, so for me, there are two keywords here, interactive learning and continually learning from experiences. Which kind of motivates the kind of projects that we do. We work in reinforcement learning, which is one of the major interactive learning paradigms. We also work with language models and chat systems, which are another form of interactive learning paradigms, to name a few. Okay. Before I begin my talk, I also want to quickly talk about COLAS, which Razvan already mentioned. Out of curiosity, how many of you don't know COLAS? Okay, there are 3 or 4 people, so I think it's worth talking about it. So COLAS is Conference on Lifelong Learning Agents, which we started a couple of years back, with Razvan, Adam, and a bunch of other continual learning researchers. And the 3rd edition is going to be in Italy, 29th July to August 1st. And it's too late to submit papers, if you didn't know about the conference before, but I highly encourage you to attend the conference, if you really care about continual learning. It's not just continual learning, for me, COLAS is about learning, under non-stationary settings, right? So you're learning and, it's not the standard IID batch setting, which is what majority of machine learning is right now focusing on, right? Like, so when things change, what kind of learning paradigms would work? It could be continual learning, it could be meta learning, it could be transfer learning, online learning, active learning, right? Like, so if you work on any of these topics, I think this is a great venue, partly because one of the objectives of Colas is to bring together the continual learning researchers who are fragmented across, for example, the oral community, supervised learning community, computer vision community, neuroscience, etc. So for this year, like, we have like a really great set of speakers, including MT, who's still not here. Please check the website of Colas if you're interested in the topic. Okay, so with that, a little bit of advertisement. Like, so I will start with the topic, which is optimization for lifelong learning. Like, but maybe one more quick detour. Like, so, like, I'm not going to introduce lifelong learning here. We talked a lot about the definitions yesterday, right? Like, so, like, what is lifelong learning? So, like, I'm not going to give a formal definition for what is lifelong learning, like, but I want to tell what is lifelong learning for me, okay? So lifelong learning for me is actually the road not taken by the ML community, okay? So, like, why do I say that? Like, let's look at the standard machine learning paradigms that we have. Like, so in supervised learning, like, we are currently stuck with benchmarks, learning offline, and then testing kind of paradigms. So this is really a trend that started in 90s, like when people wanted to make progress and want to compare against each other. Like, so they started developing benchmarks, where the majority of focus went on to designing algorithms that can learn from the training set, and then you test for generalization in the test set, right? Like, so it helped us making like models better. Like, so like now machine learning models are everywhere. But had we not focused on benchmarks and focused on the learning problem itself, like, we would have made a lot of progress in continual learning, okay? So, and I can make similar arguments for reinforcement learning. Like, so reinforcement learning for me is stuck with value functions, right? Like, so, like, value functions are nice, but they somehow embed this idea that you have a single task and you care about getting returns from this task. Like, and the moment things start changing, like, it's not very clear if we can even extend what we have and improve things on that, right? Like, so maybe we need to completely rethink how we do reinforcement learning. Like, if you consider continual learning, right? Like, so and unsupervised learning, probably the least affected by this mindset, but still, unfortunately, a lot of unsupervised learning research happens by like training a model and then testing it on the downstream tasks. Like, so there's no clear way. There's no other clear way than bringing that one number. Like, for example, if you work in language models, you care about a single score in glue or super glue, right? Like, so you could come up with any pre-training algorithm, but in the end, people ask, okay, what is your glue score, right? Like, so we are still stuck with this set of challenges in all these fields. Like, and in some sense, like, I wonder if we did not get into this track, like, so we would have made a lot of progress in true, like, real-time online learning, right? Like, so that brings us to online learning, which is probably the closest to lifelong learning. Like, so I don't know how many of you talk to online learning researchers. Like, it's a small community of people mostly doing theory, right? Like, but they have the right set of foundations, and they're anchored on the notion of regret, like, which is what reinforcement learning was also supposed to care a lot about. Like, but we somehow got out of it, like, and focused too much on performance and final scores, etc. Right? Like, so this is lifelong learning for me. Like, so lifelong learning is the actual learning. Like, so this is how humans learn, right? Like, so, and especially for people who care about, like, understanding the principles behind intelligence, right? Like, so the current machine learning paradigms doesn't make sense. Like, so, like, if you want to discover how humans learn, like, so you should be looking at lifelong learning, not like the traditional supervised learning setups, right? Okay, so that's my definition for lifelong learning. Like, now I'll really talk about optimization for lifelong learning. Okay, so the title was kind of inspired partly based on this first work, which is probably the half of the talk, right? So So I'm going to talk about this work which was published at COLAS a couple of years back, like by my PhD student Pranshu. Like this is called task-based accumulator gradients for lifelong learning. Okay. Now here's the motivation for this work. Like so, like I think we saw a bunch of talks in this workshop, like where like people talk about coming up with new algorithms or new architectures for doing lifelong learning, right? So there are a lot of algorithms that exist. Like so, you can do replay, you can do EWC, like a bunch of other regularization methods, right? Like, or you can come up with better architectures, like which avoids interference through modularity, etc. Right? However, we always use SGD and Adam for optimization in the end. Like so, like in some sense, we are thinking in the algorithmic space and architectural space, right? Like so what I really like hope to convince you today is like there is also value in thinking about this from the optimization space. Okay, like so why are we doing SGD in continual learning? Like why are we doing Adam in continual learning? Like this is something that we never question. Like so, like you come up with a new algorithm and then use Adam, right? So before I expand on this further, like a very quick, maybe we don't need the slide here. Like so, you all know these optimizers. Like still, like a very quick one-slide introduction to SGD and its variants. Like so, like first we have stochastic gradient descent, which is basically like almost memoryless. Like well, it's exactly memoryless. Like theta is equal to theta minus alpha times the gradient, right? Like so, then we have like a couple of variants, like momentum-based gradient descent, like so where you have the momentum vector MT, like which is basically the running average of your gradients, and then you use this to get acceleration, right? And we also have adaptive learning rate methods like RMS prop, like where you adapt the learning rate by some gradient statistics. In this case, it's root mean square of the gradients, right? So you can also combine momentum and adaptive learning rate, like that's where you get the famous Adam, like so, which is basically a version of RMS prop plus momentum, right? Okay, so what I want to like highlight in this talk is like all these optimizers, like which we commonly use, are designed for single task, IID, fixed data setting in mind. Okay, so why do we care about acceleration? So the fact that we need accelerated optimizers kind of arise from the fact that like you have a single task and you want to minimize the loss for this task as quick as possible, right? Like so this is where momentum helps, and this is where like Adam kind of methods also help, right? Now, is it okay to take these optimizers and just blindly apply for continual learning, but not just continual, even reinforcement learning, like which is not an IID problem, right? Like so this is what I would like to question. Like so, there's also another motivation here, like which is if you work in continual learning, you know that SGD forgets less when compared to RMS prop and Adam, and I think this is also kind of partially true for plasticity issues. Like so, there are experiments which show that Adam has a lot of plasticity issues when compared to SGD. But it is not always the case. There are settings where Adam is better, but in general, like people prefer SGD over Adam in continual learning. Okay. Now, if you think about like exploiting the knowledge from optimization for machine learning perspective, this doesn't make sense. Like so, like we have 10 plus years of research in adaptive gradient methods, like which really helped the single task supervised learning community, right? Like so, in some sense, we are throwing away all these optimizers and go back to SGD, which is not a new optimizer. Like so, we know SGD for ages, and like we are ignoring all these adaptive gradient methods, right? Like so, now, can we do better? Like so, can we develop new adaptive gradient methods which are specifically suitable for the non-IID problem like that you're currently facing, which is lifelong learning. Okay, so that is the motivation for yeah.
So when you say SGD forgets less compared to others, I guess you're not changing the loss function anyway. You're just taking many batches, right?
Yes. Yes. Like why is that the case? Like so, like a quick intuition is like, so if you look at SGD and RMS prop, like as an example, right? Like so, like adaptive gradient methods in general are aggressive in optimizing like the current objective, right? Like so when you optimize the current objective aggressively, like so you don't think too much about the previous objectives, like which means there's more room for catastrophic forgetting.
Can I follow up on that? So but you do get lower performance on tasks that you're optimizing, right? So you're like basically trading off like how much am I learning this current thing so that I forget less?
Yes. So the goal, okay, so that's a good point. Like so the goal is to come up with an optimizer which doesn't like trade off the performance for the sake of like avoiding forgetting, right? Like so we want an optimizer that is adaptive still, like we still want an adaptive gradient method, but how it adapts should be informed by the problem that you care about. Okay, so which is not the case with Adam, because if you think about it that way, Adam adapts blindly. Like so, like it adapts based on the current objective. Like it doesn't consider the previous objective, like while changing the learning rate, right? So I'm going to set up the objectives for a new optimizer. Okay, like I'm looking for an optimizer. Okay, so that I want to behave it this way. Like so, first of all, if the tasks are not related, okay, so if my current task is not related to the previous methods, like so, then I want this optimizer to be careful, slow enough, so that it can prevent catastrophic forgetting. Okay. At the same time, if the tasks are correlated, so this is where I can get the benefit of adaptive gradients. Like so, I can actually accelerate my learning. Okay, so that like I learn faster than SGD. Okay, so I want an optimizer which can do these two things. Like so, like what we propose in this work is not an optimizer per se. Like it's a wrapper for any existing optimizer. Okay, so I'm going to take RMS prop as an example to explain this new wrapper, right? Like so, like so this is how the update equation is going to look like. Okay, so in this case, I have theta is equal to theta minus eta times the gradient, like, and then I'm dividing it by a term which is replacing the usual root mean square of the gradients. And what is this term exactly? So this term is going to be Vn, like which is the usual second order moments like that you use in RMS prop for the first task, but starting from the second task, like that you're seeing, right? Like so, this is going to be a weighted average of moments from previous tasks. Okay, yeah.
I guess from a Bayesian perspective, this V is W times V is closely related to the covariance matrix from like a natural gradient set kind of optimization perspective.
You can say that.
Okay, yeah. So I'm just wondering, like, and then you're adding previous V's, is kind of looking a bit more like, adding to the efficiency. I'm just wondering if this is...
You can view, I have not thought about it that way, but it sounds reasonable. So you can view it that way. Okay, so now the question is, what is this alpha? Like, so how do I weight these different V's, right? Like so this is how we are going to do it. Like, so we are going to maintain these empty vectors, like for each task, which is basically the running average of the gradients per task, okay? And we are going to look at how much these things align, okay? So in that sense, this is kind of similar to GEM kind of methods. It's just that the place where I'm doing these things is different. Like GEM does this in the objective space, like I'm doing this in the optimizer space, okay? So like if the gradient for the current task is aligned with the gradient of the previous task, okay? So then alpha is set up in such a way that the learning rate is going to be increased. If it is not related to the previous task, like if it's uncorrelated or even opposite, then the learning rate is going to be reduced significantly so that you don't forget. Okay, so this is the idea. Like so we are doing this for RMS prop. Like you can do this for Adam. You can do this for any adaptive gradient method. Okay, do you have a question?
Okay. My question here is, I guess you can only compute the gradient for one task when the task is alive, right?
Yes.
So when you go to the next task.
We keep empty vectors from the previous task.
Okay.
So that's a bit memory intensive. So we do keep memory like the empty vectors from the previous task. Okay. So I'm going to show you a bunch of results now. Like, so first we are going to compare like simple fine tuning. Like there is no lifelong learning solution here. Like I'm not doing EWC, I'm not doing experience replay, anything. Okay, so this is a simple fine tuning, one task after another. Okay, and we're just comparing the optimizers, like the naive SGD, naive Adagrad versus tag Adagrad, naive RMS prop versus tag RMS prop, etc. So as you can see here, in almost all the cases, like maybe let's take just one example, right? Like so in split CFAR 100. You can see that SGD is actually much better than Adam, which is often the case in a lot of these tasks, okay? However, tag Adam is significantly better than SGD. Like, so now we are actually getting the benefit of adaptive gradient methods and still like not forgetting like as Adam typically forget, okay? And in general, the trend here is like every tagged optimizer is just better than the non-tagged optimizers, like in terms of accuracy and in terms of forgetting. Okay, and here are some analysis to actually show how we get this benefit, right? Like, so how do I get this extra boost, like when I switch from Adam to tag Adam, right? Like, so you can see, for example, in this example, so whenever like the model sees tasks are related or not related, like so it actually changes the alpha, the rate of the alpha, right? And whenever these change happens, you see the gap between the naive optimizer and the tag optimizers increasing. Okay, so in some sense, like the optimizer is making use of this information that whether this task is related to the previous task or not. Like and these gaps that you see are the places where the optimizer is aggressive in optimizing the current objective, but it's more of an informed optimization process because this helps. It doesn't hurt the optimization. Okay, so you can also. Okay, the nice thing about this method is like this is an optimizer. It's going to be complementary to any other lifelong learning solution, so you can combine existing solutions with the tagged optimizers. Like so here you see the comparison of like naive RMS prop, tagged RMS prop against some of the state-of-the-art methods like EWC, ER, etc. Like in general, tag methods are like better. So here I'm not combining them, like so you can actually combine them. So here is another set of results, like so where basically you can take any lifelong learning algorithm of your choice. Like for example, you take EWC. Okay, let's take this example. So you take EWC, and this is EWC with SGD. So you switch to RMS prop, you get this, which means that there's a reduction in performance. However, when you switch to tag RMS prop, you're not just getting all the benefits of SGD, but you're also doing better than that. Okay, so in general, like if you do task incremental learning, I strongly encourage you to just switch your optimizer, like to tag RMS prop or tag Adam. You can still do your method of choice, like for lifelong learning algorithm, like so you're just going to get a few extra points, like by just switching the optimizer. Okay, so. So this was done primarily for task incremental learning. Like so, if you are the reviewer number 2, you would complain that task incremental learning is a bad setting. Like so, like we want task-free like settings and like class incremental settings and etc. Like so, these are not in the paper. I think these are some work that we did after the paper. Like so, you can extend this idea to class incremental learning and even multitask learning. Like so, like in multitask learning, you can see PC grad, which is one of the state-of-the-art methods for doing multitask learning. And you can just tag the PC grad and you're going to get better performance. Okay, so like probably like the main bottleneck for using tag RMS prop is like it's memory intensive. So you can do this for small models. If you have a very big model, then you need to store multiple copies of the previous statistics, which is not easy to do. Okay, so I'm doing really bad in terms of time. So just to summarize this part, like so lifelong learning requires rethinking optimizers. Like tag is an example, but this is just one idea, right? I encourage you to think. I encourage you to think about better adaptive gradient methods for doing lifelong learning. So this is probably the first work to show that you can successfully use adaptive gradient methods for lifelong learning and still beat SGD, like because we have a lot of results in the paper which shows that tag Adam is better than SGD, which is better than Adam. Okay, so any questions? Okay, so I will continue. Okay, so I talked about optimizers. Okay, so now I want to slightly switch and talk about like the benefits of pre-training for lifelong learning. Okay, so like with very large models and like lots and lots of pre-training, like have we solved lifelong learning? Like, so like is forgetting still a thing, right? Like, so well, obviously pre-training is not going to solve lifelong learning, but there are a lot of benefits, like if you can use a pre-trained model for lifelong learning. Okay, so this is work done by Sanket during his internship with us, like, and my PhD student Darshan. It's JMLR 2023, but the work was done in 2020. Okay, so like so when you look at the models that we are using, like think about 2020, not 2023, because the explosion of models from 2020 to 2023 is so huge. Like so, but majority of the experiments were done in 2020. Okay, so does pre-training help in alleviating forgetting? Okay, so here is a motivating experiment. So you see like a standard split task that people do in continual learning here, like, and the only difference between the blue line and the red line is the initialization. Okay, so this is a digital bird, which is like the red line is randomly initialized digital bird, and the blue line is a digital bird that is initialized with pre-trained checkpoint. Okay, and we are just doing simple fine-tuning, like no fancy continual learning solutions. Okay, so as you can see here, if you initialize with a pre-trained model, you almost have no forgetting. It's a strong statement, but like the gap between these two models is so huge, right? Just standard mask language modeling on a bunch of data. So this is like a unsupervised pre-training. And then I'm doing supervised classification here. Okay, so you have all these knowledge that is gathered through the unsupervised pre-training, like which helps in like solving these bunch of tasks. Like so, like, but I think the majority of this part, like I'm going to explain why this is the case. Like what part of pre-training helps in this better performance, right? Like is it the knowledge that you get from the data, or like is it like the kind of space that you are in, like which helps you to not forget much, etc. Right? So this is the question that we were interested in. Like this was, in fact, the real motivation experiment for this work. So I'm going to show a bunch of studies here, like, but I want to highlight that this is a 40-page paper which has a lot of experiments in both computer vision and NLP. Okay, so I just picked some experiments which I think would fit the story today. Okay, so here, like we are seeing both NLP and computer vision tasks. Okay, so this study, like we're just going to look at the benefits of pre-training. Like so this is basically continuing the previous slide. Like so for every task setup that I have here, like I'm going to compare like simple fine-tuning. We are still not doing any experience replay or other things. Like so the only difference is whether I'm randomly initializing, which is the, I don't know what color is it, like so it's pinkish, and or I'm using pre-trained models, which is the purple. Okay, so in general, you can see that the pre-trained model like always gets better performance in terms of accuracy and also forgetting. Now this is true even if you use EWC or experience replay. Okay, like you can do experience replay with like randomly initialized method. Like, so that has really good performance when compared to like the right fine tuning, right? Like, however, when you also add pre-training, like you get really better performance. Okay, and this is true in terms of accuracy, forgetting, learning accuracy. It's true for both computer vision and NLP. Okay, so this kind of tells us that pre-training helps. Now, which part of pre-training helps? Like, so is it because I have a big model, or is it does it have to do with the data set or the scale of the data that we have, right? Like, so this is what we are trying to analyze here. So in this experiment, they are going to see a bunch of models, okay? So it's a digital BERT, which is probably the simplest, smallest BERT. And then there is BERT Bayes. We also have BERT large. These are like small and large versions of BERT. And we have Roberta Bayes, okay? Just the Bayes, not the large, okay? So in terms of the size, BERT large is the largest here, okay? You know, there are some interesting observations here. Like, so, like one thing that we notice here is the Roberta Bayes, which is a smaller model than BERT large, is actually doing better. And this has to do with the fact that this small Roberta model was actually trained with lots and lots of diverse quality of data, okay? So the diversity of data that this model has previously seen, it helps, which is what we can understand from the smaller model doing better than the larger model, okay? But in general, the size also helps because large BERT is doing better than small BERT, right? Like, so now this is with 5 data sets. So in the paper, we also propose a new challenging 15 data set benchmark for NLP, like, so which has a lot of different tasks in NLP, like different data distributions, class imbalance, everything involved. So here the results are a bit bad when compared to the 5 data set, but the trend holds, okay? So in general, larger models are better, more diverse pre-training is better. Like, so this kind of gives you some idea on like what model to pick, like if you want to pick a model and start fine-tuning your tasks, right? Now, why does this work, right? Like, so like we did some analysis on the loss landscapes, like, and you can see here that when you do pre-training, well, I think right now this is like a common knowledge that everybody has, like not so in 2020. I think this was close to your linear mode connectivity work and several other work that happened in 2019, 2020, right? Like, so we have some extensive analysis which shows that like when you pre-train, your model actually like is in a flatter region, like, and it's not just like flatter, like you get into these wider minimas, like where it is easy to move around different tasks, okay? So which is not the case when you have a randomly initialized model. Okay, so in some sense, flatness of the last landscape helps. So now this is also close to like SAM work. Like I think probably 6 or 7 months after SAM. Like so when we found that flatness helps, like so we thought, okay, so can we explicitly induce flatness by using SAM, like which is meant to find flatter solutions, right? Like, so can we just explicitly find flatter solutions? Like, then maybe we don't need pre-training, which gives you these flatter solutions. Like, you can just do random initialization and do SAM, and you should do better, right? So that turns out to be true. Like, so, like here you see that fine-tuning with SAM, okay, significantly reduces forgetting. In some cases, better than even pre-training. Okay, so the purple that you see here is pre-training plus just fine-tuning, simple fine-tuning. Okay, and this thing that you see here, there's no pre-training, but I'm using SAM. So just doing SAM, I can get much better results than pre-training. However, these are not two like competing solutions, right? Like, so they are orthogonal, so you can actually combine them. So that is what is actually a better performing model. Like, so like the best performing model is one that uses both SAM and pre-training. You can take a pre-trained model, and then when you fine-tune, you just do SAM instead of SGD. Like, it's going to give you flatter solutions, and it's going to be easy for you to move around tasks and have less forgetting. Okay, so any questions? Okay. I think, so the main takeaway here is like pre-training leads to flatter minima, and flatter minima like helps with forgetting, yeah.
I'm wondering how much this depends on how related the data, how related the pre-trained data is to the data that you plan to continue learning on. Like, because you can have completely different data sets.
Okay, so I don't have experiments for that, but I have intuitions. So it is true that the data distribution of pre-training matters, but it is not going to hurt you if you have a significantly different task, okay? Like, yes, pre-training and data is important, like, but the fact that it leads to flatter regions plays a significant role here. Like, so you might not see great benefits, but you're not going to see opposite effects too.
I'm gonna be that guy and ask, flatter, more flatter compared to what in pre-training? Like, what are we comparing? Because I see it's like flat in the sense that it's more connected, right? But like from the work we did with Merda, like you get that if you just do like a C-part task and then another, we didn't really do pre-training in that setting. So yeah, I'm just wondering, like, are we comparing against something or
Okay, that's a good question. So, which is, well, it's kind of related to, in some sense, like the experiments that I showed without pre-training, just SAM, right? Like, so it tells that pre-training is not the part, like, which is, well, it is important, but like probably the more crucial fact is like we are in a flatter place. But flatter with respect to what is a good question.
Maybe at some point you should brainstorm on a metric that measures flatness, something you can say like, oh, how flat is this minima? It's this number and that is that number.
Okay, I'm going to talk about a metric after this. So it might satisfy some of your criteria. But in general, like I agree with what you said. Okay. So far I talked about how pre-training helps with reducing forgetting, right? Like, so now what are the other ways in which we could avoid forgetting, right? Like, so now, okay, the results that I did not show here is pre-training helps when the downstream tasks are not significantly different, like from like the kind of task that you have already seen on the pre-trained data, right? So like if you see a totally different task, you're going to see more forgetting, right? Like relatively. Now, this is often the case, like because in a lot of situations, like you don't know what the next task is going to be, and often you're interested in a really challenging task, which might not have anything to do with the pre-training data. So how do we avoid forgetting in those situations? Like, so I'm not going to talk much about this work. Like, there's just one slide, but just to give you an idea, like I added this based on the discussion that we had yesterday about RAG plus LLMs, right? So what we do here, like, so this is a recent paper which is currently under review, like, but it's an archive, you can go read it. Like, so this talks about like practical tool usage for continually learning LLMs, okay? So the idea here is if you have really complex tasks to solve, if your LLM can use tools to solve these tasks, somehow you are working in a much more abstract space. So forgetting is less of an issue than like doing these things from scratch, okay? Again, I'm not going to talk about anything from the paper, like except for this one slide. Like, so here we look at different sizes of LLMs, starting from very small models to up to 13 billion parameters, okay? And there are 3 different setups here. Like, so we're doing continual learning with some toy arithmetic benchmarks, an advanced arithmetic benchmark, and also some glue tasks, okay? So like we're going to use tools. In the case of toy arithmetic benchmarks, we're going to use calculator as a tool, okay? There are different functions on calculator. And in terms of the glue benchmarks, we're going to use other small expert LLMs as tools, okay? So now you see 2 kinds of methods here, okay? So the blue lines are methods which doesn't use any replay, okay? And the orange are the methods that use replay, okay? So what we observe is, in general, things are hard even for very large models. Like if you don't use any tools, like you're trying to solve the task without any tools, okay? However, once you start solving these tasks using tools, plus you add experience replay, then you get almost close to 100% performance in these tasks, okay? However, if you don't do experience replay and just focus on tool usage, your performance is really bad, okay? So you still need the continual learning solution, like, but this idea of using an external tool, like, removes a lot of burden from the model.
Can I ask what's the difference between the bottom line, there are 2 plots where the blue and the red are reversed? They
These-
all both have tools, yes.
So-
That's in the next one.
This one?
Yeah, like what's the difference between these two plots?
This and this, or?
Sorry, the blue on the second plot and the blue on the first one, like what, are they not the same thing or they're different tasks or what?
So in each column maybe.
Oh.
Yeah, the two columns, sorry, I'm messing up, but like I don't understand the difference between
Oh.
this and
It's the metric.
Yeah, it's a metric. So this is accuracy. This is forgetting.
Oh.
This is learning accuracy. Sorry. So I was just focusing on one. You can focus on the one that you like. Yeah.
I'm a little confused. I didn't understand how you're using the tools. What is the tool?
Okay, so well, these are external API calls that you teach the model to do. Like so, like for example, like when you ask, like when you want the model LLM to do addition of two numbers, right? Like so, now it can directly try to predict the answer, or it could make a function call to the calculator, and the calculator returns the answer that the model gives it to.
So I don't forget if I have a dictionary here, like that.
Well, yes, but then like these results, right? Like it shows you that like even if you have the dictionary, you're going to forget. So you need extra tools.
Where like the bottom blue one?
So the bottom blue is like without replay. You just have access to the tools, no replay. So the orange is like both tools plus replay.
So what's the non-stationarity in terms of the API?
You're learning one task after another. Each task requires different set of tools.
You're saying that even if I have dictionary, the blue one will not learn, and that's the message here?
Yes, the non-stationarity still hurts LLMs. Like it's not like they can handle non-stationarity.
But it maybe depends on how you use it, no? Like I don't understand why.
Why? It makes sense because we're doing gradient descent with a parametric model, right? Like so, and it is not ideal for non-stationary setting. There's also a bit of overfitting happening with tools because these are like API calls and like you're teaching like a set of API calls, then you move to the next API call. That's the classical catastrophic forgetting of the previous API calls. So, however, the benefit of using a large model plus tools is you can quickly recover from this forgetting, like with very little replay, like so, which is.
Maybe sorry, I guess the half an hour, but still I'm commenting on your thought. But maybe the reason is that we know how to make gradient-based method work, and then we don't know anything else. Like we don't know how to warm start things, we don't know how to regularize weights, we don't know how to use tools. Right?
Yeah, I agree. Okay, so I think so. That's all about forgetting. Okay, so now I want to switch to like another topic in continual learning. Like so, we're going to talk about model expansion. Okay, so again, the theme here is like we're going to look at model expansion from the loss landscape perspective and try to understand like when expansion would help, when it would not help, right? Like so this is also work under review, like, but it is in archive. This is primarily done by my PhD student Pranshu, who has done a lot of the work that I'm presenting today, but in collaboration with Jerry, who is a PhD, and also my postdoc Quentin. So what are we trying to do here? Like so, training new models from scratch is an expensive process, and it is becoming more and more expensive like as we train larger models, right? Like so, like however, it doesn't make sense to always train from scratch like a new model, right? Like so, can we just expand a pre-trained model to continue training? Okay, so here I'm not talking about continual learning, like the traditional continual learning. Like so, let's say I just care about a single task, like I want to solve. I train a 2-layer network, I get some performance, let's say 60%. Then I realize, oh, maybe I should have trained a 4-layer network instead of 2-layer network. Or maybe I should have increased the number of hidden units from 100 to 200, right? So typically, like when you do these process, like as a researcher, then you're going to just start another experiment, like which has 400 units or like 400, like four layers, and then you continue, right? So now you're actually losing all the information that you have learned while training the small model, right? Like so why can't we just expand the small model to a bigger model and then train on this task? So this was exactly the motivation for Net2Net. Like I don't know how many of you know Net2Net. Like it's this really neat, simple idea introduced by Goodfellow and others like in 2014. if you read the motivation of the paper, this is exactly the motivation. However, it never got picked up. Like, so nobody does this in their real like machine learning research. Like, nobody starts their new model like from the previous model, right? Like, so like, why is this the case? Like, so why don't we expand and continue training? Like, so this was the motivation for this work. Like, so like we basically wanted to understand like what happens when you expand. Like, maybe if we have a good understanding of like what happens during expansion, and like if we can guarantee that, oh, if you expand now, like you're going to get better performance, right? Like, so then we can confidently start like using this in our daily routine of training neural networks, right? Like, so that is the motivation here. Like, so model expansion is in general useful, is not well understood. Like, however, there is this nice paper like from 2021, like which shows that model expansion leads to increase in global minima manifold in the loss landscape. Okay, so here you see, like, I don't believe these visualizations much. Like, so this is for your these are for your like developing intuitions, right? Like, so like before you start complaining. So, but there are papers which talks about how to visualize your loss landscape. Okay, so we use one of the standard papers which does this, but this is not even our figure. I think this is the figure from SimSec 2021. So here they show that like when you increase the model, like model's capacity, like when you expand the model, like when the model goes from mildly overparameterized to vastly overparameterized, like, so you see that the surface becomes smoother and it becomes easier for optimization, right? Now, our idea is to use some geometric properties of loss landscape to predict the impact of expansion. Okay, I think this metric might like be partially answered for what you said, like, but we still need a better metric. So what we are trying to do here is like, can we come up with a metric which will tell me that if I have 5 options of expanding, which option is going to lead to better performance gain? Okay, it's a very hard problem, I should say. So I think Francia took 2 years to arrive at where we are. Like, still, this is not a great solution. Okay, like a disclaimer. Like, so this is probably the first idea. Like, but we need to do more work in coming up with better metrics for predicting these kind of things. These are highly non-trivial to predict. Okay, so what do we do here? Like, so we propose a metric that's going to use permutation invariance in linear mode connectivity. Okay, so I think some people talked about linear mode connectivity in the previous talks, I guess. Like, but in general, the idea here is like for example, especially when you pre-train the models, right? Like, so you are going to reach solutions like where things could be linearly connected. Like, what I mean by that is like, so when you look at linear interpolation between 2 configurations, like the loss is low along these configurations, right? Like, so now like people observe linear mode connectivity in like a bunch of settings. I think this is like primarily popularized by Carolina and also Razvan's earlier works on like how linear mode connectivity helps in multitask learning, etc. Right? But we are going to use this for a totally different like use case. Okay, so what we are going to do is we are going to exploit some of the techniques that already exist in linear mode connectivity for a totally different set of problems. Okay, so like for example, like often people look at permutation invariance in linear mode connectivity, like where you just permute the neurons to get functionally equivalent neural network. Okay, but it's going to put you in a totally different place in the loss landscape, right? Like, so like if you think about the difference between these 2 neural networks, like, so I have just swapped these 2 neurons. Okay, so I have permuted these neurons, right? Functionally, they are both equivalent, right? Like, however, you are moving like in the loss landscape through these permutations. Okay, and people typically, when they do these kind of things, they do this to find linear mode connectivity, like using these permutations. Okay, instead of using this to find linear mode connectivity, like we are going to reverse it, and what we are going to do is like we are going to take new expansions, right? Like you have a current model, you're going to expand it like there are 5 possible expansions, let's say. For each of these expansion, we are going to do a bunch of permutations to figure out a metric for the manifold. Okay. Now this metric is going to tell us if this expansion is going to give me better performance gain or not. Okay. For me, initially, it was very like fancy in the sense, like I thought like these kind of things should not give like better predictions of performance, but surprisingly it does. So I'll try to quickly explain the technical details. Okay, so what we are trying to do here is we are going to take a particular configuration of neural network. Like each node in this graph is a configuration. Okay, and I'm going to connect 2 nodes if the barrier between these 2 nodes is less than a certain threshold. Okay, this is like I'm going to compute the linear mode connectivity. Like I'm going to look at the loss in between, and the minimum loss that you see, that is the barrier. Okay, so I'm going to see if theta 1 and theta 2 has low barrier, that they are linearly connected. Okay, like they are more linearly connected, right? And I'm going to do a bunch of permutations, let's say hundreds of permutations, and I'm going to compare how many pairs are linearly connected. Okay, so in some sense, the fraction of green lines versus red lines, right, is going to tell me how flat the surface is, because like all these permutations are linearly connected, right? So you have a question.
So I have a question. Maybe I'll get to this, and I'm jumping ahead, but and maybe we talked about this, but isn't this just looking at the covariance of the feature matrix and checking if that's low rank? Because to me, like if I permute 2 features and then I can linearly interpolate between them, it means that those features are doing exactly the same job. So I can average them, because it's like not, so it basically just means that like the features themselves are lower rank. So I wonder whether like a shortcut for this is just do like a covariance of the features, do an SVD and check sort of kind of the rank or the magnitude of the eigenvalues, and say that the one who's going to generalize better is the one who's going to have a lower rank. I don't know if it's true.
That's a good suggestion. Well, you work with Pranshul, so you should tell him to do this. Like so, we'll definitely try. It's a good suggestion. Like maybe that is what is happening here. Like in which case, then it is a more efficient way to predict this, right? Like so, I have not thought about it that way. Okay, so yeah, so what the manifold metric that we propose is basically the difference between these fractions, okay, for the phi star, which is the original model that we started with, and theta, which is one of the expanded models. Okay, so I'm going to compute this metric M for a bunch of expansions, and I'm going to pick the expansion which has better like value in this manifold metric. Okay, so in this case, like we're going to compare this idea of predicting the performance with a bunch of other algorithms which were not proposed for like expansion, but proposed for neural architecture search. So this kind of predicting the performance before training is a major thing in neural architecture search community. Okay, so in neural architecture search, like so you try different architectures. Now you want to know how good is this architecture without training it, right? So these are some of the existing methods to do that. Like so we borrowed all these methods for our problem, and you can see that manifold metric is probably the most consistent metric in predicting this. Like so, this is the correlation between the performance gain and the metric's prediction. Okay, so the correlation is high for manifold metric when compared to some of the state-of-the-art
compared to the true.
Yes, this is correlation with the true performance gain.
So like you train the model with small, then
you expand and then you train it again with the expanded model. So whatever the final performance that you get, that is correlated with what you predicted before training this model.
And so what is then higher correlation? I see.
Higher correlation is better.
Okay. Why not just plot them and it's easier to see the relative, because correlation doesn't. It
Okay.
could be deceiving.
Yeah. Well, okay. I also have some other graphs which shows the metrics. Okay, so there are a couple of hyperparameters here when computing the metric. Like so, one is the threshold. Like so, at what threshold I can say that there is a linear mode connectivity, right? Like so, the barrier threshold that's Q. And there's also the number of permutations, like, so how many permutations I'm going to try, like, before I decide, like, whether, like this is a good surface, right? Like, so, like, in general, we see that as you increase the threshold and as you increase the number of, like, permutations, you get much better, like, prediction, which kind of makes sense. So you can decide to pick these numbers based on the computational resources that you have. And so I'm going to show you some results on, like, manifold training, like, like, this is training after expansion, okay? So, like, in this case, this is CNN on C410. So you see that there are a bunch of expansions that we do from 10 channels to 12 to 16 to 24, etc. And you see the actual performance gain, okay? And you see the corresponding manifold metric, okay? So they kind of correlate in, like, predicting, like the performance, okay?
I did not understand the metric actually. Could you go back? I thought maybe I'll understand eventually.
Okay, well, maybe I'll.
So like M theta.
Okay, so metric. Okay, so the metric is basically the relative gain between, like, the flatness of the original model and the expanded model. Okay.
Flatness, like, sorry, what is? So like, how do you get it without training things?
Okay, so that's where we use these permutation ideas. Like, so, like, without training, like, so we just permute the function, like, and see how many of these permutations are connected linearly. Like, so, like, if the last barrier between these permutations, like, let's say for 80% of these permutations.
I thought you were growing. Sorry, maybe I just come from this field, so I don't get it.
No, this is after growing.
After growing.
Okay, maybe I'll quickly
I thought you were going to expand, so
yes.
I thought somehow you're going to add neurons.
Yes. Okay. Theta is expanded model. So phi star is like before expansion. Yes. Theta is expanded model. Now for both these models, you are looking at how good the manifold is for learning.
So you're saying that you're going to permute both of them.
Yes.
And then if some metric in permutation is different, then there's going to be more gain.
Yes.
Okay, but when you do real thing, you don't have theta, right? You only have 5 star.
No. Oh, okay. So for that, you need a method, right? We are using net to net here. Net to net is like
correlating the metric, I guess.
Yes.
You're not really giving a method to.
We use the existing expansion method, net to net.
Okay, you use a method net to net.
Yes.
So why does net to net correlate with? Like, I don't understand. So is the goal to show that expansion somehow is correlated with this metric?
Oh no. Well, okay.
To give a new method for expansion?
No. Okay. So the goal here is to come up with a metric which will guide you, like, which expansion is better. Okay. You could have 5 different expansion methods. You can use all these 5 methods. I will tell you, like, which one of them is going to be better.
Sorry, maybe I can also interject here. I mean, I also don't want to be that guy, but like going back to Dawson, like I think what Dawson said, there are quite a lot of expansion methods like splitting steepnesses, then Firefly, GrabMax, they've all did some kind of like Hessian covariance kind of thing to like do expansion and like base it off of their like. Have you actually tried like looking at any of those?
No, not here. Like, but you can use any expansion method that, like, you have. Like, so we use net to net, but you can use other expansion methods. Like, and
the point is the thing already. Like, if you have one of those like natural gradient or something based expansion methods, it's already telling you how to measure, right? Like,
okay.
It's like in the method. You don't need like a permutation.
Okay, so point me to those papers. Like, so I'll take a look. Yeah.
I'm even more naive here. So you actually grow from 5 star to theta because if I just imagine I just add in random ways, it won't be.
No, okay, yeah. So maybe I should have explained net to net. Like, so we are not adding random units. Like, so we use this method called net to net, which basically takes, for example, a 10-unit network. It expands to 20 units. But it is a function preserving expansion like method. Like, so, like it does some calculations and puts new neurons in such a way that the function is completely preserved. So like nothing changes in terms of the output for the same input.
If I remember correctly, it just duplicates the unit and then adds a bit of noise so that it breaks symmetry. But like the 2 units are kind of the same more or less.
It's a very simple method.
Okay, so this expansion will somehow still say this theta will be a local for the expanded loss landscape?
Yes.
Okay.
So if you do a bunch of expansions, like which one of them is better? That's what I'm trying to. That's the goal here. Like so. Okay, so I think I ran out of time. So, like, I'm going to just quickly talk about plasticity, like 30 seconds or 1 minute. Give me 1 minute. Okay, so so we had a lot of discussion about plasticity in Razvan's like talk and also in Rupam's talk, right? So I'm taking a slightly different angle here. Like, so everybody's looking at plasticity for computer vision and reinforcement learning problems, but because I do a lot of NLP, like we were interested in knowing whether plasticity is an issue with NLP or large models in general. Okay, so this is like a work that we just submitted to EMNLP this week. It's not in archive yet. It will be in archive soon. But one major result I want to highlight here is plasticity, even though it's a big issue with computer vision and reinforcement learning problems, is somehow not that big of an issue in NLP. Okay, we're trying to understand why, right? Like there are some intuitions and some experiments in the paper, but I don't think this is completely well understood. So here I show you like two tasks. Okay, so one is AG news with like there are a couple of pairs of tasks. There's AG news, which is an NLP classification task, and there is C410. Right? And we try to use the same architecture for both the tasks, so that architecture is fixed, just the data is different, okay? And you see that for the NLP tasks, like we don't see like laws in plasticity, like well, that is not true for computer vision tasks, okay? Like why is this the case? Like, so there are many things that are playing role here. Like, so is pre-training the reason? Like initially we thought maybe it's because of the pre-training, right? But we have experiments which shows that pre-training is not the main reason. Like even for methods which are not pre-trained, okay, like so plasticity is not an issue. And is it just because of the transformer architecture? That is also not true. Like so we tried some experiments with LSTMs, CNNs, MLPs. Like in all these architectures, like we don't see a loss of plasticity. And this is almost always true for Adam W than Adam. So when you do Adam, you can see loss of plasticity in some cases, okay? But when you do Adam W, there always exists like one good learning rate or many good learning rates, but this is not an issue. But this is not true for computer vision. Like in computer vision, you cannot find, for some of the settings that are reported in the literature, you cannot find any good learning rate, like where plasticity like issues doesn't arise, okay? So like and these were shuffled tasks. Like so we also did this for like sequence of data sets, and as you can see here, as I go through different data sets, right, like so for a variety of architectures, the performance on an average improves. Like I don't see loss of plasticity happening, okay? So like why, like we have some hypotheses and some experiments in the paper. Like so for now my hypothesis is the type of data distribution, the discreteness and the distribution of words that you see in language makes things easier, like when compared to like computer vision tasks, like where the input is image. But why is this exactly the case? We don't know. Okay, so this is like a really recent result I wanted to highlight and poke your interest in looking at NLP for these kind of problems. Okay, I will stop here like with a little bit of ad. I see a lot of PhD students here, and there are also PIs like who have PhD students, like, and I'm looking for 2 postdocs like to start very soon, like one in optimization in general. If you're an optimization PhD, like, and you're interested in like exploring deep learning or lifelong learning or LLMs, right? Like, so this is a perfect like position. And the other one is on foundation models and LLMs in general, like, but with a bit of more focus on biology data. If you have friends or if you have students like who would fit these topics, please ask them to talk to me. So I'll stop here. Thank you.
I'm going to be talking about sort of Bayesian neural networks, and I'm going to be sort of arguing that Bayesian neural networks are not Bayesian, and I'm going to be arguing that we need to basically completely rethink them. So it's going to be sort of slightly deliberately controversial, so I'm sure there will be lots of discussion as I'm going. So, starting point, Bayesian neural networks. We've got some sort of distribution over sort of weights, biases in our networks. We've got the sort of probabilistic neural network. We put a prior over its parameters, so that's implying some sort of stochastic network. They're sort of being sort of spouted as sort of these powerful models for kind of probabilistic prediction, in particular for kind of doing uncertainty quantification and sort of good regularization, and in particular for sort of things like sequential decision making. So it's often spouted that you might want to use them in kind of active learning and sort of similar settings where we care in particular about kind of reduced uncertainty. So in the talk, I'm going to first...
A lot of this I do not agree with. So maybe we're talking about different Bayesian neural networks, right? But I'll let you go with the talk. But I wanted to say that.
Fair enough. I'm not sure I agree with a lot of that as well. So this is sort of more hypothetically, they've been proposed as these sort of things. This is how they're often solved, and actually I agree, I don't think a lot of that is correct. So the focus of the talk is going to be around sort of, should we have a fully stochastic network? Should we actually be doing this inference-based scheme where we put a prior and do inference? Or, given these are expensive, problematic, should we instead look at kind of partially stochastic networks? Should we have networks that are maybe not coming from a Bayesian formulation and where sort of some of my parameters are stochastic, but some of them are learned to sort of deterministic weights and biases? So the sort of spoiler for the talk is that we're basically going to say that no, I don't think we should do these sort of fully stochastic networks, and yes, let's go and these partially stochastic networks are potentially going to be much better. Obviously, this is a bit reductive, but like this is just sort of where we're roughly going. Okay, so let's take a step back and let's go things more carefully. And of course, we're going to start with Bayes' rule as always. So sort of Bayesian neural networks originally come from the idea of I'm going to put a Bayesian formulation down. And when I say Bayesian neural networks aren't Bayesian, I don't mean that their formulation is not Bayesian. They obviously are formulated originally as a Bayesian system. We put a prior over the parameters, i.e. the weights and the biases. We set up some sort of likelihood function where we pass everything through and then we have a likelihood at the end. And of course, Bayes' rule tells us that this is proportional to posterior. This, in turn, gives us a stochastic predictive model. So ultimately, a lot of what we care about is not actually what's the distribution over the parameters of the network. That's pretty arbitrary. It's the sort of push forward of that distribution to the actual predictive space. And so we're hoping to get sort of uncertainty in our predictions at test time, and in particular, potentially sort of reducible uncertainty if we want to do things like active learning. To do that, we of course need to do approximate inference. So we're not able to calculate that posterior, we're not able to sample from it. We've got to have some approximation, say Q. And in general, this thing's going to be inaccurate, and in most cases, it's also going to be costly. And of course, as you will say, that there are cheap versions of this as well, but there's sort of definitely a trade-off, and it's definitely a problem that is difficult, and we generally can't get something close to this. In particular, what we're actually often doing is we're trying to do inference here in millions, maybe even higher dimensions, over something that's sort of not necessarily single modal, and it's way beyond anything we really actually tackle in kind of Bayesian inference. So this is sort of horribly intractable, and I'm going to argue sort of so intractable that we're off from doing anything kind of approaching it. And where we're going to be going then is to say, instead of this Bayesian formulation, I want to sort of set up some kind of partially stochastic network. So I want to set up some kind of learning scheme where I'm going to learn a network where some of these things are stochastic and some of these things are deterministic. So sort of hypothetically say I could do variational inference where I'm just going to learn the mean of these and keep them sort of as normal parameters. And here I'm going to learn, say, mean and variance to make them sort of stochastic. And the question that first comes with this is this just sort of an approximation of the fully stochastic network? So I'm not the first person to talk about these sort of partially stochastic things, but pretty much unequivocally when they've appeared before in the literature, people have said, oh, instead of doing this fully stochastic thing, maybe we're going to sort of approximate it with this partially stochastic thing. They're kind of seen as like a cheap man's Bayes. And I'm going to be arguing that this is not true. Basically, I'm going to be arguing that actually, at least certainly from a theoretical perspective, often these partial stochastic networks are possibly better. Empirically, we're going to find that they're often better as well. And so we shouldn't be thinking about them actually as these sort of approximations, but as potentially sort of preferable schemes in themselves.
So what do you mean by stochastic? Like, is it a random variable in the Bayesian sense, a random variable in some other sense, or like, because it could be noisy, SGD is noisy, I don't, right? Like, there's lots of things when you say, should they be fully stochastic?
What I mean is that we've learned a scheme, and at the end, some of my weights are fixed, some of my weights or biases are not fixed. So I'm learning a distribution over some of these and not over others, or I might have a set of samples where some of the weights and biases are shared across samples and some of the weights and biases are not shared across samples. So it's a case where basically whether things are fixed when I pass them through the network, or whether I am sampling things inside the network when I need to pass things forward. So with the sort of the fully stochastic case, this is sort of clear cut. I'm kind of arguing this is a Bayesian formulation. I've written a prior, I've put a likelihood is the normal thing. It's not the only thing you could do, but it's the normal way to set it up. And then
I think I'm following what you're saying, and just to clarify, like, let's say you do frequentist estimate of a parameter, right? You still have some kind of, you could do like Hessian around it that gives you some Primer-Rao or bound or Fisher information matrix. So you still have some kind of sense of confidence, uncertainty, or whatever you want to call it, right? But when you decide to do prediction, you may be Bayesian about it, meaning that you average over them by sampling through them, or you may not. But it doesn't mean that there's not a distribution or some kind of, curvature around it. So when you show this picture, just want to be clear that you're not, like you're saying, even Laplace approximation is bad, something like that, like having this Hessian doesn't mean anything. We should just completely ignore it and just look at the value of that data that we have. And for others, maybe we should.
Okay, so this will sort of hopefully become a bit apparent through the talk. There's kind of multiple steps. The first thing I'm going to be kind of arguing is that none of this is really Bayesian actually in the first place, and therefore kind of when we think about this as doing a Bayesian posterior predictive, it's not, and therefore they're kind of that thing we want just doesn't exist. And so really what we've got is we have some network that has some stochasticity that we can then average over that stochasticity at prediction time if we want, or we can not. So say we do a plus, then we can draw multiple samples from that and average over the predictions. So we have some network that is stochastic. We've done an approximate inference scheme, for example, that gives us samples or a closed form approximation. And when we want to make predictions, we're generally going to do some sampling of that and do some averaging to make our predictions.
So can I put it in this way? For those layers you want it to be deterministic, I put a very high precision, and I don't infer the precision. I just fix the precision to be a very high value. While those stochastic layers, the weights you put some inferable precision. We let it flow with the data. In the end, when we do the inference, we sample from those high precision layer, we somehow get a deterministic mean. Well, at those other layers, you get more variance.
No, not really. Okay, so I have a network. That network is defined by a set of weights and biases and some activation functions, some sort of architecture. So that the parameters of my network are a set of weights and a set of biases. Those weights and biases, I can have a point value for all of those weights and biases. I can have a distribution over all of those weights and biases, or some of them can be fixed to single values and some of them can have distributions over. So the fully stochastic one is where there's a distribution over every weight and bias. The partially stochastic one, I'm assuming that some weights and biases are just numbers, and some weights and biases have some kind of distribution over it. The picture I've got is actually probably not the best one in the sense that it doesn't have to be stochastic layers and deterministic layers, and what we're actually going to find is what you really want is a mix of stochasticity and deterministicness inside each layer. So it's not actually a per layer thing at all, but it's just when we learn it, how do we learn it in the way of some things being fixed, some things not being fixed? So big question is, whenever people do these Bayesian neural networks, they are implicitly saying they want this to be fully stochastic. The formulation of saying I write down a prior, I do some approximate inference, that is a formulation that is based around this being a sort of a fully stochastic scheme, and is that actually preferable to partial stochasticity? So to sort of start getting into this, we can start saying, what are the reasons we might want it to be fully stochastic? And the first is that we might just go with the Bayesian justification. We might say, okay, this came from a Bayesian formulation. Maybe I like this because it came from a Bayesian formulation, and there is actually sort of good Bayesian reasons to have actually set it up in this way. The second thing is that maybe it increases expressivity. We would often think if there's sort of more stochasticity in my network, if we've got more stochastic parameters, you would generally expect there sort of to be more flexibility in the sort of distributions that it can approximate, and so there's sort of a hope that maybe that extra stochasticity, that extra work we're doing, is going to give us something kind of the power and the expressivity of this network. Finally, there's a question of does it improve our practical performance? Maybe this choice is just empirically justified, and this actually works.
Maybe there's a fourth one. It's just simpler to not have to think about it. Right? If the variances automatically kind of became very small, that's on the thing. It's just easier, right? I mean, if I have to make this choice, then I have to make a decision. Sorry, I'm not dissing or anything.
So this can be true for certain inference schemes. So say I'm doing like natural gradient variational descent, yes. And there are reasons where sometimes that formulation comes out nicely. What we'll see is that there's lots of cases where it doesn't. So say I'm doing HMC, I can kind of train to a map, I can fix lots of them and do HMC over my 10 million parameters, or I can go and do HMC over 20 parameters. So it really depends on sort of inference scheme. And yes, there are some cases where it is just justified by simplicity. But what we'll even find is that in some of the cases where it seems like swag, you might expect that it just sort of naturally comes out because we're kind of averaging over the gradient path. We're actually going to find that swag is worse when it's fully stochastic than when it's not. So even in some of these cases where it just sort of seems to naturally come out, it's actually an implicit assumption we're making that's potentially not well justified. Yeah.
I mean, so to answer the question with Laplace, I mean, there it's also very common to do like last layer only or the subnetwork that you were citing. And it's actually the interesting thing that we found is it's much harder to get it to sort of set the prior and everything right, train it right, so that you can do full network posterior predictive. So it's much harder to set everything up in the right way so that the full posterior predictive with all the weights would perform well compared to the last layer one, which is very, very hard to beat. So I think that would be a bit of evidence for what MT is saying, that it's so if you wanted to do all weights, that's just much harder. And sort of making it simpler might sort of just make it simpler in the end in terms of like the inference procedures as opposed to being sufficient.
So are you saying that it's harder to do last layer plot?
No, it's harder to do full network.
Okay, yeah.
This is very hard. Like it's very
Yeah.
you can get it right if you set the priors very well and so on, and you train the network really to convergence and so on. But if you don't do that, like the full one will always diverge to some extent. I think Swag does the same thing.
Yeah. So yeah, absolutely. So like yeah, we've got this implicit assumption of full network inference. Most of the literature is based around this, and there are good reasons. I haven't even started to go into that. We might want to avoid Okay, so where we're going to go is that basically we're going to see that none of these things hold up, essentially. It's not going to behave like a Bayesian model. It is not going to increase expressivity. In fact, theoretically, it's going to have worse expressivity than a partially stochastic network. And we're going to find sort of practical performance-wise, again, it's not beneficial. Even when we do tune things, as Alex was saying, which is hard, even when we do our work and try and get that right, it still seems to not perform very well. So let's start with the top, okay? We've written down a Bayesian model. Presumably there's some nice kind of Bayesian justification because we wrote down a Bayesian model. So does the Bayesian justification for this sort of full stochasticity hold up? Is it good that we could write this down as a Bayesian model? And was that a good thing in practice? And the first thing, sorry, it's a bit of a delay, is to think about, well, we've got this approximate inference we need to do, and that approximate inference is really not very accurate, and different schemes give me completely different behavior. So this is just a sort of simple regression problem. My samples from the prior look like this on the top left. H and C gives me one kind of fit, variational inference this one, Laplace another, swag another, and these can't all be correct. Sort of one of, maybe you say, okay, H and C is the gold standard, but even for this really simple problem, and this is also quite a small network, these other inference schemes, they're still very popular. They look nothing like the H and C inference, and so we can't really be calling these guys a posterior, or even really an approximate posterior. They're so far from that, it's not really true.
What kind of Laplace is this? Is it diagonal?
I think it's full Laplace because it's a small network. So yeah, we did a few variants. I can't remember which one I exactly put on the slide, but we did do this including full Laplace. And what gets even worse is that sort of what we really often want with Bayes is consistency. So Bayes is sort of consistent under its updates. So the order we sort of see the data doesn't matter. A posterior at one step becomes the prior at the next step. But if we go and take a Bayesian neural network, we actually do this. We take the posterior from one step and then use that as a prior and redo the inference. Everything again just kind of goes wrong. So this is doing variational. We've got some data, we do some variational inference on it, we get a new posterior, we get some new data, still doing okay here. But as we get a few more data points, we suddenly find that it completely forgets its old data. And this kind of sequential updating that we should be able to do in Bayesian inference. And certainly if we're doing active learning, this is like the key reason you would argue for active learning, is this is kind of your reducible uncertainty, this ability to predict how it will change. It just goes really quite wrong. And again here, now we try and put HMC, this sort of supposed state of the art, and actually even HMC is falling sort of quite foul of this. I take this sort of variational posterior here, and I do that as the prior rather than my normal prior, and I get this pretty terrible fit. So we don't really have, again, this sort of sequential updating that we might see.
How do you do it with HMC? Like, how does it?
So we take this variational approximation here as the prior, and then we're just running HMC with that variational approximation as the prior and the new data that we've seen, which is, it's actually in with the other data, I think this.
And you give it infinite data when you want. So, I mean, that's the theory.
I mean, unfortunately, I couldn't give it infinite data or infinite time, but I'll try that next time.
Right? You cannot expect consistency.
So yeah, so we're justifying that these things converge, but the argument is basically we're just so many orders of magnitude away from where we need to be to have anything about convergence really happen.
I think one nice thing that basic people would like to have is exchangeability kind of thing, right? But whenever you start to do approximation, I think exchangeability won't work. Okay, so I get many of the cases, I mean, and from my equation, when you do the sequential thing, without exact Bayesian inference, you see forgetting, exactly because you don't have this exchangeability thing hold on.
Yeah, totally agree. I mean, I'm not trying to say that there's some magic thing that suddenly necessarily gets this everywhere. I mean, a GP might for this kind of data, but it's more of a case that we've made this assumption, and we're telling other approaches that they're heuristics. We're saying, oh no, deep ensembles, we can't have them because they're not Bayesian. Well, none of it's Bayesian in the first place. So like, why it's really a stopping of we're crushing certain research paths because they don't fit an ideal that isn't actually happening.
Just being Bayesian is not going to fix, the problem. So you do anything in this situation, anything, other than this, I don't know why you didn't do it, you will not get right answer. It's not like it's broken because it's Bayesian.
I'm not trying to argue it's broken because it's Bayesian.
So you're showing, like, the slide that you show, and you say, oh, well, it looks
No. I'm trying to argue that it's not actually if it's not actually behaving like a Bayesian system. What I'm saying is that we might have chosen to do this because it was a Bayesian formulation, and that actually requires it to sort of act like a Bayesian. So if it sounds like a duck, looks like a duck, it's a duck, and this doesn't look like a Bayesian, it doesn't sound like a Bayesian, it doesn't act like a Bayesian.
I want to have formal prediction bound here. This will be really filling the whole space, because that's what you will see probably. You know, you have finite energy. Maybe that's why it doesn't work.
Sorry, but like, I would love to see the next slides.
Yeah, okay, yeah, we're over halfway through it. I haven't got this on the intro, basically. Okay, so next question, what about better inference? So there's this mail-off paper where they start saying, okay, what does the Bayesian neural network posterior really look like? And they presented lots of results that sort of said, oh, here's what the posterior really looks like, here's loads of tests that show that it is. And to sort of save some time, basically it doesn't if you look at their own results more carefully. If you just download the raw data and you actually analyze it properly, you can show they haven't got the posterior. And this was huge amounts of compute. It was like, I can't remember, but it's hundreds of thousands of GPU hours with HMC that's like way beyond anything practical. And basically, what we did is we just do some sort of bootstrapping from HMC chains, and if you do some bootstrapping from HMC trains, and particularly if you put any corruption on the data so it's not the original inputs, it should look like this, and it looks like this. So this is sort of agreement within chains. So long story short, you can very quickly falsify that even with huge amounts of compute, full HMC inference, you can quite easily show that is not samples from the posterior. And this is true not just in parameter space, this is in predictive space. So the argument has often been, okay, maybe it's not the true posterior of my parameters, but it's all okay because I care about predictions. This is in predictive space, and it shows you in predictive space, you provably do not have samples from the posterior. And therefore, okay, we're not doing inference. So in short, I would argue that this thing is not behaving like a Bayesian, even with huge amounts of compute, and even when we put a lot of effort into it. So maybe there's nothing else that does that, but it doesn't in itself give us a justification for this approach. So a heuristic might actually give you better on this. It might not, but this itself is not a sort of justification. We have to go forward to the empirical justification and rely on that, not the actual formulation.
Sorry, I'm not sure I've got the agreement.
Yeah, sure. So basically, these are different HMC chains, and then it's the percentage of the time that the prediction from the two chains agrees. So on the right, it's sort of, this is how on average sort of things agree, and then it's sort of this on the left is agreement of independent chains, so how much does a sample from chain 1 agree with a sample from chain 2, and on the right is jumble it all up, and how much does two arbitrary random samples agree with each other. So what it's showing is that things don't agree as much if they're from chain 1 or chain 2, and if the chains aren't agreeing, they can't be samples from the posterior, because they should all be then sampling from the same distribution.
So this is like a mixing kind of thing, right? Because in their paper, I think they did the standard R-hat mixing thing, and they say like in the function space that it's mixing.
Yeah, it's just wrong. They do it in very idealized settings, and it's frankly a bit dubious.
Your previous examples all relied on one way or another on approximation, so variation approximation, loss approximation. It's not surprising that those don't give you true posterior. But HMC has asymptotic guarantees, right? So why is this not? Is it just that if they ran it longer, it should work? Is that true?
Yeah, but it probably, I would guess on an engineer's estimate it'd be longer than the life of the universe. So, with just so many orders of magnitude off compared to where you would run HMC as a statistician and where you would expect to get anywhere near to sort of that regime. And I'm joking in the exact length of this, but I have no idea. It's definitely, they were already running way more compute than anyone is ever practically going to do in the next 20 years. And so for the foreseeable future, we're definitely not going to have the compute to get this in a convergent regime. Okay, so next question is the expressivity. So the other thing we might say is that, well, okay, it might be good to have sort of more stochasticity, because that should kind of give me a more flexible system. It's like if I'm reducing lots of things to point estimations, that's a sort of a strict subset in some ways of the things I could have where things are all from distributions. So there's some possible argument that, okay, I put more stochasticity into the system, maybe I get more kind of flexibility that comes out. So which of these is kind of more expressive in a sense of what functions it can kind of represent, and kind of what is the hypothesis class that's kind of underlying these two sort of setups, and is one of these actually a better hypothesis class than the other. So another way we can look at this is we can say, let's give ourselves sort of an arbitrary conditional distribution approximation. So I've got some inputs, I've got some output that I'm trying to predict, and I'm trying to capture that output distribution given the input. And I'm going to focus on regression because sort of classification is trivial. With classification, a deterministic network's enough. You can just regress from the inputs to the probabilities, and that's just a deterministic regression problem. You don't actually need stochasticity for expressivity when you look at classification, but in regression you do, because now it's a full sort of possible distribution that we might be looking at. Alternatively, you could think about Y as kind of the logits themselves and a distribution of the logits and kind of what things can we do. So can we approximate some arbitrary distribution, and how can we kind of do this? So the result we show in short is that partially stochastic networks with careful setups are what we call universal conditional approximators. So you've come across probably the universal approximation theorem that I'll lay out a bit more carefully in a minute from sort of neural networks, which is this idea that they can kind of approximate any deterministic function arbitrarily well. And what we're going to show is that with certain conditions and certain setups, partially stochastic networks can do this for conditional distribution approximation. And the setup that you basically need, and this is a bit briefer, but in short, we need to have a number of random biases that is equal to the output dimensionality. We need a number of additional deterministic units in the same layer that's equal to the input dimensionality, and we need a downstream arbitrary wide hidden layer. So basically any neural network that has this in some sense embedded in it, that I can then add lots of extra layers if I want. I can add extra deterministic units, extra stochastic units, but as long as it's kind of got this thing as a sub-network living somewhere inside it, this thing is going to give you a universal conditional approximation, provided that we have activation functions are continuous, invertible, and non-polynomial. So this is so something like a tan H would be fine here, sigmoid would be fine. ReLU we can do, but we have to do some extra work. Some restrictions on activation functions. We need some set of stochastic units and lots of deterministic units. And the key point I'm making is that I can now, from this, I can sample from any conditional distribution arbitrarily well. So obviously I've just made a bit of a claim at this moment, let's go into details, but yeah, sure.
It's like a marginal distribution for one output. So when you say arbitrarily well, is that for one output of one data point, or is it for any collection of data points? So you can have like any stochastic process on any collection, or any number of data points. So that seems even harder.
I get the question. It's quite a good question. It's basically the latter, but because the latter can always be formulated as the former, as long as it's a finite set that's incoming. So sort of formalizing it fully as a stochastic process would take some work, but I can always say that it's like a high dimensional input process to a high dimensional output process. And if the size is varying, I can always ignore some things. The only thing that's then difficult is like the infinite case. So actually proving sort of Kolmogorov consistency might actually be difficult, but for any sort of finite truncation of stochastic processes, it should be fine. to sort of formalize really exactly what I'm saying with this conditional approximation, you need to understand something called the noise outsourcing lever. And if you've not come across this, perk up, because I think that this is one of the most important theorems in all probabilistic machine learning. Lots of people are not familiar with it. So what the noise outsourcing lever says is that if I've got two random variables x and y, then there exists some kind of noise variable eta, which say is Gaussian, and some measurable function f tilde, such that eta and x are independent, and x and y is equal, not just in distribution, but equal to x, f tilde, eta, and x. In other words, f tilde eta of x is y given x equals x. So what I'm saying here is that for any conditional distribution, there is going to be some way of taking away the noise and then mapping deterministically that noise and what I'm conditioning on to produce the output variable I want. So anytime I'm trying to get that kind of, say, predictive distribution, I can always map that in some way. There is some arbitrary function that will take in noise, my inputs, and it will give me the correct distribution. So say, for example, I'm doing regression. What I'm saying here is there is a function that will take in the input of my regressor, it will take in a noise variable, and it will output things that are exactly according to whatever distribution I want them to be according to. And this thing exists. It's called a generator function. It's not unique, and that's also quite important. There's actually an infinite set, usually, of these generator functions. And there's lots of different ways I can actually set up this eta. So it doesn't need to be Gaussian, it's just there for sort of general purposes to make things easier. But really what we're saying is I can always map inputs plus noise to outputs of any distribution. So now what we really want to say is that we can basically get our network to kind of give us this f tilde in some kind of sense. So the second thing we're going to need is the universal approximation theorem. So this universal approximation theorem from the 90s sort of says that for any sort of inputs on a compact subspace, and f theta mapping from that inputs to outputs as a fully connected neural network with one hidden layer of arbitrary width, a non-polynomial activation function, then this can basically approximate any function arbitrarily well. In other words, single layer MLPs with an infinitely wide hidden layer are universal approximators, and they specifically can approximate anything that is continuous. So they can't do step functions, but any continuous function you can do. And this can also generalize, so it doesn't need to be a one-layer MLP. If I've got a multi-layer MLP, this also works subject to some extra restrictions, but I need basically one infinitely wide layer. In other words, if my network's big enough, it can fit it.
Previous, yes, okay. When you grow dimensionality of x and y, well, it's kind of like in the GP setup. Okay, so first you need to grow m.
Actually, you don't.
Okay, and second, if let's say you don't grow m, then would the f2d function be the same always when you grow dimensionality of x and y?
So f tilde is not unique. So there is multiple ones anyway. M can always be 1 because you have these kind of space filling curves. What we're going to see in a moment is that for it to map up here, it's got to be continuous. So we are going to later say that we need M to grow, and we need M to grow with the number of outputs. And that's actually so that this f tilde can exist and be continuous, rather than just its general existence.
Okay, your f tilde is non-unique, but when you construct this set of f tilde and then think about the intersection of these sets when you grow the size of x and y, would you actually have a sort of like a non-empty set? Do you see what I mean? What I'm trying to see here is whether there is this, let's say, this set of f tilde that satisfy these states regardless of how I grow x and y.
I get the question now, let me think. I don't think so, in general. as y grows, you can make it autoregressive, and there's sort of some autoregressive scheme. In certain cases, like a GP, there will be some common function. In general, though, if I add an extra input, there's no kind of natural way, I think, for my function to sort of change as an extra input comes in, because I've just sort of defined another problem. That's a sort of I'm trying to do y given x in the first place, and if I give an extra input to x, I can have arbitrary change in what that conditional distribution now is, so there's not really an easy way to kind of generalize how that will work.
Sorry, I have a question. So I'm a bit out of my depth on the probabilistic side, but I guess you're relying on the universal approximation theorem to kind of get your proof. And I wonder whether this says a lot, because in some sense you're going to say that the partially stochastic one are universal approximator of stochastic functions. But that, I don't know whether that says that, I mean, we had the same issues with neural networks, right? The universal approximator doesn't say anything. It doesn't tell you that this class of function is better than that class of function because it's a universal approximator. Like, basically, that maybe you approximate the stochastic function only when the width goes to infinity, which will never happen in practice, while a fully Bayesian model would actually do much better with a much smaller model. So I wonder, like, is there anything pragmatic that you get out of this, or is it going to end up being like, well, they're just kind of the same class, but we don't know if one is more efficient than another to approximate?
Yes, this is a great point. Remember, like we were originally talking about the expressivity. So originally, we were sort of saying, is this sort of intuition that more stochasticity makes it more expressive? And we're sort of, you're right that we're focusing on the asymptotic case, and so that is going to be the main result. And basically it's hard to do the finite case. There is going to be an important bit that comes out, which is that any finite fully stochastic layer is going to be problematic. So you're actually going to have sort of an information destruction that happens in a fully stochastic network. And so this is going to give us insights into sort of what you need to preserve in terms of information that's coming in, and that sort of a fully stochastic layer can actually be detrimental to sort of preserving that input information. But in general, yes, I completely agree. We have to kind of go to the empiricism, we have to kind of look at this and how they behave, and that's really where the proof is. We're arguing that these are unjustified assumptions people are making, that we're not trying to say you should definitely all go and use these partially stochastic ones. It's that we're all assuming you should use fully stochastic ones, and there's lots of reasons you might think for that, and they just don't necessarily hold up. And it's kind of, the burden of proof is kind of the other way. No one has proved this hypothesis that maybe finite ones that are fully stochastic do have better expressivity than the partially stochastic ones. It's kind of, we haven't been able to prove that's not true, but like everyone's sort of assuming it's true, and there's no proof for it. So, this gives us insight that it's probably not true as well. Okay, so we've got this idea of noise outsourcing lemma. We've got our noise coming in, we've got our input, and we're going to be able to transform that to our outputs. We've got our universal approximation theorem. We've got basically saying a big enough network will approximate any function. In particular, it can approximate this generative function f tilde that we're trying to get. And so the proof is basically to show that our network can recover noise and input, and then the downstream network is a universal approximator. So if I kind of come back to this, here I've got a number of units that's equal to the number of inputs, that's equal to the number of outputs. These H1 and H2, these are the ones that are going to generate my eta, my noise. The H1 free, that's the one that's going to preserve my input. And then this downstream layer here, this is a single layer MLP with infinite width. This is the universal approximator. So I need to have all of these components, I need to be able to get the input. If I lose knowledge of the input, I can never get it back. I need to be able to have noise that's separated from the input, because otherwise my noise outsourcing lemma won't hold. And so I need a network architecture that allows us to do that. So unfortunately it gets a bit more complicated when you really get into exactly how you set the network architectures to do this. The simplest is just to input some noise at the start. So if I take my inputs, and then I input a number of, say, Gaussian or any other continuous noise inputs right at the start of the network, then I've got myself one of these UCDAs. I can also just stick it in the first layer, and this is where the invertibility of the activations comes in. I need something where my activation functions don't kill information, because if they are non-invertible, say I use ReLUs and I don't do something else that's careful, again, I can kind of destroy information about my input that I can never actually recover back. So some of the things that come out, as I say, we've got this key idea of not destroying information, and this is where the need for these deterministic inputs come in. So if everything is stochastic, I can't recover the inputs anymore. If I can't recover the inputs, I can't necessarily do my exact approximation. So sort of a finite width fully stochastic layer is theoretically problematic because it will potentially destroy this information I actually need for prediction. I had this idea again, we need some sort of invertible activation functions. There are ways of doing it with ReLUs. You basically need double the number of units, because then one unit can do max x0, one can do min x0, so you can kind of recover both parts. And then you need to also make sure your noise is positive only, so that the noise doesn't get killed off. So if you've got these kind of three components, you can get away with ReLUs as well. And as I've been saying, this fully stochastic layers is generally going to be problematic. We can also keep adding layers. We can always have sort of layers be kind of identity functions. You can just keep propagating things. I can have a layer that does nothing. I can add extra units. Again, they can do nothing. And so sort of all the theory will hold as networks get bigger if I need. The other thing to think about here is some of this gets difficult to prove if I look at the weights. So all the architectures we've managed to establish, these are all based on stochastic biases. So here, if I come back, this was a stochasticity actually implicitly that I was saying on the bias, because if I have on the weight, it's not clear I can sort of disentangle that stochasticity with what I've times it by, but when it's added, I can kind of have the weight be 0, and then a 0 weight plus a bias gives me a random number to give me some independent noise.
Okay, maybe my question is not about this proof procedure, but it's mainly about the result that you're using is, to me, actually indicating that in some sense, the dimensionality of the randomness does not matter, or as long as it is, let's say, finite, and you have some clever way, right, to transform, let's say, this finite dimensional random noise to some interesting thing, then you get some interesting, let's say, distribution out. So that actually something relates to this idea of neural processes, right? That is something when he came out, he somehow excited my supervisor and he now actually moved away from GPs. So I don't want to criticize him, but I guess maybe my question is actually, do you see any value of having, let's say, infinite dimensional noise?
No. I think there is need for infinite dimensional noise when you need to be truly non-parametric. So neural processes, Gaussian processes, the real benefit comes in is there are cases where you want truly non-parametric predictions because of how it behaves and sort of how uncertainty estimates behave in a truly non-parametric way. Can actually. Sorry?
Do you have an example of truly non-parametric case?
Sorry, say that again.
Do you have an example, let's say, in deep learning applications that need truly non-parametric solution?
I might open that to the floor. Hypothetically, it's cases where you want sort of truly non-parametric prediction. So if you're getting a lot of data so it doesn't saturate, there is some behavior in sort of sequential updating that's very particular. I can't, off the top of my head, think of a good application. And going back to your earlier point of what the result shows is it doesn't necessarily matter how much noise it is. I just want to add the caveat. It doesn't matter how much noise it is as long as there's enough, where enough is your output dimensionality. Because if you have less than that, then you've got no continuous generating function. So the generating function exists, but it's no longer continuous. And if it's not continuous, then it can't be approximated with the universal approximation theorem.
So your definition of the noise inversion theorem is the definition of a random variable. It's a total measurable invariable. This is the first thing we teach. We were taught it, right? So that's basically it, right? So there is no difference between that lemma and what the definition of a random variable fundamentally is. This is more of a remark, right? So
Pretty much. There's some care that needs to be gone in the proof, but I think I'm always surprised how often people from computer science backgrounds don't properly know their definition of random variables and where this comes from. And I think there's lots of cases that fall foul of this. I mean, we never think about the fact enough that like stochastic neural networks just need a stochastic input. This is always just sort of discarded away, but as you say, the fundamental definition of a random variable tells us that's enough.
So one question, one remark. So your picture is not representative because if you want to preserve the input, there has to be a chain where in this example, this is an example I understand, but the H1s are affecting you have to have one chain which preserves the input till the end. So the output of the stochasticity cannot influence that, because then by your second layer, your input information is lost.
But I think that is it, so it's from X to here to here.
But HN2 loses that information.
Then H13 has it, and then yes. So this weight, all of these weights can just be 0. So I'm allowed to choose any weight I want, and then I'm just going to choose that that's 0, that's 0,
so
that's 0.
That's what I mean by you have to protect the input chain without getting affected. You can have a
Don't forget we're proving the existence of something that matches it. So.
The third one is a remark, which is that so the non-polynomial activation function is for folks who work on deep learning theory. That actually shows up very commonly. That's something I work part-time, I have used it. The easiest way to get to that is to look at the Harmite series, infinite series, and orthogonal representation. So that's actually a very important requirement, that activation functions are non-polynomial. If you get into the weeds of real theory, that we have all seen it papers.
Yeah, absolutely. I mean, this is something that's we're not introducing, this comes from the universal approximation level. This is already deeply ingrained in the approximation in the first place.
Sorry, I want you to get to the experiments, and I know we're a bit out of time, but I just quickly. So as Alex said, like a very popular way of doing this partial stochasticity is to use last layer of last. But what you're doing here is kind of the opposite of it. Like you do the first layer randomness, and then the rest is deterministic. Like, would your proof also work for last layer methods, or is that like?
It's the single case that doesn't work, and it's quite easy to show this because if it's the last layer, the form is fixed. So if I say have a Gaussian on my last layer, because my actual predictions are then a linear projection of that, I can't get any form of distribution I want out of it. So it's kind of trivially the case that last layer is not universal. It's still often practical. There's lots of benefits to last layer. There's lots of cases where that can make things much more tractable. And I'm not actually advocating we should never use it. And you'll see in the experiment results, often it works quite well, and it's often there. It can be universal if you know the form. So if you know it's a Gaussian prediction, then again it can kind of become universal. But this goes back to kind of the classification case. It's universal not because it's stochastic. It's universal basically because it's just a deterministic prediction, and you could have just done a deterministic prediction to approximate it.
And trying to what you just said about the biases and stuff, it seems a bit like the way you set up the proof, like you're kind of now shoving it into the biases because you want to use some of the parameters of the model, but like it seems morally what you actually want to do is to have a fully deterministic model and just have additional random inputs, right? Like have the normal input X and then just some random variables that are noise that you also input, and then you have a whole network that maps to that. Do you think that's actually like a practical solution?
Yeah, I mean, that's basically epistemic neural nets. I mean, they have some extra stuff on top of that, but that's kind of what they are set up to do. And yeah, the way our proof works is we prove that, and then we prove all of the others can recover that. And so the key is basically, I didn't destroy that as I went forward, and I've got my stochasticity enough to get back to something that behaves as if it was that. So yeah, and I'm not trying to advocate that this very immediately tells us this is exactly how we should set all of these up. It's an expressivity proof. It's showing that like the intuition of the amount of randomness doesn't actually match up as we think it does to sort of how powerful and expressive this thing is. It's not to go and say, we should do this, we should do that.
Yeah, actually, because this was mentioned, I was thinking of FNets, and I think there are some, there's a paper about doing VI, but basically just injecting noise, and then you only do VI on this actual noise variable. And I think it's interesting that your argument for the partial stochastic vectors actually doesn't like have anything about Bayes at all. We're just talking about how to get distributions. So have you tested the like non-Bayesian terms like FNets against the partial Bayesian? Like, okay, I can see the appeal of partial, but like, is there any appeal to Bayesian then? In the end of the day.
Yeah, I keep wanting to get students to do this, and no one's doing it. Someone wants to do it before we had time to limit. The student finished up before we had time to do that. So it's been on the stack in the list as a while, and I did a master's project last year where I didn't quite get far enough to get into doing this. But absolutely, the question. What I'm really advocating for all of this is we've assumed that like these Bayesian neural networks, this inference formulation is the way forward, and we've just done everything as if it is. And what we need to do is we need to go back and say, okay, there's lots of different ways we can do. Which of them actually behaves most Bayesian? Which of them actually gives us most reduced uncertainties, best consistency, best predictive performance? And we need to kind of, it needs to be a bit more sort of top-down and more investigative and understanding how these things behave, rather than saying that like from first principles, this is how it should be, and therefore we're going to go and do it that way. So, okay, so we've shown theoretical expressivity, we've shown that this sort of intuition that the number of random variables corresponding to sort of how powerful it is doesn't match up, it's not really true, and therefore we can't really justify this full stochasticity because it's in some way clearly giving us a more powerful model. As Razvan pointed out, it's possible it does, but there's no demonstration of that, and it certainly doesn't asymptotically, and there are definitely sort of problematic cases in destroying information as well. So of course we then come on to probably the key question for all of it, which is practical performance. It's sort of, should we be doing Bayesian RX because they work? It's often argued that, okay, they're problematic everywhere, but they sort of work. And what we kind of find is not really. They're kind of no really better than like some of these other things that you can just sort of do instead. And then to start with the conclusion that it's a bit sort of time, basically we don't sort of find any systematic benefit for full stochasticity across, we do 4 different inferences, 8 data sets, and there's definitely no clear trend to basically more stochastic networks performing better. We're not saying they're always the worst, or there's like one clear thing that's always better than either. It's just there's no kind of, it doesn't seem to be any empirical justification for what's essentially the de facto choice that everyone already makes. And as Alex pointed out earlier, there are disadvantages. There's costs, there's memories, there's sort of instabilities, and we're dealing with all of that pretty unnecessarily, I think, basically. So to start off with a super simple example, we've also got some regression. We could do variational inference on all of the layers or just the last layer, and we can get some weird behaviors where basically VI over all the layers can give us this really kind of silly behavior, whereas actually stochastic last layer can actually give us something quite good. Similarly, sort of HMC, it's not a Stark, but if we do HMC on the first layer, in this case it was giving sort of higher uncertainties than kind of HMC on all layers. So again, it's not matching up, it's sort of more stochasticity, it's more stochasticity at the end.
Your previous slide. What is the attribution function used for that?
Not sure. I didn't run this myself, I can't remember exactly.
I think, we have some results basically saying that if you have, well, this is kind of in between uncertainty setup, right? If you have this fully stochastic thing and then you use random networks, then this thing will happen. Okay, you can prove this thing will happen. So I guess this basically says, well, it is possible that for some architecture, well, and combined with some inference method, you will have pathology behavior, right? I mean, the question here is whether, this is generally true, or, there might be some other kind of combinations that this will hold up.
Oh yeah, totally. I'm not trying to say here that all variational inference is terrible for neural networks. My point is exactly pathologies can occur and you can get these weird behaviors that you don't expect. This is not a There is like an infinite sort of ways you could set this up. I'm sure some of them will work. We didn't fight to make this not work. This was just the default setup with how people would run it with using other people's code. So I think we took here, I think Sebastian, who's an author's code from the last paper, and just run this directly, and this is what it gave us. So this is, yeah, it's a point that like things go wrong, and this is not like a hacked result, it's just sort of an example. So moving on, so it gets interesting when you look at some other things that you would expect to just do globally. Like a Laplace approximation is not necessarily that hard to do over everything because it's nice and cheap. But again, it doesn't really kind of sort of work out. So here we're doing, on the grey is a sort of your map estimate, the blue is a fully stochastic network, the orange is in this case input and outputs. Layer stochastic, and the red is where we use some swag stuff to sort of decide which things to put Laplace on and which not. We can then look at what happens as we sort of corrupt the input data. So one of the things people often want to use Bayesian neural networks for is sort of better generalization and less overfitting. And what we generally find is, yeah, across all of these, there's no particular sort of benefit for the full stochasticity. So for example, this one here has about 1,000 times less parameters, and it's generally doing sort of better, in this case, on log likelihood. We then try it with swag, and this is interesting because swag, you're just sort of averaging earlier steps, essentially, in your stochastic gradient sense. You're sort of combining steps of your optimization, and so you'd expect here, because this is the thing you already naturally have, it's sort of actually cheaper in some ways to do swag with the full stochasticity. But even here, in this case, doing the input, and first layer in this case of the ResNet was doing much better. The output layer being stochastic in this case wasn't as good. And again, you get some sort of memory benefits for not doing it everywhere. Variational inference, so we did CFAR 10, CFAR 100. Deterministic doesn't do great. But again, I think in this case, input layer stochastic was generally doing the best in terms of accuracy and in terms of output and negative log likelihood. It was the output layer and the last block being stochastic. So there's not really a clear trend. We were hoping that we would maybe sort of see there was often kind of early stochasticity was better or late stochasticity was better, and we just didn't really find any noticeable trend. The thing that was clear was that there was no case we tried where sort of fully stochastic was best. Every time there was something that was doing better than fully stochastic, but what was changing. So it was all a bit much for the muchness, and we need to kind of think more in terms of speed, and sure, there's more work that kind of needs to go. One last thing was, we can look at, in this case now, HMC, and sort of what happens as we increase the amount of stochasticity. So what we've done here is we found the map, and then we are doing HMC starting at the map, keeping most of the variables fixed, but only doing HMC on some sort of, I think it's a random subset of the parameters. And what we see is that there's very much a benefit to sort of test performance as you add some stochasticity. But already by the time 1% of your parameters is stochastic, we're getting a big jump. By the time it's up to sort of 10%, everything's sort of totally saturated. And in fact, it possibly goes up a bit at the end again. And if we look at a sort of a different data set, this is even more stark, where there's a sort of a clear kind of, in this case, kind of benefit to being in this sort of relatively low stochasticity regime. So again, there's not a clear trend where I can say you should all go and do this or that. But what I'm saying is that something was assumed to be kind of fixed and assumed as a known thing that we should be fully stochastic. The jury is totally fully open on, and there's much more things we can look at.
So how did you decide, like, which 10%?
I can't remember, if I'm honest. I think it was a random set, but I would have to go and check. So I'm pretty much done, but the conclusion here, as I've been saying, is there's not a clear sort of empirical evidence for this sort of stochasticity. It's not a clear evidence that we shouldn't ever do it. I'm not saying let's all throw it all away, but we've made this assumption, and there's not evidence to sort of support it that's currently there. So moving forwards, we've got this idea that these partially stochastic networks are just as expressive, they're often better performing, and they're potentially cheaper. And perhaps more importantly, they open up a sort of a new way of thinking. There's lots of other algorithms we can do that are potentially basically stochastic that we don't think about. There's lots of new avenues and new approaches that we could be thinking about that we're not. And I'm really advocating that we should start thinking about all of these a lot more. So to finish again on the meme, sort of we need to stop maybe thinking fully stochastic networks all the time, and let's start thinking a bit more about partially stochastic ones. So again, I'm hiring. Please have a chat if you're interested. Thanks.
Hello. First of all, I just want to say, could you maybe go back one slide? Recently. I fully agree with the second meme, but for the first meme, actually, I'm not so sure. First of all, the kind of like you show some case like the in-between thing didn't work out. Like there was like some physiological behavior for BI, right? Actually, we wanted to show a demo yesterday with iPhone, but we didn't have time. We just on the exact example, and then actually there you see that I want to it's basically what you actually expect it to be. So it's actually not saying that. I think probably like when it's fully stochastic, maybe the problem's a bit harder. But then if you really try to solve it like carefully, it can actually be done in the correct way. And also, I think many of the VI like it's actually like based on a prop. I guess what you're using, right? Many of the based on a prop implementation that you can find probably online are actually always have more or less some like random problems, and then it's actually quite hard to implement it correctly. I'm just saying this, and also in another thing is sorry, in the middle, I think maybe you're saying about maybe like randomness can destroy information and everything. But actually, if you think about this, like we're usually using Gaussian noise, right? And then Gaussian, you can actually do reparameterization trick, right? And then you can artificially double the node, and then you say half a node I use the mean that is going to be trained, and half a node equal to zero mean noise, right? And then that is the equivalent to adding Gaussian noise everywhere, right? And then, so in some sense, the fully stochastic, partially stochastic, I don't know, it's like kind of artificial, right? And maybe one last point I want to say, I'm really sorry, yes, is that maybe like preserving the information is actually not a big issue, because right now in the modern case, I think at least more than 90% of network is based on residual connections. And in this case, it is preserved already.
Okay, so, yeah, okay. So first, I agree this is a bit reductive. This is, as a joke, to be kind of provocative. This is not, I'm not really saying we should entirely forget fully stochastic networks. And as I said earlier, if there are cases where there is benefits with, say, natural gradients or whatever to being everything fully stochastic, that's perfectly valid. It's just, it shouldn't come from the Bayesian formulation itself, because it's not behaving as a Bayesian model. That Bayesian formulation itself shouldn't be a justification. But say we have stochastic gradient methods, and we can say, oh look, when you do stochastic gradient methods with natural gradients, it's kind of doing a bit Bayesian, so therefore that's a justification. That's totally fine. Secondly, the thing with the fully stochastic case with zero variance, yes, but you don't generally want something as a limiting case in your set. So this is on the edge of that set, it's not in that set. So it's going to sort of, you're going to have something that's kind of running off to infinity to actually try and do it. And then all manner of things are going to kind of go wrong anyway, because actually you're creating problems when you do that, because usually you've got it sort of a log variance and you're mapping it, and something's going to be going where you don't really want it to go. Moreover, if we're doing a fully stochastic network to recover something that isn't fully stochastic, so it's I think a bit of a waste. And so the third point again was, I forgot.
Oh, it just like a residual connection, right?
Yes. So yeah. So the yeah. So residual connections is another way of potentially nicely setting it up so that you can get it around it. It's the key is, yes, you need something information preserving, and a skip connection around a fully stochastic node is a perfectly good way to do that.
Okay.
Really nice work. I mean, it's really interesting, and also to have that more. I think that's the existence or sufficiency proof, I would call this, for the predictive uncertainty. I think this is really useful to have that, to know that what we actually need at least, right? My question would be so if we now sort of go towards more partially stochastic networks, right? Can we still get sort of all these benefits that we would want to get from Bayesian inference in the end? Because I mean, I don't necessarily think that we start with Bayesian as we say we want to have all weights stochastic. It's more like, what is the objective if we don't do that? Because then all the other weights are kind of like hyperparameters, you could say. Like if you make it more extreme, and it's like deep kernel learning or last layer kind of thing that doesn't really work so well maybe. So I'm wondering, what are we doing inference on?
I think that's a key question. We don't necessarily know the answer. I think what I'm arguing at the start is that we didn't get what we wanted or thought we were getting when we set up as Bayesian, and so we need to stop pretending that we've got something from it. I would say one good way of looking at it is I do quite like the sort of epistemic neural network way of thinking about it, and thinking in terms of kind of really correlation between predictions and kind of how we can set architectures up. And I think, again, that there's a lot of stuff we need to think much more carefully just in general architectural constructions and how can we set up an architectural construction and our training schemes, and think almost more of a deep learning way and less of a Bayesian way about a lot of this for how we can get it. And basically stop dismissing stuff because it's unprincipled, because actually it's all unprincipled, and we need to sort of,
Let me first also something. So I really like sort of how you phrase it now in the end, and I think we should think a bit more like that. And one thing that I think we started doing in deep learning, and I would like people here to do as well, is to think about the learning process, not just expressivity. And there, it reminds me sort of something that MT said, which is like when you're fully stochastic, that acts as a smoothness that actually makes the loss surface well behaved. Is that not real? I mean, that seems like a good reason why you'd want to be fully stochastic. Because you talked about instability, is it really more unstable to train fully stochastic model? In your experience, or?
I don't know, I mean, yes, generally, I wouldn't say, I mean, there's probably people in the room that have got more practical experience training these than me who might be able to answer that better. Yeah, maybe things are smooth, and maybe there are other reasons, but I'm kind of arguing that that's basically we only need to be thinking, and those kind of arguments, rather than the formulation that we've currently got.
Last question.
Okay, I can really spice things up. Okay, so if I somehow become a really practical deep learning people, I would basically say, okay, I would also say no to even partially stochastic networks, or even let's say EpiNet. Because to me, right, from the practical point of view, the most problematic thing for Bayesian neural network, okay, is actually Monte Carlo. The computation cost is just way too high. Okay, so I think depending on how you actually design, let's say, the path in jet randomness, right, with EpiNet or with neural processes, or with, let's say, your method of that, even if you put, let's say, the randomness in pretty low layers, right, it means that if you do Monte Carlo, you need to do multiple forward paths. Okay, so this is the thing that if I'm becoming a pure deep learning person, I will absolutely hate it.
Yeah, but I care a lot about active learning, and in active learning, if everything's deterministic, there's basically nothing I can do to say how it will change. So I kind of agree with you in some ways, but I would also say that we're not just usually looking necessarily for direct predictive uncertainty. We also want a case of how things will change. And if we've got some samples, that gives us a way of doing it, because we can kind of look at, okay, how will these samples change in weight, how will one become better than the other? But if I just have a fully deterministic network, it's much harder potentially to sort of say the change. So I sort of agree with you at a high level in some bits, and this is something to think about. But say we've got very complicated output distributions, it may be very difficult to do that fully by parameterizing it. It may also be that, we care about reducible uncertainty estimates. So I think there are still reasons for that, but I agree this is something we need to question, and this is something to think carefully about.
Great.
All right, thank you.
Okay, so we'll start. So this is the last talk of the day. It's my pleasure to introduce Adam. He's a professor at University of Alberta and a CPRI chair, and he's going to talk about continual subtask learning. Adam.
Okay, so I'm going to try to yell into this thing because I don't want to hold a microphone. So if someone online can't hear me, hopefully they'll tell us, and then I'll.
No, they can hear you through that mic.
I know. Yeah. So I want to go like this, and so I can't do that with the microphone. Yeah. So I'm a little bit of an outsider to this group. I came here last week, and it was very overwhelming. A lot of strange terms, but you know, as we've gone on, as we've discussion yesterday, we've talked about modularity and things like that. It's becoming more familiar to me, and I think this is a really fertile ground to get some of you guys interested in some of the stuff we do in reinforcement learning. And it's really useful that Rupam set the stage because I was a jerk and I didn't explain reinforcement learning very well, but he did, so I don't have to worry about that anymore. But yeah, so I don't have a lot of fancy algorithms to sell you today, but I do have fancy problems that I want to sell you, and I want you to come work on our problems because we need help, and I think this is where you guys want to go. So the workshop started last week with the video of the baby. It also restarted again with the video of the baby. I've used this video in many of my talks. This is my nephew Lawrence. And we often show these videos, but we don't talk about them enough. We just show them and people are like, yeah, you want to build a baby. But when we look at this, we should observe some things. Watch how this baby studies the plastic every once in a while. It becomes very, very focused. It's alternating between things that look like pretty random motor babbling and also intense focus, like something caught the baby's attention and it started doing things. And of course, there's all kinds of crazy stuff going on here. It flips away from his very imperfect control of the world. His mom is holding the video screen and moving things around. These are the kind of learning systems that I want to build. And my discussion of this video is all about the behavior, what the baby is actually doing, not what score it's getting, like what top score did this baby get? Is it state of the art? I don't care. I don't care about that stuff. I care about what the baby's doing. So I've been showing videos like this for years and years and years, motivating my research program. It doesn't always land well depending on the groups. So, you know, I showed this video just because MT showed the video, but I actually motivate things kind of a different way nowadays because of the way I've shifted my own research program. And so I'm going to talk about the need for continual learning. I also like calling it tracking. That's exactly the way I think about it. But in the real world, I think about applications, I work on applications, and it drives my fundamental research program about how we need to build better learning systems. And I'm going to go through two case studies. One, I'm just going to look at a deep RL system that we looked at when I was at DeepMind, and just a basic demonstration of, those systems are not ready for continual learning, at least in the way we're thinking about them. Then I'm going to introduce this problem of continual subtask learning. Then I'm going to do a small experiment in a non-stationary bandit-like task. Again, I'm not super pumped about the algorithms being used here, but I am super pumped about the problem settings that we're looking at. And then finally, I'll take some steps towards moving that towards MDPs and function approximation because the bandit setting is way too simplified. But I feel justified for the bandit setting experiment because last week we spent 20 minutes discussing how to estimate a mean online. So I'm going to do more of that. Yeah, so my basic claim is that many real-world problems require continual learning. And so I work on a system like this. This is a water treatment plant in Drayton Valley, Alberta. I've become pretty good at describing water treatment by just doing an animated arrow. And so water comes into the side of this building in a big 2-foot pipe, just right where the arrow comes in. It goes into this big tank. This tank is where you put chemicals in. It's the coagulation tank. Basically, you're putting chemicals in there and mixing the water because you want the solids to clump together, because we want to filter the water, because we want to drink it. So after it spends some time in the mixing tank and you add some chemicals, it goes off into the two parallel filter banks here. And the way they work is pretty easy. There's a bunch of little floss hanging down. And the way I think about it is that it's like you have a straw and you put a straw in water and you want to suck water into the straw, but you cover the bottom. And so the only way you can get water into the straw is if you suck it through the pores in the plastic. And when you do that, it only lets clean water through and all the dirt and debris and contaminants stay on the plastic itself. And then so every once in a while, you know, that filter floss thing gets really messed up. And so you have to clean this filter. And can anyone guess how you clean a filter in this system? It doesn't involve people squeegeeing them off. That's expensive. Think of like a process. You've got lots of water. You just run the process backwards. You run the water through the system and it goes out through the pores and blasts all the crap off the filter membrane, and then you drain that tank. And that's all happening in those rectangles. There's 2 of them because you want to have redundancy in your system. And so this is a system we've been working with for a while now. We've used reinforcement learning to control chemical dosing. We've used reinforcement learning to control that cleaning schedule, which we call backwashing. This is a real live learning system that you can use, and we've done this in multiple locations. So it's not just this plant in Drayton Valley, Alberta. We've done it in mobile deployments in British Columbia. We've done it in other places too. And so you can do reinforcement learning in the real world, but it's a continual learning problem. And so let's just talk about reinforcement learning for a second here. So Rupam already explained it really, really beautifully. So I'll just draw the picture again, except the difference between our 2 diagrams is Rupam was writing state and I'm writing observation. I think that's perfectly fine for the purposes of these talk. I just want to emphasize the fact that I don't have kind of MDP state, right? I don't have a sufficient statistic to summarize the history of interaction. I have observations, and we're going to need to build those sufficient statistics. I'm not going to focus on that in this talk, but I just want to talk about that. That's my problem set. But of course, this is not what we do. And so this was already introduced earlier. You know, the world is really, really, really big. And so this is the setting we should be thinking about. This is exactly the setting I'm in water treatment. And so there's lots of implications of this, but like the way to see this very, very easily, and we can argue all you want, but as soon as you start putting the other agents in the world, it becomes very obvious that the world is much larger than the agent. Because the agent wants to interact with the world, and if it wants to interact with the world well, it might have to model the minds of other agents. Each one of you has a very big mind. Let's throw that in the environment. That's a big thing. And in fact, the agent is in the environment as well. So if you want to predict and control the world in an efficient way, you're going to be dealing with something that's going to be vastly bigger than your agent could ever hope to be. And this is interesting because it has all these implications. Now, it's eventually just going to lead to tracking, but I think it's useful to point these things out. So we're never going to accurately know the state of the world. Even this thing where we're trying to compute the sufficient statistic, that's always going to be an approximation. We can't represent the optimal policy, which people love to talk about in reinforcement learning. We can't have the optimal value functions. That's not possible. And any models we build are going to be gross approximations to the world. That's just the nature of it. There's things happening somewhere in Africa that I'm not modeling very well. And if you ask me about it, I have a shitty model about it. And that's just how these things work. I guess I shouldn't swear while we're being recorded, but anyway. And so to get to the tracking part, it's all about this appears non-stationary to the agent, right? It has an incomplete observation of this world. And so that just appears as a non-stationary process to the agent. And that will just be the reality that the agent operates in forever. And so, you know, just to beat this dead horse a little bit more, when we talk about water treatment, you know, weather and climate matter. And of course, you could put in the time of year and all that kind of stuff. But, you know, the last 2 summers have been, you know, hotter in Alberta than they ever have been before. We have 100-year floods, 100-year fires. 100 years is supposed to mean it happens on average every 100 years, but now they're happening every couple of years. All of that stuff is unprecedented. Mechanical wear and tear, like Rupam works on robots, he sees the same kind of thing. Mechanical systems change over time and they're not always sensorized in a complete way. And so you just have to deal with that stuff. And then maybe the extra fun thing here is we've got operators walking around and they change valves, they add more chemicals sometimes, they shut stuff off. And those people are really, really hard to predict and model as well. And maybe the one difference here that I'd like to emphasize is that unlike a lot of other people that talk about you know, doing learning in the real world, they always talk about how crappy the data is. Actually, the data is really, really good in these kind of industrial control settings, but it doesn't actually matter because it doesn't capture all these situations so that I can pre-train something ahead of time and then just deploy it. And this is back to the classic arguments of machine learning. Like, in fact, machine learning researchers 20 years ago were making the arguments to engineers, you can't engineer for all situations. We need to do learning. And now machine learning people are making the argument, well, as long as we have enough data, that'll cover all the possible situations. It's the same argument again. Like, it's weird. Let's stop making that argument and let's start building systems that learn in deployment. And so we have some papers about this where we show what the data looks like. And even in the prediction setting, you can think of end-step predictions. Building static prediction things in the system just doesn't work, but learning online works really well and learns very accurate predictions. And of course, that's the first step to building a control system, right? You have to be able to predict the future before you can control it. And so, yeah, we need continual learning, we need tracking. And there's all kinds of things that we do in reinforced learning. And I'm going to keep being attacking or mean to reinforced learning researchers because there's only like a couple of us here. And it is very, very true. We don't care about stable learning systems, right? Take any deep learning system, you run it once, state-of-the-art performance, you run it again, really state-of-the-art performance, and then collapses halfway through, or it just never learns at all. And depending on your random seed, you can see this kind of stuff. Generally, we build learning systems that converge. We want them to finish learning to get to a good point so that we can look at it. And what we want is adaptive learning processes. And we also need these agents to specialize to now, because they can't see everything, because they can't model the world, they're always going to be trading off their function approximation resources. So right now is the most important time, and you have to allocate the agent's resources to right now. And we need to build agents that learn many, many things. I'm going to come back to this towards the end of the talk, but we talked about curriculum and we talked about like building modular components and putting them together. We typically don't do this in reinforced learning, right? We do the end-to-end thing where we get a nice shiny policy at the end, but we do in general want to build agents that learn many things about the world and put those things together and organize their learning as such. And we also talked about what's our definition of continual learning, lifelong learning. There's another phrase we can talk about, never-ending learning. That's another good one. Yeah, we have all these names and then we have no definitions. I typically just take the reinforced learning framework as my definition of continual learning because it's a loop. It never ends. Look, it's continual learning right there. And in fact, I would argue that pre-2015, that was the standard view of reinforced learning. You were building continual learning systems. We weren't designing things that worked for 200 million frames and then stopped. And so, in my work, I really want to de-emphasize final scores. And I like what Mike Bowling said about this. He's a games guy at the University of Alberta, but also a great RL researcher. He was like, this is like one of the worst things that ever happened to reinforced learning, that we could define this optimal policy. And then we were so excited. We were focused on that artifact, the optimal stationary policy. And it's not the thing that I want in my water treatment plan, and it's not the thing that I want in any of the experiments that I'm going to show you. But, so, we have big learning systems. Maybe some of them just do it if you put them in the right problem setting, because I think another big piece of this puzzle is, we talked about benchmarks and what are the right problems to try these things on. So maybe we can just do something like this if we take a fairly sophisticated agent. So I'm going to do that first. And I think this is also useful just to show you what some of these degenerate learning systems look like in reinforced learning, just give you a taste of what it's like. So first, this is conventional deep reinforcement learning. You have the exact opposite of what I talked about. You have this massive learning system and the tiny, tiny world. Atari 2600 is almost trivially small, right? 128 bytes and ROM is 4 to 16 kilobytes. DQN is very small. Yep.
Just a question. So isn't exactly this figure kind of puts the question, the whole thing about the world is bigger than the agent? Because we have this situation and still we have continual learning problems. Like that DQN agent struggles to learn even though capacity is not an issue for it.
Yeah, so if I was really fancy, I would have sliders on this, and I would claim to you that even if I just slide this a little bit, it gets worse and worse and worse and worse. And my next experiment, I'll try to make the world just a little bit bigger, and then it'll be even worse.
Okay, so your point is that the size of the world is like strongly correlated with how bad things are.
Yeah. And I'm not going to go through that exercise here, but this was just to also make the point for people who are not in my community that this is pretty much the standard way we operate. And this is DQN. DQN is like our smallest, simplest possible agent. So I want to make a more continual learning problem. I want to make the environment a little bit bigger, but I'm also going to try to use a very strong baseline agent. So Rainbow, I like to call it the kitchen sink agent, which is basically like they made DQN and then they made prioritized DQN and distributional DQN and all these DQNs with hats, DQN with ice cream, all these different types of DQN. And then this paper basically puts all those best pieces together and builds a really high performance system. And I want to do Atari, but I really dislike these setups where you train an agent on something and then you say, surprise, here's a new task you never had experience in and I want you to do well in it. And I don't like those kind of steps, so I often like to think of these things as loops. So I'm going to start my system off and it's going to play some games. And this is my ignorance in Atari. I don't know what any of these pictures mean. What game is this? Great. Pac-Man. You're going to play Pac-Man for 20 million frames, and then the agent's going to be teleported to a new game. We're not going to reset the replay buffers. We're not going to do anything like that. We're not going to change any of the terms in Atom. We're just going to go right to the next game. This is some game. Then we're going to go another 20 million frames. This is clearly boxing. Why I know that one, I don't know. This is Breakout. And then we're going to go to this one. And then we're just going to keep going through that loop over and over. But the key thing here is that the agent is continually exposed to these problems. It's not just a one-off surprise test environment. It keeps living in these worlds over and over and over. So in principle, it should be able to learn in this setup. So let's look at what happens, okay? So I'm going to show you a sequence of plots here. So this is the first bit of experience. You start the loop with Alien. So maybe that was the first game in the cycle. I don't know. I'm cutting off the labels of access its performance. This is pretty good performance in Alien for a number of frames it was there. So then it learns for a while, and then it immediately goes to another game. Don't worry about the gray lines for now. I'll explain them in a second. You go to Atlantis. So now you start learning Atlantis. You might think because you learned in Alien first, you couldn't learn Atlantis, but you still do pretty well in Atlantis. And then you go to boxing. The curve is a little bit lower here, and the gray one is giving you an idea that it's lower than it should be. But learning is happening here as we progress through the sequence. The interesting thing is what happens as you keep going. So now we come back to Alien, and all of a sudden we couldn't do nearly as well as the first visit. So we took a huge performance drop, and we couldn't get back to where we were, even though we spent the same amount of time in the problem. And then we go to Atlantis, and Atlantis is even tougher. You're just really not doing well. And then boxing, we see a degradation as well. I didn't show you the whole 5-game sequence because it doesn't fit on the slide, but you get the idea. This was going through a 5-game sequence. The gray line here is what happens if you reset the agent every time it visits the problem, right? And so that is a baseline that you could use. It's not a particularly interesting baseline because there's nothing being transferred or extracted across these tasks, but this is exactly what's happening. So being worse than the gray line is really, really bad. And in fact, it's like super catastrophic, like as you spend more and more time. So now I've just shown you what happened in Alien as you visit it over and over and over. It just gets worse and worse and worse and worse. And the reset agent is doing exactly what you expect. It's just the spiky train going on. And so this is both interference and losing the ability to learn.
Somehow, so is there any control, like the data it's seeing is the same somehow, or if you control for that?
It's very hard to control for that in reinforcement learning because the agent is making its own decisions.
Yeah, but just to kind of avoid maybe you fix the random seed somehow.
I think you could.
Where does this come from? Is the question maybe the initialization, but.
We'll talk about what's happening in this particular experiment. I don't think it's a general claim, and I think there's another thing going on here, which is hyperparameters, and that's really hard to deal with because Rainbow is 20 million parameters. It has about 28 hyperparameters. That's really hard to resweep. In fact, Matteo, who's an engineer at DeepMind, did resweep Rainbow for another setup. I have no idea how he did it, but we can't depend on the world having Matteos to solve those kind of problems.
You just need Matteo in that.
I mean, that's a good way to get awesome papers to have Matteo in the loop. But anyway, yeah. So this happens across games. We have results for 10 games instead of 5 games. We have results where you have one game, but then you go through modes in Atari. Modes in Atari are things like in Freeway. One mode has cars, the other mode has cars and trucks and things like that. And we see a pretty consistent pattern across the board here. And we even mess with the schedule, like how long you are in each one. This is a pretty reliable phenomenon. This is taking Rainbow as an artifact and saying, let's study this complete agent and see what happens. So we can mitigate this to some extent, and mitigation is like the word we often use in continual reinforcement learning, and it's kind of a negative word, and I think it should be because basically we're trying to bolt on solutions to something that seems to be pretty fundamentally broken. But when we looked at what was happening here, you look at the loss. The loss is still going higher and higher and higher, but the updates are getting smaller and smaller and smaller. And in this case, it was because all the gradients were dying and all the activations in the network were dying. This is something that generally happens in reinforcement learning. So if you just look at Rainbow and you just train it in the regular setup that it likes, where you spend 200 million frames in each game, you get to a point where like 2% of the network is active at the end. This is just a thing that often happens. And so of course a fix to that is use concatenated ReLU, which is basically just ReLU of the input, ReLU of the negative input. It doubles the size of things, but it does prevent this loss of learning. But of course, this is not ideal either, right? This is what happens when you just train an alien. And in fact, so we're not only doing worse than just training an alien, we're also not getting any goodness out of visiting the other domains. There's no positive transfer between domains. And maybe for this setup, you might say, well, that makes sense. The games are very, very different. But this is a long-running theme in Atari, right? We have 3 paddle games in Atari, and people don't see transfer between the 3 paddle games. You would think that that would stand to reason that that would be possible. So to plug for CoLAS, this was a paper we had last year at CoLAS. There's lots more results in here. And like I said, if you look at the hyperparameters, I think you could possibly tune this away. But that's also something that I don't think we want to go down that road either. I think there's even more dragons down that road. So, yep.
Maybe if you did like something like training different models on each game and then somehow trying to use that to make sure you stay.
Yeah.
Just thinking like maybe they
Yeah, I think you could definitely do things to resolve this. The question we were asking here was, in a large monolithic end-to-end agent that kind of utilizes all our best principles in deep reinforcement, like prioritize replay, much smarter way of sampling from the replay buffer, distributional reinforcement learning, which there are many reasons to think why that could be good. Could be good because of histogram losses, but it's also probably good because it has many heads on the network. These things can't make a single agent solution that can solve this kind of sequence problem. And I also want to build learning systems where it's not just for a finite set of tasks. It has a large set of tasks and it actually gets to decide. And that's where I'm going to go with this talk.
Sorry, if I can add one point. I think really the issue here is not DRL, but it's a function approximator. So this is the issue of the neural network learning. It's not DRL. It's just in RL creates the right kind of non-stationarity to kind of really see this problem, but it really has nothing to do with prioritize replay, all of these tricks. This is something else. It's just the neural network.
I mean, yes, and then there's the additional problem, of course, in RL is that your learning system gets screwed up, which screws up the policy, which screws up your data collection, and then it's a death spiral, right? And that's just the life of working in reinforcement learning. So like when Razvan showed the double descent curve where you train and then it gets worse and then it gets better again, that's unlikely to happen in RL because you've destroyed your policy in between. Yep.
So for me, I think it's not just the issue of the function approximator, right? It's the issue of the function approximator plus gradient.
I'm going to keep going because the last talk was 2 hours long. All right. So and this was my question earlier about how do we organize knowledge? How do we represent knowledge? Well, when I think of building learning systems, I often think of things like this. I made the picture very small so you can actually see the components, but I wanted you just to see that we have boxes and there's arrows between those boxes and we're trying to reason about what does this box do? What's its job? How does it feed information to other boxes rather than just one box that takes in images and outputs pi star. And so when we think about these things, I think these are fairly defensible things in the reinforced learning setting. We need to do state construction, right? The world's partially observable. We need to think about how we're going to represent our knowledge. We need to think about how the agent should act and explore the world. We have to do temporal abstraction. That one will take more time. We can go fight about that afterwards. And we need models and planning. I think models and planning, I would definitely die on that hill because that's how we all work. Like, you don't model free your way to the airport here, you plan. And so first I want to talk about knowledge representation, and this is just for Sarath because he said that reinforced learning people think about a single task. That's not at all what I think about. So I like to think about agents that learn many, many things. And so the simplest way to think about this is just agents that have a body that interact with the world and they try to make lots of predictions about the world. And a lot of these are what if type predictions, right? What if would I bump if I drive forward? If I navigate to the lab and then try the plug-in charger thing, will that work? So these are very, very natural, what we call predictive questions. You could call them scientific knowledge. They're basically a prediction about the outcome of a little experiment. And so for a long time, we've been thinking about how we formulate these actually with value functions. And so we call them general value functions because they're just a simple generalization of value functions. Value functions in reinforcement learning, that's the future value of a state, right? The discounted sum of future rewards under your policy. Well, it doesn't have to be rewards. We call it the cumulant because it could be any signal observable to the agent. And we don't have to think about termination in terms of whether the environment is terminating. We can also think in termination in terms of the agent has a termination function and it gets to pick that thing, and that gives you a wide range of different predictions you can make. I won't get into the details of this, and again, we can talk more about it, and I can point you to references, and I think that's kind of the point of all these talks. Read these papers and let's talk more. But the two things I like to think of with general value functions is they allow us to represent procedural and declarative knowledge. So the declarative knowledge are those what-if predictions. If I do this thing, what will be the outcome in a long temporal extent? And of course, value functions do procedural knowledge. That's what reinforced learning does. It learns how to do stuff. So we've got these two types of things, and now we can start reasoning with architectures that learn many, many of these things at the same time. But for this talk, I'm going to focus mostly on predictions, okay? So that declarative predictive knowledge. And so I'm going to think about subtasks as a large collection of general value functions. And in fact, the experiment I'm going to show you, it's going to be a large collection of 4, but the idea generalizes, and it's that I'm showing you a small experiment because experiments are really, really hard to understand. I want to show you a small thing so I can hope you can understand it, and then you can easily see how it can become bigger. But yeah, I'm thinking about general value functions as these subtasks that I want to learn. And you know, just in case you want to learn more about general value functions, you know, this is the foundation of all these ideas that have been used in reinforced learning. Universal value function approximators, auxiliary tasks like the Unreal architecture, predictive state representation, successor features, subtasks and planning, all these can be cast as collections of general value functions. And so it stands to reasons that we can think about building AGI architectures as collections of these general value functions. And so maybe very quickly, I'll just give you a very quick one. So if we were trying to build a robot that cared about the probability that it will successfully plug in if it runs some navigate to charger policy. So we specify the cumulant as 1 and now I'm writing S because that's the agent state, that's not the observation. The agent state has some component of it that notices is plugged in, and otherwise you get a 0. And then this is just a regular action value function that we talk about in reinforcement learning. It's the future sum of these things. The termination is going to happen according to some function that detects the plugin, and it's going to be conditioned on that policy. But you can have many of these value functions. You don't just have one. Okay, so that's my substrate for how I want to build these learning systems. And now I really want to get back to the baby rubbing and studying the plastic, because that's the part that I'm really, really interested in here. And from here on in, I'm not going to talk about performance numbers or things like that. I'm going to talk about behavior of learning systems because I think it's something we should focus on. So I do want to build learning systems that learn to act, and I want to have it act such that it balances all these subtasks efficiently. So I'm going to give the system the policies for these subtasks, and I'm going to walk through some examples to make it concrete for you guys. And we're going to learn those general value functions, and we're going to try to do it efficiently by changing what the robot does so that it gives good data to each one of those, because that's a hard problem, right? How should the agent spend its time in the world to make sure its predictions are accurate? So I call this the continual parallel prediction learning problem. And so the idea is the agent is navigating and exploring the world, and it has this large number of predictions it wants to update. Each prediction is a subtask learned by an independent passive subagent. So the subagent is just watching the stream of experience it's getting from the one agent, and it's trying to update the predictions, and we want that to happen well for all of them. And so just like my water treatment plant, my thing has one body. Just like Rupam's robot, one robot body. It's very common in reinforced learning to have multiple copies of things, but here I'm going to restrict myself to one body. So how does that one body act? And then, just like I said before, learning is never going to be finished. So actually, this is a reinforced learning problem. And this is what a reinforced learning person would do. They would try to turn it into yet another reinforcement learning problem. And so each one of these sub-agents is updating their predictions. That's going to produce some statistics about the learning process. If I can aggregate all those statistics of the learning process of each one of those subtasks together into a number, that could be a reward that then another reinforcement learning agent on top could try to maximize. And so we often call this intrinsically motivated reinforcement learning. Basically, the idea is that internal statistics to the learning process should guide the behavior of the agent. And so just to draw a picture of this for you, so this is our typical agent environment interaction diagram. I'm just going to have my agent interacting with the world, but it's also going to be learning these two independent prediction problems at the same time. And I'm going to, for the purposes of this talk and for this paper actually, I'm going to get rid of environmental reward because it's actually really hard to balance those two things. And this is an important problem enough just to study it on its own. So let's get rid of external reward. And the goal is just to learn those predictions well by taking actions in the world. And so I'm going to compute my intrinsic reward based on the progress of those two prediction learners. So let's do a small experiment in a bandit-like setting just to make this idea more concrete. So this is a stateless problem. It's a bandit, so there's no context, okay? And in fact, we're just going to be doing online incremental mean estimation. And so we have multiple prediction subtask learners, and each one of them is just trying to estimate the mean of some target signal. Okay, so we have n independent subtask learners. Every one of them is going to use an LMS rule like that one right there, right? So subtask learner I is just going to update based on the scalar prediction it makes and the actual signal it sees. And of course, there's noise, stochasticity, and non-stationarity, so this isn't a trivial problem. But the restriction here is that, you know, when the agent pulls the bandit arm, it gets a sample for only one of the prediction subtasks. So it can only update one prediction subtask at a time. So the agent has to decide which arm it pulls to get data to update the predictions. And I'll show you this in kind of like a loop. So if we have our agent here, our agent maybe decides to pull arm 0. That's going to generate some sample from this distribution, which is indexed by 0 here. That piece of information is going to be sent back to the agent. It's going to then update the first prediction about that thing, which is then going to produce a statistic about that learning to produce the intrinsic reward. And then maybe on the next step, the agent picks a different action. It picks the second arm. So that's going to generate a different learning signal. So now we're indexing by 1. So we're going to draw a sample from that distribution, and we're going to send that back to the system, and that's going to update the other prediction. And so you only ever get to update one prediction at a time, and it depends on your action choice. So if you needed to learn this prediction better, you might want to pull that arm over and over and over and over until you get that prediction more accurate. Okay?
Can you just go back to the previous one?
Yep.
This one to make sure. N was, sorry, the previous slide.
Yep.
N was.
It's the number of prediction tasks, which is also the exact same as the number of arms in your bandit problem. Okay? No problem?
Try to understand in what case I have this kind of constraint where I can only make an update on one task.
Yeah.
Related to something.
So not really. This is very much an artificial toy setting so that we can study this problem setting, and then I'll move it to MVPs from there.
Okay.
So I'm not using standard benchmarks here. I'm asking a question about, given the set of restrictions, what kind of solution method should I be looking at? Okay, so we already went through this loop. That's the problem with animations.
So quickly, an alternative could be that I make an update on all of them.
And we'll get to that. So just to make this painfully concrete, you know, imagine all the target distributions you were learning from were constants, right? So when you pull the first one, you get a 4, and if you pull the first one forever, you just always get 4s, and the other one gives you 11.4. That's a very easy behavior problem, right? Pull the first one a couple times, you see it's 4s. Pull the second one a couple times, you see it's 4s. It's easy, right? Both your predictions now have 0 error. There's no stochasticity here. You could also imagine that one of the targets is stochastic, so it's drawn from, you know, a 0-1 Gaussian. So every time you pull it, you get a new number. And if you're learning with a learning rule that has a constant learning rate, that will forever generate learning progress. And this is what people call the noisy TV problem, right? That the agent is attracted to noise, it's attracted to the unlearnable signal. And of course it is learnable. And then maybe the most interesting case is imagine that one of these targets has some structure and they're drifting according to some random walk. So, you know, we have the noisy one there that you might pull a few times and realize it's noisy, but then you have the green one here where every time you sample it, it has some temporal structure. And in fact, you should keep pulling the green one so that it doesn't get too far away from you if you're trying to estimate its mean. So just to kind of give you like a picture of what that looks like. So This is just data sampled under a uniform distribution, but it gives you an idea. You know, we have two high variance targets, the black and red ones. We have the constant target, and we have the green one. And we just want to build a learning system that samples these things in the right way so that it can learn the predictions accurately. And so if we think about behavior, you know, you can look at the paper and you can see that the different solutions and what kind of errors they get. But for the purpose of this talk, I'm really interested in what these systems do. This is kind of an intuitive result that you might expect, which is it starts trying out all the actions uniformly, and then it pretty quickly figures out that the constant arms are easy, and so it stops selecting them. It also figures out that what I'm calling the distracting arms are not the thing they want to pull either, and it slowly stops pulling them, and then it's eventually attracted to always pulling the drifter arm because that's the thing you need to do to keep your prediction error low. So that's exactly what this learning system ideally would do in some sense. And so I just want to talk about two simple intrinsic rewards. If you go to the reinforced learning literature, you'll probably find 20 proposals for intrinsic rewards in the literature, and you'll also find different ways of learning these subtask learners. But let's just talk about two simple ones. So a classic one that has this noisy TV problem is just that, what if you used an intrinsic reward to drive the behavior based on just the total prediction error of the subtask learners? Obviously, that's problematic because you have a stochastic component and you have amount of learning component, right? We can make this part small, right? Because we're getting closer with our prediction to the expected value of the distribution, but the individual samples, YT, are always going to be varying from the expected value. So you're always going to have this irreducible stochastic component if you just have a naive squared error learning system. And then there's another really simple, stupid one that I call weight change, but you can also just call change in prediction, which is just, you could make an intrinsic reward based on the change, how much you've changed your prediction in an absolute value sense. So how much learning did I do when I sampled an arm? I got a new sample from the distribution and I updated the subtask learner. Now you should be sitting there thinking that's also stupid, and you're right, it is stupid, so you have to combine it with something else. So if you do these things with a fixed step size in your LMS rule, none of these things are going to work, right? It's going to be attracted to noise. Depending on the speed of your random walk, it may or may not follow that random walk. This can't modulate its learning up and down. It's a pretty stupid learning system. But of course, we know there's a million ways to make adaptive learning systems. This is using Rupam's AutoStep algorithm, actually. And so it's just a meta-learning algorithm that adapts the step size. And the right way to think about it is that if the errors are in the same direction or approximately the same direction, like they're all positive, it's gonna crank up the learning rate. If the errors are fluctuating around 0, it's gonna start modulating the learning rate down. And so you can see that doing this is already gonna help us a lot. And of course, there's many different ways to do this, right? Like I said, I'm not super interested in the solution here, I'm interested in the setup. And so just to make this more concrete, I'm just going to use LMS rule with either with or without Rupam's AutoStep algorithm, and I'm just going to use a simple band algorithm. In this case, I'm using the gradient banded algorithm because it's actually really, really good for non-stationary learning tasks, but you could use window UCB, you could use dynamic Thompson sampling, there's lots of things that you could use here. And so let's just look at the combination of these things I talked about, right? So you use squared error and you use fixed step size, badness happens, right? So what is this? This is 500 runs of this system. So the solid lines are the average performance, and then the light lines in the back are the individual runs. I like showing both because when you look at the mean, it's not clear what's happening here, because when you look at the individual lines, you can see that sometimes it's focusing on the red one, the noisy one, and then it drops and goes to the black one. And so this system is just not doing what we want. It's really getting attracted to these distractors. If you do this adaptive step size, I guess things are a little better, but it's still attracted to the distractors. It doesn't actually solve that problem. But if you do this weight change thing or this prediction change, and there's other things that work here too. You know, uncertainty reduction is also another good choice here. But if you do the weight change one that I suggested with the fixed step size, it's bad. But if you do weight change with a smart adaptive algorithm, then good things happen. You get the smiley face and you get the kind of behavior that I was talking about. And I just wanted to put this in here. Like I said, there's a whole cottage industry in reinforced learning about developing these very complicated intrinsic rewards. And that's the message I want to get across here, is that This is a complicated intrinsic reward. This is Pierre Odier's work. He's done lots of great stuff in this space, but he has this error derivative approach, which is basically looking at two windows of the error over time and then seeing if the change in them is in the right direction. The issue with that is now your intrinsic reward also has hyperparameters, and now you need to set those hyperparameters, and they're problem dependent. So I have hyperparameters in my agent, I have hyperparameters in my intrinsic reward. I don't want to add more hyperparameters. The simple weight change had no hyperparameters, it just worked. And it also, it works okay, but it's not nearly as nice as the other one I showed. And in fact, we did a bunch of different settings in this paper. This is a very, very simple setting where we just had one drifting target, but you can have it so that you have the same setup, but then they all permute after some amount of time, and can they readapt? You can have different drift rates and all these things. And basically in this paper, we went through a bunch of these classic intrinsic rewards and just showed that once you make the distributions complicated enough, things just start breaking very, very quickly. So, maybe this is a really obvious point, but I think it's worth making, which is the subtask learners need to modulate their own learning up and down. Classically, what we do is we just take whatever subtask learners we get, and then we try to put all the smarts into the intrinsic reward. If you have something you can put in your intrinsic reward that makes it a clearer signal, that should be in the subtask learner and make it learn better. Because if your subtask learners are doing a good job, then simple statistics of the learning process should be helpful to guide behavior. So more sophisticated subtask learners, not more complex intrinsic rewards. And like I said, there's painfully long empirical study of this in JER, but I think it's fun. Okay, so as Rupam was saying, there's lots of limitations with the setup. For example, exploration is trivial. You just pick arms. There's no state space to navigate or anything like that. We were learning one general value function at a time. Obviously, we want to learn many, many things. I want to learn a collection of general value functions. To do that, I not only need to update more than one at a time, in fact, I need to use off-policy learning, which if you're in the reinforced learning community, you should shiver a little bit because that often causes problems. We didn't have any state, no context, right? But we need to have state context. We need function approximation. We need to build big boy learning systems, so we want to go that way. And the things we used here were very, very simple. The gradient bandit algorithm, in fact, in that simple setup, it was very competitive with dynamic Thompson sampling and other much more sophisticated approaches. But in the full MVP setting, we need to think about totally different algorithms. So let's talk about that. So this problem is designed to look like the smallest possible step from my bandit problem, and that's by design, and that's how I proceed in my research program. I build small problems that I can understand and march forward until I get lost, and then retreat back and forward and back over time. And so I built this problem really thinking about parallel learning systems and sharing experience and the utility of learning things in parallel. So here we got this silly agent. Actions are north, south, east, west. This is purely tabular. Start at the start. When you reach one of the colored states, you teleport back to the start state. It's a double T maze. So now I want to build an agent that learns multiple predictions, so 4 predictions, as it navigates the world. And so each one of these predictions is about navigating to one of those goals. So it's a policy contingent prediction. This prediction is about if I follow the shortest path policy to the blue goal, what would happen, okay? And of course, we have 4 of those predictions. And so what we want is, as our agent moves through the world, it gets to update all those predictions, right? Every step in the world, it's updating those predictions, and the game is how should it move through the world such that it gets those predictions accurate, because it needs to get to the ends of those hallways to make those predictions accurate. And so not every action is actually useful for those predictions. The backward step there was not useful for any of those predictions, but that's just the kind of learning system we have. And when you build robots all the time do things that are not relevant to all the things they're learning about. So we need to build systems that are robust to that and encourage to take actions that are relevant to what it's learning about. And so, this agent moves through the world. And so you can think about, again, if it's learning these 4 subtasks, these might be the prediction error curves for each one of these subtasks. So, these ones, as it's moving around, it's making really good progress on those. The prediction error is going down. Maybe this one is like the noisy one where we're not making a lot of progress on. And maybe this one was like the drifting one where it's harder, it's slower, but we are making progress on it. Yep.
I'm just curious, how is this related to like inverse RL?
How is it related to inverse RO?
What's your learn? I forgot what you're trying to learn when you reach.
So these are all value functions. And so I haven't specified exactly what these value functions are, but basically they're a value function where the cumulant is 0 on every time step, but then when you get to one of these colored squares, you get a sample from a distribution just like in the previous problem. So you might get a constant number, you might get a noisy number, you might get something that's following a random walk, and you're trying to make that multi-step prediction. Good? Okay. And so, of course, some of these are easy, some of these are noisy, and some of these are very difficult, and you might need to spend a lot of time. So when you think about this as a behavioralist, you're thinking, okay, well, this system needs to walk to goals, and it needs to focus on the difficult ones, and these decisions need to be based on how well the learning process is happening as a whole. And in fact, here, a round-robin policy, one where it just go to the first goal, then the next goal, then the next goal would be very wasteful, right? Because it would spend time visiting goals when they were all completely learned. I guess there's other people that work here. Okay, so previously in the banded setting, when I sample an arm, I get a number from a distribution. I only update a single prediction at a time. Here, we update all the predictions on every single time step. It's a little bit more sophisticated than that, depending on how you're doing your off-policy learning, but I think this is a reasonable approximation of what's going on. And so here, we're going to take the learning progress from each of the subtask learners, add them all up, and make that our reward for a behavior learner. And so, maybe my prediction algorithm here is a form of temporal difference learning, is really good at learning these multi-step predictions, and we can do it off policy, i.e. in parallel from a single stream of experience. And maybe I'm just going to use something silly here like Q-learning or SARSA, because it's a well-defined on-policy learning problem. It's not a big deal. But I'm still not introducing the environmental reward here. I'm still just focused on this problem of parallel subtask learning. So this is actually really hard, because when you think about it, all those parallel learners might have different timescales of prediction, right? So their learning timescales might be different from one to the other. How fast they make progress is different, and then that has to feed into the behavior learner, which has to then turn that into sensible behavior. There's multiple timescales of learning happening in the system, and we have the learning progress from different components feeding into other components. This usually makes for a really non-stationary big mess. And so it's actually really, really hard to get these systems working well. And this is just one approach we use, and we're now iterating on coming up with better approaches. Question?
Yeah, I did have a question.
Yeah, good.
So I'm wondering, in the end, like I know you call these things cumulants, but you still have to hand define them. So I'm wondering to what extent this is different from just a reward from the environment. Like I could have said, well, I have an environment that has rewards in these places, and it comes like that, and I'm maximizing. Like, to me, it felt like you wanted to do a paradigm shift where we're ignoring reward, but somehow reward is still there and we're doing the same thing.
I'll get back to it. Yeah,
okay. We'll
come back to that. Great question. Okay. Yeah, so we have one stream of experience. So every one of our subtask learners is going to have to use some form of off-policy prediction learning. That's okay. We've actually made a lot of progress in off-policy prediction learning over the past few years. But the intrinsic rewards are very, very non-stationary, right? Like as your learning system is doing better and better and better, the reward driving the behavior is actually changing over time. And that's really, really hard, because almost all reinforcement learning setups we think of, the reward is a function of the state in action. It doesn't change over time. So this actually is really hard. And then just making those subtask learners efficient is actually really difficult. So here we're going to use successor feature decomposition to make this easier for us. This is going to be hard without lots of background, but I'll give you a flavor of what successor features are like and why they're useful in this context. So, we have a state progression here. We're starting in some state. We're going to move through different states, and then we end up at some state st plus k, and we take action at plus k. And you can imagine each one of these points, we have features, and maybe those are linear, or maybe they're the last layer of a neural network, but we have feature layers. We have a feature vector for each one of these state action pairs. And so the successor features for this are just the expected discounted cumulative sum of those feature components, which is actually just a value function. And so yet again, I've cast a learning problem into learning a collection of value functions. So this just ends up, if your feature vector is length d, you're learning d different value functions. And you can do that with temporal difference learning. You can do it off policy. And then why are these things useful for us? Well, they can allow you to decompose things. So we have our cumulant function. We have 4 of them that we want to learn, 1 for each of the ends of the maze. So let's just consider one of them getting to the red one. The nice, beautiful thing about successor features is that you can decompose these things into learning the one-step, what we call the reward model, so the one-step cumulative model. So if the cumulative function for a single step is approximately equal to the features times some weight vector, then we can do this beautiful decomposition where we can learn that weight vector C, and then we can learn our successor features, and then we can just do the inner product between those two things, and we can directly compute our value function. That's kind of the magic of the successor feature decomposition. And so basically, we want to learn a prediction, a value function for getting to some goal. And we're going to break that up into learning the one-step cumulative component and learning the successor features for that thing, because these successor features, and animation's bad again, these successor features are conditioned on a particular policy. So I had those 4 policies, so I'm going to have to learn successor features for each of those 4 policies. But you can do this decomposition, and then when you can do this, it works really, really nicely, because basically we can say, I'm going to have a really efficient tracking algorithm to learn this one-step cumulant function, and my cumulants could be non-stationary, like from the random walk, and then I'm going to learn the successor features using some value function learning approach, but those are stationary. I told you that my policies were given, and so they're not changing, so the successor feature components of this are all stationary, so I can learn them slowly and accurately, and then I can very quickly track the green part. And so it changes the setup a little bit. Now to learn these individual predictions, we're using the successor feature learning algorithm, and then we're just using a basic on-policy algorithm to select actions driven by the intrinsic reward, which is computed from learning all those individual predictions. And so this is a bunch of crazy lines. The thing to see here is we kind of have a labeling convention here of, there's 2 parts of these labels. The pie is talking about what algorithm is being used to learn the 4 subtasks. And then the mu is what the base RL algorithm is that's taking that intrinsic reward and deciding actions in the world. And so the key thing here is that basically to get good performance, this is very bad performance. This is the prediction error across all those 4 predictions we're learning. You really need to be using the successor feature algorithm because these things are non-stationary. But you do have a choice here. Sarso works well. Also Barretto's GPI works really, really nicely here, and it's actually a really, really beautiful fit. But it's also a little bit limited. So, but I told you I was mostly focused on behavior. This is an error plot. And what I really love about this system, what I think is really, really beautiful, is that a natural curriculum emerges, right? So I showed you the animation. The agent takes actions and moves up and down, left and right in that world. But there's nothing in the setup of the learning system that says go to goals, right? I don't actually let it follow policies. All of it is learned behavior from the learning progress of those 4 things. And what emerges is a very deterministic behavior. So it looks exactly like my bandit setup was before. Initially, it's visiting all the different goals. And then for a while, it gets attracted to going to the blue one, which is at the end of the blue hallway, you get a random number. And so the system would go there and say, update the blue prediction learner, random number, this looks great. It keeps generating learning progress, but eventually the system figures out that's not valuable, and it stops going to the blue goal, and then it starts going to the green one, which is when you get to the end of the green hallway, you get a number from a random walk. And so it's the same kind of structure as my bandit learning problem. But when you watch the system behave, the system actually goes to the different goals over and over and over. Again, this is not programmed directly any way into the system. This is just emergent behavior from the process of trying to get your prediction learners to be accurate. Now, I wrote down here, and of course it was clear from the example, that this is a tabular setup, right? And we did all kinds of experiments with neural networks, with linear function approximation, continuous AMRs. We're not doing Atari, we're not doing big things. I actually don't know how to do them, not because I'm stupid, but because actually I don't know how to run really good experiments in those sets, because we need to do multiple runs, right? And so it's going to be a little bit mean to this group. Everyone in this group is talking about, what are the distributions of things, and are you making statistically accurate assumptions? And nobody defined their error bars in any of their talks this week. No one talked about how many seeds they used, right? Okay, maybe you did, sorry. But this is common, right? Like this is a usual thing. And when I want to move these things to bigger domains, that's a hard challenge that I don't know how to get across. The reinforced learning community just doesn't care. Like couple seeds, good enough, report standard error. What is standard error? You're assuming you know the variance and you're assuming it's normally distributed. These things are generally not true. I have a whole paper about how the distributions are not like that at all in reinforcement learning. Anyway, scaling up is hard, and I think it's also important that we can build small experiments so we can understand behavior and I can look at those things and see it's doing the right thing. The successor feature thing was like a beautiful fit. Like it was like successor features were designed for my problem setup, but you can do other things. And so like one idea is non-stationary replay. Doing a replay for this learning successor features is a good idea because that's a stationary learning problem. Doing a replay to learn a non-stationary cumulant function is a stupid idea because it's literally drifting away. You just have a replay buffer full of irrelevant data. But you can do non-stationary replay, which is you estimate the reward component as a fast-moving function, and then you plop that into your replay tuples, and then so you can get rid of the successor feature part, which is a little bit problem for scaling, and also successor features have this really dirty problem that getting those features right for the one-step thing is actually hard, and if they overgeneralize it, it really breaks in a bad way. There's also some really cool ideas that come out of reinforced learning about emphatic methods and interest. Rupam has worked on emphatic methods. These are basically a way for the learning system to change how it weights the updates. So in a reinforcement learning system, how much function approximation resources you put to anything is based on what the agent is doing, right? So if I spend all my time giving talks, that's the most important thing. I'm gonna over specialize in that. But sometimes that's not always the right thing to do. And in fact, our divergence cases in reinforced learning are often due to misalignments and state weightings. And so emphatic methods are a way to principally tell the learning system which things to care about and how to modulate its updates that way. So we also explored that in the paper, and it actually was very, very helpful. And then interest is this thing where you say, I don't care about getting my predictions right in some of these states. And so my example is like, I don't care about giving talks underwater. Being underwater is not relevant to my academic career, and so I shouldn't care at all about whether I do good talks underwater. So there's lots of interesting algorithmic things that we can do in this direction, and we've started exploring them. So next steps, I was using Sarsa. Sarsa is like the simplest, most naive reinforced learning system you can have. I think we need to do much better. I think we need to integrate models and planning because this is all model free. Model free is very, very sample and efficient. We want the system to actually imagine going to these things and changing its learning progress. I want to work with larger environments, and I really dislike that I was drawing things from a random walk, but that was just a trick, right? I was imagining that my agent is in a world where there are some things that it just has to continually attend to because they're hard. And so that's what that's simulating, but it sucks. Like coming up with a random walk and setting those parameters, it's gross. So I want naturalistic problems that exhibit this kind of structure. And of course, we want to add back an environmental reward. We want to care about learning systems that try to achieve goals. And then as Andy Bartow says, intrinsic motivation is for when its goals are satisfied and what does it do with the rest of its time? What was that baby doing? That baby wasn't hungry, it wasn't tired, it was learning about the world, right? So we should be able to put these two things together. And then where did the subtasks come from? They came from me. And in fact, it's worse than that, right? Because also the policies I specified the policies. The policy one is easy to get rid of. You can just learn the policies at the same time. We've done it, it works fine. But where do those subtasks come from? Previous work, eons ago, Satinder Singh, Andy Bartow, they did novelty-based things. I was actually gonna start with that and say, okay, they did it in the early 2000s, but they did it all in tabular. We need to bring this to function approximation. But one idea for this is what we call the cycle of discovery, which is basically this idea, and this is a huge idea that I'll just either confuse you or make you angry, but we can talk about it after the fact, which is we have this loop. And this loop is that the agent is learning its own state representation, and then we want to use that to drive subtask discovery. And so the idea is that if you have a good representation of the world, what does it do? It's going to be compositional, it's going to be abstract, it's going to break the world up into its components, maybe those are good sub-goals. You know, if you have a feature component that gets large because you're in the middle of the room, maybe that's a good sub-goal. And so we're starting to work on that now. Not surprisingly, standard feed-forward ReLU networks, this does not arise, and it's not a good idea. But I think it's a good way to drive representation learning research towards features that would be good sub-goals to obtain. So my take-home messages for this are, you know, continual learning is all about partial observability and non-stationary. It's like two sides of the same coin. And you know, there's just a whole cottage industry of saying deep RL doesn't work in continual learning. Sure, I showed you yet another example of that, but like I said, I do think it's illustrative of what the problems look like. I think subtasks formulated as collections of general value functions is a general idea, and I think there's lots of legs in it. I didn't talk about it today, but models of the world could be thought about as large collections of value functions, and we can talk about the details of that. And I really think that our learning systems can't just maximize external reward, they also have to pay attention to their own internal learning statistics. There's lots of different ways that you can do that, but I think if you agree with that statement, we're good friends. Wanted to say one more thing, which is, you know, the environment matters, and I think this is where we get most misled in reinforcement learning. I think it's where you guys most get misled also, because it changes everything you do. So we talked about, you know, how come compositionality doesn't rise? And it does arise in large language models because language has that beautiful compositional structure. That's a key, right? Atari games are stupid. People will tell you, people who know about games tell you that Atari games were some of the first computer games, and they didn't have a curriculum. You just start off in Atari and you live or die, and it doesn't really change over time. And you have to go to more fancy games like The Legend of Zelda, where Link starts off in the village and nothing bad can happen, and you learn about your sword and stuff like that, right? A very natural curriculum. And so, you know, we can't do Atari. So we did StarCraft, right? And in fact, I was there at DeepMind when that happened. And, you know, we were all talking about, okay, if options and temporal abstractions and models, if they don't matter in StarCraft, they don't matter anywhere. And it didn't matter, right? Like not even a little bit, just giant end-to-end learning system. And then Minecraft, okay, Minecraft, you must definitely have to learn skills and models and things in there. And the answer is, so there's models there, but we can have a discussion about what exactly is happening there. We definitely didn't need skills or hierarchy there either. And I think there's an interesting phenomenon going on here, which is I think that we need to think about learning systems and environments that are friendly to learning. So think of babies, think of smart animals. Prey animals are, when a deer is born, it gets up and starts running in like 30 seconds because the world is trying to eat that deer. If you go to higher animals, what happens? They play with each other. Who keeps those things safe? Mom keeps them safe, right? They're not worried about dying. And I think that is something that has held us back a little bit, is we need to think more naturalistic. We build these in Minecraft, you know, I don't know a lot about Minecraft, but I know that at some point it becomes nighttime and zombies are going to kill you. And that happens pretty early, so you don't have a lot of time to figure out how the world works. And that's just not how learning systems in the world work. And maybe the last point I want to make about it is, there's also this really interesting thing. There's a physical curriculum in humans and animals, right? When you brought your baby home, did it navigate to the end of the ant maze? No, it couldn't move. It was only on its back, and it spent the whole time looking around and looking at high contrast things, because that's what babies do. They learn about vision. And then they start moving their arms, and they start learning about how they can extend their arms and not. And then, you know, parents are there always with the toys, ready with the toys. And then as soon as the baby's ready for the toys and object manipulation, that happens then, right? But there's a physical curriculum that operates in parallel to the learning curriculum. And I think it's, I don't know what to say about this, but I think it's a fascinating observation that we don't really pay much attention to. And then the last point I want to make is that Rupam showed videos of robots, and I think, again, like the baby video, it's easy to miss the point. I wanted to show this video. This is Linda Smith's work from Indiana University. I spent 2 years at Indiana University. She put cameras on babies of different ages, of dozens of babies, and just recorded what they look at and what they do. So this is a 12-month-old. This is the data stream of the learning system. Like, it's insane. Look how shaky that is. It's just wandering around. There's all kinds of sensory stuff going on. This, of course, is ignoring all the auditory and tactile things that are happening. These are the data streams we want to talk about. We could build a robot that's less shaky like this, but then maybe it also is less agile, right? So there's a physical trade-off there too between the data collection and the system itself. And so I think these are just fascinating things. And I'm not one of these people like, we have to build exactly like the baby. That's stupid. We have computers. Computers can run really fast. They can do things in parallel. We should exploit all that stuff. But we should be inspired by natural language systems, not constrained by them. And that's it.
Questions? If not, I can start with one, which is like on the StarCraft and Minecraft and all this. So do you really think it's just the environment? So my intuition is that it's really the how we evaluate the system is a problem. Like if you evaluate the StarCraft properly, you would need. So I guess you would agree with that.
Yeah, I think there's all kinds of things going on as usual. So I think like the adversarial environment, the evaluation function is just all about score and performance, not about watching what the system does, all those things.
This isn't really so much as a question, it's just like curiosity. So I'm not sure I have an opinion on it, but I'm wondering about yours. Like there are people who claim that like these baby kind of videos that they construct like data sets that like self-supervised learning methods seem to have a decent amount of correlations with that. Like, what are your thoughts on that kind of stuff?
This is me a little bit guessing, but I do recall that there's lots of experiments where people try to evaluate passive learning systems, and I think passive learning is fundamentally hard, and so I'm not sure how much it informs these kind of active learning systems. Like, you can't learn certain things about the world if you only just get to passively watch a data stream. Like, you need to explore the world, you need to try things out. I remember years ago when I was a young grad student, I went to a talk by John McCarthy, and he had this gears problem. And so we all know John McCarthy, the person who made our field, thanks to John. And he had this gears system where he said the agent would look down and it would see the gears from above. And he would want the agent to come to understand how the whole system worked just from looking above. And I thought that was just a crazy perspective. Like, if you really want the system to learn that there are gears and this is how they work, it needs to like look in there or take things apart. And I think that's a fundamental principle of learning.
I really like all of these examples. They are very thought-provoking. And so then I start to think, how can we don't know much about RL, and so I like Razvan's comment also that, it's a neural network problem. Then I get, okay, maybe it's solvable if you're making these algorithms, right?
Yeah.
And for me, I think the most interesting part is representation, because I think if I could solve that, then maybe, or make progress on that, then a lot of things are kind of already there. And when I think about these multiple places where, I think really beautifully done, by the way. So it's very clear that there's a very clear representation, and these four things differ in that, right? So yeah, I'm just wondering, how can we do this? Like, if we make things in supervised learning, like let's say make an algorithm like Adam, or we get some memory to it.
Yeah.
If we apply this naively on this setup, there should be some signal, right? It should do something interesting. Like, if we start to look at our variance estimates, or we start to look at these memories that we like replay examples or gradient matching I was talking about.
Yeah.
Do you think that would be useful?
Yeah, and I think representation learning is one of the areas that reinforcement learning needs the most help. So like, when we look at standard supervised learning, we can look at the networks and we can see them getting compositional abstractions through the layers. There's different ways you can analyze. You can have Gabor filters. You don't get that stuff in reinforcement learning. In fact, my argument that is in reinforcement learning, neural networks just learn this really complicated nonlinear function that encodes a policy. There's no abstraction emerging. None of that stuff is actually happening. And so the question is why? Is it because the diversity of our environments and how we evaluate them, or is it just because the representation learning ideas that we're importing from supervised learning, because we don't have any new ideas for representation learning, we're just borrowing them, are they just not appropriate for this problem set of where everything's non-stationary and temporal and things like that? So help us with representation learning. That'd be the first place to start.
Let's talk about it.
Yeah.
I can have a remark on that. One thing that I noticed when playing with RL and the neural networks is that the functions you need to learn in RL are considerably less smooth than the ones you get doing supervised learning. And neural networks just don't deal well with non-smoothness.
If you ever try to learn something that's not smooth, like you have issues. And I think that that's also like a wall, which is like why some of these things you need to do them in RL because you don't necessarily have the right, or like you need to simulate the non-smoothness in supervised learning and see that's a wall. But I think that's like a kind of like also like a cool problem that you don't
Do you mean that when you switch from one game to another game,
no, it's like if you just look at the value function over the states, if you have states on the x-axis and y-axis.
Because you can beat human performance on like that setting, right? So that it must be doing something there.
Sure, but like where you have issues is when you have these non-smooth transitions, when you have very similar states that have very different values, like neural networks are not that good, and that's where, you know, if you put like MCTS or whatever on top, like you get a lot out of it because it can deal with that. Any other questions?
Not asking questions.
Oh,
it's late.
Okay, so then we can
continue
continue the discussions in rates and other things. Oh, let's thank the speaker again.